Yeah, we're live. Okay, hello and welcome to your 2026 weather and climate live stream. Okay, I've at least gotten the name right. I was so nervous about that. I am your very first host, Virginia Schutte. We will be broadcasting live and continuously for 50 straight hours starting right now. Our programming is a bunch of people in the scientific community sharing their incredible work, and our purpose is to get you and as many people as possible to contact your members of Congress in support of science. But first, I want to know who is here with me. I know I'm not alone. I can see it on YouTube. So I want to know from y'all in the chat, who watched the stream last year? Put first if this is your first time, put second if you were with us last year. I want to see what kind of composition we got here. Oh man, I already see some of y'all were here last year and you're hyping up in the chat. I appreciate that so much. Hi, hi, hi. Hi to everyone who's joining. It's so nice to see y'all. So many seconds. Okay, back for year 2. So excited. We Heart Earth, let's go. I love this. So we're all going to get to hang out again together. I was thinking about my crew that I hosted last year who settled on OGs as a reaction to anything that's maybe not going our way. So I'm excited to see my OGs 5 to 7 folks. Next thing I want you to do in the chat, tell me where you're watching from. I want to see where we're getting you pulled in from. If you're in the United States, if you're abroad, how many states we got. So many of you are back for year 2. This is so great. Thank you for letting me know that you've come back for round 2. Can't say I'm excited that we're doing a round 2, like that we feel we have to, but I'm excited to be back here with you. Okay, you are from the US. Thank you. But like, is there a state in the US that you're currently watching from? Massachusetts, New York, Georgia, France. Welcome from France. I'm seeing several New Yorks. So I think New York is currently winning. Watching in DC with my AGU peeps. Thank you for your support. Kentucky, that's where I'm from, Colorado, Maryland, New York. Okay, so we've got everybody all over. Next question. I want to know, this is a bit of a challenge. Can you put an emoji in the chat that tells me what kind of snack or beverage you're going to have to enhance your viewing experience? If you are not snacking or beveraging on anything, feel free to send me a coded message through emoji. We're going to see what happens. I'm so excited to guess what you're snacking on. I'm waiting for like a unicorn to come through, in which case we need you on our team to do magical things for us. Okay. So all you New Yorkers, all you second timers, no emojis. No one's snacking on any unicorns yet. Okay. Oh, popcorn. I can clearly pretzel. Oh, this is working. I wasn't sure if you would do the emoji. Vegan food for the climate. Do you feel represented as a vegan by emojis? Someone is, well, you're not eating rain. You must be drinking water. Someone else is having, oh man, chocolate. I wish. I thought about my snack situation before, and I've just got a statistics pun on my mug. I'm telling you that I am statistically not different from a good dad. So I've got water. I'm eating rain along with whoever you were. Okay, I'm going to say that's a pizza and not like a worm pot. Okay, so I also want you to know, you can feel free to ask me any questions as we get going with our marathon stream. And then I want you to also put in the chat, what do you do for your career? Are you in the sciences? Are you in something else? I would love to get a sense of kind of your situation as you tune in. While you were telling me about you, I want to set the scene for us and this second year and everyone who's coming back to us to join us again. I am delighted that you've joined us, you second timers, snacking on rain and chocolate and vegan food for the climate. We are doing this live stream again because you and we have the power to determine the future of science in the United States. Last year, we lost about 20% of the federal science workforce. That's 25,000 people. As a result, we know less about the threats to our lives and livelihoods. We are training less students to revolutionize our way of life. And we have lost years of specialized expertise that we will never recover. Current proposals from our own government for this year are designed to further change the way that science works in the United States. Proposed actions include drastically cutting funding for science, limiting the types of science that can receive support, and preventing scientists from sharing our results with each other, with policymakers, and with you. The most important part of what I just said is that further breaking how science works is, for now, just a proposal. Congress has the power to preserve the scientific systems that keeps millions of people safe. Congress has the power to insist that their funds get distributed as they were intended to be. And Congress has the power to change our current course. We have the power to hold Congress accountable and make sure they act. We at the Weather and Climate Livestream are doing everything we can to make it easy and effective for you to contact your representatives in support of science. Our 100-hour live stream last year prompted more than 30,000 calls to Congress. And in the end, Congress passed a budget that rejected large-scale cuts to federal science agencies. This year, we wanted to do something even bigger than 100 hours from last year to get lawmakers' attention again. So last Saturday, 9 days ago, one of our team members started walking from Central Park in New York City to Washington, D.C. He is headed that way right now. I think he just passed the 200-mile mark earlier today. We have more than 100 letters that he's going to deliver to lawmakers when he gets to Washington, D.C. We've got, I think we're up to 4 members of Congress who are going to welcome him to D.C. So I just want you to know, I know I started with depressing statistics, but this harmony that we are doing here, us on the live stream team pulling you together as a community with us, and y'all viewers speaking out on behalf of science. It's already working. It worked last year, and it is working again this year as we walk from New York City to Washington, D.C. So though this live stream and our very long walk are motivated by desperation, we feel united with you in determined joy. We already know how to ensure that science serves Americans long into the future. We fund science and we protect the integrity of the scientific process, as lawmakers from many backgrounds have been doing for decades. So thank you for tuning in again, and hopefully for acting again this year to make all of that happen. Speaking of joy, I would like to lean into a bit of a vibe shift, and I would like to bring in 2 people who are working a lot behind the scenes. I'm going to have them help me introduce what we're going to do here over the next few days. Viewers, while I'm getting them on screen, please suggest in the chat incredibly silly questions that I should ask them as part of their introductions. I'm going to look at what you do for your lines of work. You are doing statistics, you're a student. I'm a student, but I'm studying physics and astrobiology. That feels like some kind of qualifier I don't want. You're a student and you're studying physics and astrobiology. So let's see, Snackless in New Jersey. I'm so sorry to hear that. You're an environmental consultant. Oh my. Oh, that's a peace symbol. I thought someone was snacking on a bunny. That's totally fine. Okay, so I'm going to get our first other person on screen. Let's see, Andrew Williams. Will you please join me on the stage? Andrew,
Yeah.
Okay.
Hello. Can you see me?
Well, okay. So Andrew and I are in the same place.
I'm happy to be here. Super excited to be part of the stream.
So this is my room.
Glad to be joining.
This is my room.
I'm not meant to be here.
No, because I gesture like this.
But you said that like I was supposed to be. Oh,
away.
what? I'm meant to be downstairs. What?
Okay. I'm waiting to hear him tell me that. We had planned this awesome gag, and if he falls down the stairs, I'm gonna feel so bad.
Right here?
Blushing. All part of the wholesome fun and no liability risk here at the Weather Climate.
I didn't fall down the stairs. So
You
that's a big
made
win.
it. Hey, Andrew.
I did it.
Oh my gosh, nice to see you.
Great to be here. Great to be here.
Okay. Okay, Andrew, it's time to I'm going to get serious. We're getting serious because it's serious business that we're doing. Please introduce yourself and what you do. Who are you? What do you do?
Yeah, so my name's Andrew, and first of all, I'm a proud cat dad. So I'm a father to my cat Cleopatra, that's what it's short for. She's my favorite collaborator, and in my spare time, I'm a climate scientist at UC San Diego, and my research revolves around studying clouds and rain, particularly in the tropics. So, like, if you're on a flight and you look out the window and you see one of these huge thunderstorms, that's the type of thing that really, really just fires my imagination. And the type of questions that I like to think about are like, how will these big thunderstorms change in maybe like a warming world in the future?
Why are you part of the weather and climate live stream this year?
I think that at my core, I really love science. I love this field, and I love the people in this field as well. And I really want to share that with everyone, all of you people who are watching. And over the next 50 hours, you're going to see over 100 scientists from our field, really like people doing the best work on the planet, but also just great people. And I think I just want to share the joy and the excitement that we have for our field and what we think it can bring and benefit people. And we also want to highlight that this work doesn't happen in a vacuum, and it only happens because of federal funding, which is paid for by taxpayer dollars. And so I hope that as we go through this event, you'll learn a lot of science, you'll meet a lot of new people, but also you'll get some sense of like what may be lost if these cuts go through.
All right, Andrew, what is your third favorite type of insect?
My third, okay. Well, I guess we should make our way there, right? So first favorite type of insect, definitely a stick insect. They're just the coolest insect. After that, probably one of those like millipede guys, 1,000 legs. Third favorite, maybe a cockroach, because I've lived in New York for a while, and they worm your way into your heart, So.
Do they, Andrew, worm their way into your heart? Like literally as you're sleeping in bed. I do not live in New York City, but that's the way I imagine you setting that up. Is I live in New York City with cockroaches, and now I love them. We're all friends.
Yeah, they worm your way into your food, your walls, and your heart. So.
Great. I'm going to move straight on from that and bring in our next person from the live stream team. Jonah, can you please come out onto the stage where everyone can see you?
Hi, everyone. Hi, Virginia. Yay. Hi, Andrew.
Hey,
folks watching home.
Hat you have. Jonah, will you please introduce yourself? Tell us who you are and what you do.
Sure. So I'm an atmospheric scientist living in Boston. I'm the Chang Family System Professor in Earth Climate Sciences at Tufts University. I study something called the climate sensitivity, which is basically how much warming will we get for a given increase in carbon dioxide in the atmosphere. And it turns out it's really related to how the clouds will change in a warmer world. So I spend a lot of time thinking about all different types of clouds, from dreary stratocumulus to the sort of exciting cumulonimbus systems that Andrew was talking about before.
Great. Why are you part of the Weather and Climate live stream team?
Well, I've been working in this field for about 14 years now. And when I first started working in it, I was just shocked to see how many, kind of what Andrew was saying, there's so many wonderful people doing work. It feels like there's this whole secret team out there helping us understand how the Earth works, how the atmosphere and the ocean, all the different parts of the climate system work. And when these funding cuts started to come in, I was so sad to think about this precious thing going away and people just not even knowing they had this treasure. So I wanted to help the world know about this wonderful resource that's out there, all of these people doing this great work, and to help protect it. So, and this year in particular, Virginia mentioned a lot of the things at stake. in particular, I want to mention the National Center for Atmospheric Research in Boulder, Colorado. We'll be hearing about it during the live stream, but it is a wonderful center. Many of us use the resources from NCAR, which it's called. And so I want to be here to help folks understand the wonderful science that's being done to help us understand the Earth.
Great. Your question, there's a lot of cloud love in the chat.
Oh boy.
What's your favorite snowflake or cloud process?
Well, I'll talk about cloud process because I got a chance to walk a little bit with Sil Foisey, who's maybe he's somewhere in Maryland right now. I'm not sure, but we walked a bit outside of Philadelphia. And Sil is doing these great shorts on YouTube, and I got to talk about one of them about how there's bacteria that actually help to seed clouds, that help to deposit ice. It's very hard to form ice particles in clouds, but there's this really cool bacteria called Pseudomonas syringae. I think I'm butchering the Latin, I'm sure, but apparently they now use this to help make snow for skiing resorts and things like this. So go to Sil's video if you want to learn more about it, but it's really cool to think that there's all of these links between biology and clouds and climate. So I think that's my favorite cloud process.
Thank you very much. Viewers, it is time for you to fill the chat with praise for Andrew and Jonah for answering all those questions on the spot, for Andrew for making it down in the basement. I could stomp above his head right now. And I want to, while you're getting so much praise in the chat, you two, I want to ask you in 1 minute only to tell me what you're most excited about in the upcoming stream hours. So Jonah, you're first. I'm going to be obnoxious about the 1 minute thing to make sure we get started with our first speaker on time. So in 1 minute, I will cut you off. What are you very much looking forward to about the stream? Go.
Okay. Well, I think, I'll look at the schedule here. One of my favorite talks is, we're gonna have a talk at 5 o'clock from Jen K, who's gonna be talking a little bit about NCAR. So you can learn some more about just why it's so important to us. So just stay tuned, it's coming up really soon. But tonight, Nadir Jeevanjee will be talking about one of my heroes, Suki Manabe. Manabe is a scientist who worked at a government lab here in the US, at GFDL, and helped to make the first accurate forecast of climate change back in the 1960s and 70s. So people have been doing this for a long time. And there's also a great talk coming, so that's tonight. Tomorrow there's a great talk from Bronwyn Konecki about 1,000-year rainstorms in St. Louis. I think Bronwyn's talk is and about tying this into looking at the deep past of the Earth and about how that ties to NCAR. And there's going to be also a lovely talk from Flavio. Oh, okay. There's a lot of great talks coming up, folks. You're in for a treat.
So aggressive, Virginia.
I said I'd be so obnoxious, but I feel so obnoxious. But we have to get started with
we're not. There's so much to look forward to, folks. It's coming.
Thank you for having too much to look forward to that will fit in a minute. Andrew, it is your turn. Will you please tell the lovely viewers who are definitely doing a good job praising both of you? I really appreciate the love in the chat. Will you please tell them what you're looking forward to in 1 minute or less about the live stream starting now?
1 minute or less. Okay. So there are 3 things I'm super excited for. So the first thing is Jeff Masters, who many of you may not have heard of, but Jeff is a legendary hurricane scientist and hurricane hunter. He spoke last year at the live stream about how he flew through a Category 5 tornado and lived to tell the tale. And that video is, and this year at 7 p.m. tonight on Eastern time, he's going to come and tell us more stories about his crazy times as a hurricane hunter. So I'm excited for that edge of your seat stuff. On day 2, if you're an atmospheric scientist, one of the huge names of the field is Jeff Vallis. And Jeff literally wrote the book on on a big aspect of atmospheric science. It's like literally so big, I use it to press tofu. It's huge. And he's going to give a talk 9:20 Eastern tomorrow. And then on day 3, we have Emily Becker, who is an expert on El Nino. And she's going to talk about the upcoming forecasts for what might be a super El Nino. So I'm super excited to see what she has to say there.
Boop.
boopity boop boop.
I didn't
It's a very, we do all our own sound effects here at the live stream.
Yeah.
With our large budget, we got the
Very large budget. We got, yeah.
sounds that we could.
We got hats. I don't know. So.
Oh man. Okay.
And a shirt.
So thank you so much for helping me set the scene for the live stream. Andrew and Jonah, I am going to send you off to press tofu and look at the clouds. And I want to bring up our first speaker, Adam Sobel. Adam is a professor in Columbia's departments of Earth and Environmental Sciences, Applied Physics, and Applied Mathematics. And I think, Adam, you are also at the Lamont Doherty Earth Observatory. And I feel like that's enough for me to say about you, and you should just take it away. Thank you so much for joining us.
Thanks, Virginia. Is the sound working?
Yes.
Okay, great. So it's a great honor and pleasure to give this first talk in this event. I think it's amazing what the organizers are doing, and it's a big honor to be part of it at all, and especially in this privileged time spot. So I'm going to talk about my own career. The organizer said if you could be specific about like how these things affected you. So I decided to sort of use my biography as the linchpin of it, but really it's not about me. I don't think I'm particularly important. I'm sort of like one molecule in this giant enterprise that so many other people and institutions and ideas are part of. So I'm going to use my own experience as a way to look into all of that. So if I can change the slides. Okay, so to be biographical, I have loved science since I was a little kid. My father used to take me to what used to be called the Hayden Planetarium. It's now the Rose Center at the American Museum of Natural History. And it had this analog device that shone little lights on this on a big dome ceiling, and you could see what the stars looked like, and they explained about stars and planets and meteorites and comets and galaxies and all those things. And so just to say, for many of us, it goes back to the beginning. This is some of the first things I can remember. And also the American Museum, a great public science institution funded by city and state and federal, as well as philanthropic funds. Just, shout out to one of many great public science institutions that I'm going to mention in the next few slides. So when I was in high school and college, I kept studying science, especially physics and math, but I wanted to be a musician for a lot of that time. Here's me playing with my goofy high school rock band and CBGBs in the 80s. Turns out I was actually the second member of my family to play CBGBs. I'll mention who the first one was at the end, but that's me on the left. You can't really see. And on the right, I wanted to be a jazz trumpet player. And I won't say anything about the picture on the right, except that if you look up my name and Drink Me and you make an effort, you can see a video of me when I was about 24 years old playing music on the internet. Anyway, but through a long circuitous route, which I won't explain, I got out of college, I tried to be a musician, I did a few different things, and eventually I decided to go back to science, and somehow I ended up studying meteorology at MIT. And I was extremely fortunate to be there and to have as an advisor Alan Plum, one of the great scientists of the field, now retired, but still around. And even more fortunate in that I had a fellowship from NASA. It used to be called Fellowship in Global Change. It's more recently called Earth System Science. But this paid my way through graduate school and also gave me a lot of freedom because I wasn't dependent on my advisor's grant as is typical of graduate students. So I had got to, take a little more risk and try a little bit of my own thing. So that was all great luck. And what I worked on at that time, and I haven't really worked on it much since, but I worked on something called the stratospheric polar vortex, which is a belt of very high winds over the pole in the stratosphere in winter. And this is a picture from one of my first papers about it. This is the northern hemisphere, but it's especially important because of in the southern hemisphere, the polar vortex is where the ozone hole happened. And just to give you a sense of all the different ways, a graduate student can learn from people besides an advisor. There was a postdoc in the lab named Darren Waugh, who's been a now successful scientist and professor in the field at Johns Hopkins for many years. And he was kind of my second advisor and taught me a lot. And I used simulations and data from Lorenzo Polvani, who had been a collaborator of my advisor, but he had moved on to Columbia. So although I would end up there later, this was my first contact with that institution. And Lorenzo's been, these people were both mentors for much of my early career. But the reason we were working on the stratospheric polar vortex, as I mentioned, is because of the ozone hole. And the ozone hole was this, and so the science I was doing, which I'm not going to explain the details, but it was related to that and motivated by that. And the ozone hole was discovered in the mid 80s. And then by a couple of years later, in 1987, the first Montreal Protocol was signed, where the countries of the world agreed to stop producing the chlorofluorocarbons that were depleting the ozone, and we're going to increase skin cancer risk for everybody, for the planet. And this was an amazing scientific achievement. Just to give some credit to people, so NASA had flown a bunch of aircraft campaigns with this airplane, a refitted U-2 spy plane called the ER-2 that made measurements of chemicals inside the polar vortex and showed that it was the chlorofluorocarbons that were causing the ozone depletion. And Mario Molina had done the science years earlier with Sherry Rowland that had predicted that this was going to happen. And Molina was one of my professors at MIT. I took classes from him. He was on my committee, and he won a Nobel Prize. He and Rowland and Paul Crutzen won the Nobel Prize while I was there. So that was a pretty amazing thing to see as a graduate student, one of my professors get a Nobel Prize. And so that was the history. But then by the time I graduated in 98 technically, this was kind of a solved problem. I mean, this was a success story. The scientists figured out what was wrong. The policymakers listened to them and solved the problem. The companies, chemical companies all agreed to make new stuff that wasn't new chemicals that weren't as bad for the ozone, and problem solved. So I figured this was time to work on something else, because that's what happens in science. When something is solved, eventually you move on. And so I went to University of Washington as a postdoc, and here again I was really lucky to have a fellowship, this time from NOAA, administered by the University Corporation for Atmospheric Research, UCAR, the entity that runs NCAR, which you've just heard about from the organizers. And so I had this fellowship, and I got to go to University of Washington and kind of work on something different. I had the freedom to do that, and I switched topics because the ozone problem was solved. And there's I'll tell you in the next slide what I was working on and with whom, but this is just a picture of me looking blurry and young. But my host was and mentor was Chris Brotherton, a great scientist at a great department. I didn't manage to put the Washington logo on here, but great department at the University of Washington. Chris was my mentor, and he let me, he gave me some ideas and things to work on, but he also let me explore my own ideas, and we came up with this idea, which ended up getting called the weak temperature gradient approximation. And I won't explain it in detail, but say it's about the tropical circulation. So Andrew mentioned tropical clouds, and it's about how tropical rain is related to the large-scale circulations in which it occurs, how the air moving around is related to where and when it rains and why. And it takes advantage of the fact that the temperature is basically the same almost everywhere in the deep tropics, if you're not too close to the surface at least. But it's fundamentally a mathematical idea about how to formulate the problem of clouds in a little region. So I've drawn clouds in a box here. It's fundamentally a mathematical idea. And the mathematical idea was old, but we came up with a different way to use it in computer models and ask some different questions. And this was, and just as a detour before I say a little bit more about that, Chris later became one of the pioneers of what's the AI revolution in our field that I'm sure you'll hear about over the next 50 hours. But this is now we have models that are not based on physics, but that are based purely on AI. And Chris is one of the people that's made that happen now at the Allen Institute for AI. But back to the idea, the weak temperature gradient approximation became like one of the kind of the big idea of my career, and I with a lot of different people, I've been expanding on it in different ways since then. But just to name one of them, we worked on a thing called the Madden-Julian oscillation, and that's something that people who aren't in the field probably haven't heard of, but it's probably the most important weather and climate phenomena that happens on timescales of sort of weeks to months. So it affects weather over timescales that are like shorter than what we call climate, but longer than the normal weather forecast. And it's named after these two guys, and they were NCAR scientists who first really figured out that the MJO existed. They didn't call it that because they didn't name it after themselves, but that they sort of discovered it. Expanding on this weak temperature gradient idea, I worked on this with a number of colleagues, Eric Maloney at Colorado State, but we were the same generation. We met at Washington, and Dae-Hun Kim and Shugwang Wang, who came as postdocs to our group years ago and then stayed around as research scientists, and now have, our faculty members in Korea and China respectively. But we have did a bunch of work on this. And when I started working on this problem years ago, we used to say we don't understand what the MJO is, but I think we don't say that anymore. We kind of do understand it, and I think our work's been a part of that. So that was one thing that came out of the weak temperature gradient approximation. A little more about the idea itself. It was inspired by another idea that I'd learned as a graduate student that was beat into my head at MIT, which is called quasi-geostrophic theory, which is a complicated bunch of words. But quasi-geostrophy was really developed by a guy named Jules Charney, one of the great sort of founding fathers of modern atmospheric science, and he's on the right, in the far right in this picture. And it's a mathematical idea. So I'm showing two equations here. One is the weak temperature gradient equation, and the other is so-called geostrophic balance. And in both cases, it's like you have an equation that tells you how the atmosphere moves in some way, and you know what the two main terms are, and you cross off the other ones, and then think about what that tells you, and then you slowly add them back in, and you sort of make systematic approximations. And so weak temperature gradient came out of trying to think like, knowing Charney's example and trying to think like him. And that example, although it's a theoretical example, it goes back to the very beginnings of weather prediction. So the first computer weather predictions were done in Princeton, the Institute for Advanced Study, on one of the first digital computers called ENIAC, organized by John von Neumann, who was involved in the Manhattan Project and a bunch of other things. He's second from left here. And really, QG was designed in part as a way to make it possible to solve the equations faster, so that these first forecasts on these incredibly crude computers by today's standards could get done faster than the weather itself happened. So now, the weather forecasts don't use this approximation anymore, but back then it did. So it's just to show the close connection between theory and applied work and forecasting in this field. And we were kind of trying to learn from that tradition. A little more detour before I go back to say something about weak temperature gradient stuff. So a little more history, the Princeton project that I was just describing led to the creation years later of the Geophysical Fluid Dynamics Laboratory, the NOAA lab that's just been mentioned, where Suki Manabe, who's been mentioned also, pioneered some of the first climate models, for which he also got a Nobel Prize. And here is one of the graphs from one of his first really important papers that got him the Nobel Prize, and also a title from a recent paper that Nadir, Jeevanjee, and Isaac Held and Ramaswamy wrote to sort of explain Manabe's achievement and why he deserved the Nobel Prize. And just to say that, as I think was mentioned, Nadir's going to give a talk about this at 8:20 tonight, so you can learn more about that. But I started hanging out at GFDL when I came to Columbia in 2000, Y2K, I moved here. And as a new assistant professor, I was a groupie at GFDL. So I went down there, I took the train down to Princeton pretty often to hang out with Isaac Held, one of the great scientists of our field, who had actually been Manabe's student before that and then stayed. I just think that, the sort of the mentorships in this field are interesting. And Isaac, for those who don't know him, one of the great ways to learn about him is this blog that he kept for many years, which is still up, although he's stopped writing new things on it. And I gave that, where he sort of explains many different issues in our field at a level that's, I don't want to say it's easy, but it's a little simpler than maybe a full research article would be. Very, very clear and articulate. Anyway, one of the things I was thinking about with Isaac was El Nino, or ENSO as we call it, the El Nino Southern Oscillation Phenomenon, and how the patterns of sea surface temperature that happen, that vary with ENSO, and these typical El Nino and La Nina sea surface temperature patterns are shown on the left, how those affect the temperature of the atmosphere, which has to have a much more uniform temperature. And we sort of thought about what that means and wrote this little paper here. And I'm listing the funders. I'll try to put the logos of the funders where I didn't forget to do that. And around the same time, another paper on the same topic, I got to work with a grad student at named John Chang, who was just finishing when I arrived. And we were thinking similarly about how the teleconnections affect the weather in other places. So how, when there's an El Nino event, there's these typical relationships of what happens in different parts of especially the tropics, but the world generally. And we were thinking about how that happens, and especially how the Atlantic and Pacific Oceans how the Atlantic and Indian Oceans respond, and why they respond the way they do when there's an El Nino in the Pacific. And we were using some of the same ideas as in the previous paper. And to bring in another tradition, another set of connections here. So John's advisors were Mark Kane and Steve Zebiak, who at Columbia, at first at MIT and then at Columbia, had developed the first predictions of El Nino, which became the first seasonal forecast. So now you can go online and see from the Weather Service and NOAA how there's predictions not just of the weather a few days in advance, but of how next winter or next spring or whatever is going to be a little warmer or a little drier or a little cooler or wetter than average. Here's a current map of the temperature outlook for the US for this summer. And this is based on Kane and Zebiak's achievement predicting El Nino. And so John had learned all about this, and I was learning about it from them at the same time. And so we wrote this little paper. And just to take it up to the present and how our work, I think, has had some small impact on this much greater, body of work. There's now the way that El Nino and La Nina events are defined by NOAA and others has just changed. So instead of using the sea surface temperature in different little boxes of the Pacific, now it's the relative sea surface temperature. So how a little patch of the Pacific differs from the rest of the tropical oceans around it. This is called relative, SST instead of SST, or relative Nino index. And this has been implemented based after a lot of work by Michel Leroux, a NOAA scientist, Michael Tippett, my colleague at Columbia, and a whole bunch of other people. But I think, and it leads to better classifications of El Nino, little bit better forecasts, a little bit clearer connection to impacts. And this, I think, although many people contributed to this, I think it's fair to say, tracing through the literature, that our studies that I just described to you were part of the foundations for this, thinking about this change. Okay, so after all that, at the same time when I got to Columbia, I started working around hurricanes. And in particular, I was working with another colleague, Susana Camargo, who was a plasma physicist who had just changed fields. So plasma physics, totally different field, but she moved from Brazil to the United States and became a climate scientist. And we started working on hurricanes and climate. And she worked at this institute called the IRI, which I was part of as well. And this is our first paper on the left. We wrote a whole bunch of other ones. And then in 2012, New York City got hit by Hurricane Sandy. And this was a big life-changing event for me in ways that most of which I won't talk about, but I did a lot of media and taught a class about it and gave public talks and did a lot of other things, ended up writing a book. It was just a very moving experience to be sitting here in the city I'd grown up with and experience this catastrophic event in real time. But one of the things that came out of it was we started talking to the insurance industry. So it led me to think about the ways our science is really used in the world. And we started talking to the insurance industry, and then Susanna and Mike and I hired this amazing young postdoc, Jiaying Li, and with our little advice from us, she developed what we call a statistical dynamical downscaling model, or a hazard model. That's the kind of, it's based around the kind of thing that's done in the insurance industry to price risk, where you don't have enough examples of really damaging hurricanes to estimate the risk. So you make artificial ones to sort of extend history. And we built one of those that's sensitive to climate change with funding from ONR, the Office of Naval Research, which is federal, NYSERDA, which is New York State, Swiss Re, which is private sector. We built this model and developed it. And now this model is being used by a bunch of companies in the insurance industry, plus the World Bank and a lot of academic colleagues. And also, I should say, a lot of our students and postdocs have gone to work in the private sector because they've sort of learned about it in part through our groups, the connections we've developed. But so we've done some projects that have been sponsored by the insurance industry. On the left is a plot that I won't explain in detail, but it's about how hurricane risk changes, projecting how hurricane risk is changing in the future. And this is sponsored by a company called Aon that we've been working closely with and still do. And Swiss Re is another company that also sponsored our research. And here's an article that got written in Fortune magazine about us, and that's Xiaoying and me looking serious, but just to show that we really are doing this. We really have got a good partnership with companies in this industry. And so, having said all that, I want to summarize, and then I'll give a couple of last slides. But I want to summarize some of the threads that I think have come up, in my career that I've tried to describe. So the first is, I've just been incredibly fortunate to work with many great thinkers. Some who have mentored me, the people that taught me everything I know and supported me as I learned and worked with me, and vice versa, the younger people that I've tried to pay it forward with. And, I've learned from them as much as they from me. And the ones that I've named here are only a small subset. I just can't put everybody on the slides, but there's many more where those came from. It's been a joy and a privilege. I mean, I think you see that from the organizers in the live stream already. We're really fortunate to do this work, but joy is a necessary ingredient. I mean, science is not just hard work, it's a creative activity, it takes inspiration. And if scientists are miserable, they can't do their best work. And so that's just a fact. I think it's fair to say that in some small way, the work that I've been a part of has contributed to better forecasts on various timescales, risk assessments that are used in the insurance industry and elsewhere, and just understanding of weather and climate, especially including extreme events. That's been my focus for the last 15 years or so. But not only that, also, larger scale climate variability and change and weather. I've tried to outline how I've been a small part of much larger intellectual currents that have led to much bigger achievements that aren't due to me, but I think they came out of this same ecosystem, and we can expect more like it in the future. So numerical weather prediction. I mean, we now have weather forecasts done on powerful computers using the equations of physics that are pretty much right most of the time if you don't go too many days out into the future. Seasonal climate forecasts came later, that we now can predict whole seasons. The Montreal Protocol, where good policy that's saving lives and promoting the well-being of people all over the planet, because we recognized that we were putting bad stuff in the atmosphere and it was hurting everybody, and we just stopped doing it. And Nobel Prizes, I named 2, Molina's and Manabe's. Of course, there's also one for Susan Solomon and the whole IPCC team that I didn't mention, but that's at least 3 Nobel Prizes in my lifetime for our field. All this work benefits the private sector as well as the public. So I've said that, but it's not just insurance. It's also, there's a whole private weather forecasting industry and many other areas of the economy where our work is used. And I hope you'll hear about some of that in the next 50 hours. It's almost all been government funded. I mean, our group has been fortunate to have some private sector funding also, but the work that we've done even there would never have happened, would have never been possible without the work we'd done earlier that was all government funded. And I've named some of my sponsors, I've put others on the screen. It came in many different ways and forms at different phases of my career, but it was all awarded by peer review, meaning other scientists who judged proposals that I and others wrote, with little or no political control. I mean, of course, politics ultimately controls the whole system, but nobody was looking over the shoulders of the peer reviewers and the program managers. That's the system that has made US science great. A generous funding from the government, allocated by peer review by other scientists, not politics. That's how we got where we are. The country is a leader in science and technology. And by the way, almost everyone mentioned in this talk is an immigrant to the United States. Very few people, I'm an exception, I was born here, but most of the people I showed on the screen are not. Most of them came at some other point in their life. And this is another great thing about the US system. We Americans are not necessarily smarter than everybody else, but we have a good system. Generous government funding, awarded, relatively meritocratic despite whatever flaws it may have, and that draws smart people from all over the world that contribute their ideas and their hard work, and it lead to all these achievements that I've been talking about. Now, the last slide, as I mentioned in the beginning, I was drawn to art, especially music, as well as science, and I had role models for both in my family. So I've had this slightly crazy side project over the last couple of years where I've been writing and researching and interviewing people about my late uncle, the artist Sumner Crane, who still has a small cult following. He was in a band called Mars in the late 70s that was part of No Wave, kind of an experimental noise rock movement. He was also a painter. I've got one of his paintings in the background here, and these are also some here. He did abstract and realistic ones, and he was really a starving artist. I mean, he believed in his art. That's all he did, and he made no money at it, and was literally kind of hungry some of the time. And I thought about, he's just one case, but in some level, he has something in common with a lot of other artists. It's not really a good way to make a living. So I thought about both. Both are creative activities, but I ended up in science because science has jobs, like actual jobs that you can get through some sort of normal channel. Not that it's easy, it's still competitive and hard, but they exist. And those jobs exist because the government supports the research through the post-World War II social contract, where the government funds science, in the way that I've been talking about. And, so that helped me make the decision. 2 creative activities, but one you can get a job and one you can't. And I don't think, this is my last slide, but I don't think we want science to become like art. I mean, I think art is tremendously great and important to human life, but it's subject to, you can be an artist if some rich person supports you, or if you happen to fit some trend in culture or politics and you can get a lot of followers, or you're willing to starve to do it like my uncle. But science isn't like that, because the public, the government has believed it's important, the public has supported it, and the taxpayer has supported it. And that's why the US is a leader in science and technology. So I think we want to keep that. And in the next 50 hours, you'll see all the richness of weather and climate science that this system has produced. And we hope you'll call your representatives to stand up for science. The last thing I want to say, because I don't think they're going to take too much credit themselves, is just to credit the organizers of what you're going to see in the next 50 hours. Brilliant young scientists, totally volunteer basis on which they're doing this, volunteering their time. Here are their names here, just to give a lot of credit to them and thank them for doing this. And thank you for paying attention. And I'm looking forward to watching the rest of the next 50 hours. Thanks for your time.
Thank you so much, Adam. And I appreciate the shout out. And I just want to turn it right back to you, because we are only able to make this work because we provide a framework into which folks like you can come and give your time. So appreciation all around. Thanks to everyone in the chat who's also still engaging with us. We have some great questions for you. Adam, I want to start out by asking you, do you still play music, specifically the trumpet? This is from Infinity Chaser.
That's an easy one. No, not for many years. I'm a fan now.
Are you sad? Should I feel sad?
No, it's like I said, they're both creative activities. And when I went back to science, I was like, well, I got to be all in on this, and I can't do both. And I don't know, I've never really felt sad about it. I like to do karaoke. That's about as far as it goes.
You can always do karaoke imitating a trumpet.
Really blew everyone away.
Okay, great. So shifting gears into a high-level question. This one is from WhatDog75. What sort of large achievement do you think we might be on the forefront of right now?
Wow, that's interesting. Well, I guess just to answer a slightly different question, and then I'll see if I can take it forward to answer the one that was actually asked. The thing that's happened in the last few years that's been astonishing has been the AI revolution that I mentioned only briefly in the context of Brotherton, because just to say a little bit more about what's happened there, I mean, this great tradition that led to weather forecasting and then climate forecasting has all been based on models that are built on physics. So we know the equations of motion that describe how the atmosphere and the ocean work, and we solve those equations on computers with whatever approximations we have to make. And as the computers get more powerful and as the models get better, because lots of brilliant scientists work on them, at NCAR, at NOAA, at NASA, and other places around the world, and as the observations that feed into them get better, those forecasts have gotten better and better. But the AI models didn't exist until a few years ago, and they work totally differently. Some of them don't know about anything about physics at all. All they are doing is data science. So just like Facebook, can recognize your face because it's seen a lot of faces and the machine learning algorithms have been trained. There's AI models that have just been shown a lot of weather, and now they can predict the weather without knowing physics. And that's astonishing. That happened in just a few years, and I would not have believed it could happen that quickly until it did. Those models still aren't good at doing climate change. We still need physics for that, but there's a lot of people working hard on that. So if I had to guess, just extrapolating, I think there's a lot of possible breakthroughs that can happen, and if I could predict them, I would be trying to do them. It's hard to predict future breakthroughs, but I think we're going to see more the dramatic sort of like exponential advances that have come from AI in the last few years. I think it's reasonable to extrapolate forward that we're going to see more breakthroughs from that. And I have some ideas about some of those, but I think there's going to be much more that I can think of.
So I actually wanted to ask you about the AI part, because many people have strong feelings about the AI that is marketed to us in everyday life, how do you talk about the AI that goes into weather and climate work, and how similar or not it is to the AI that people might be accustomed to interacting with in advertisements or in apps or programs that they use on their computer?
Well, I think the ones that people are interacting with in normal life are mostly large language models, so your ChatGPT or Claude, or what, you're talking to a chat bot of whatever level of intelligence it has, and that those are based on machine learning, and the weather models are also based on machine learning, but it's a completely different application. I should say that my take on AI is like, it's generally not good at actually predicting things in the real world. I mean, the large language models are based on predicting what thinks the next words should be, but actually predicting like outcomes in the real world is not a strength of AI. But because what's really happening is often different than the training data. But weather, not so much climate, but weather seems to be one of the cases where it really does work, because there's a huge training database, and current weather is similar enough to previous weather despite climate change that the models still work. So I don't know. It's all machine learning under the hood, but it's a very different application from large language models. And I think, people can have sort of political debates about the social and political implications of AI, but I think that's mostly coming from the large language models. And I think the application to weather prediction is relatively innocent, in my view.
I appreciate you clarifying that, because it is hard sometimes to make the difference between the different use cases. So thank you for going there with me. Okay, this next question, I really want to ask it. I want you viewers to know that I am not by background a climate scientist. I am a marine ecologist. And so, Adam, I'm going to ask you this question, and I'm going to ask you to first simplify it for those of us. There are some in the stream who are not scientists by trade. I'm going to ask you to simplify this question, and then please answer it in a way that hopefully all of us can understand. So your question from Michael Diamond is, are there different versions of RONI corresponding to different regions, like Eastern versus Western Pacific? Or does NOAA still use the traditional Nino 3, 4, 1+2, etc.?
Wow. I feel like there could be better.
I feel a little relieved.
So I'll do my best.
Michael, you're really doing it.
Save that one for Emily Becker when she's on, because she will be able to nail that one perfectly. But I think basically, to step back from ONI and RONI, which is ONI is Oceanic Nino Index, but to step back from that, the typical ENSO, the simplest ENSO index that has been in wide use is the so-called Nino 3.4, which is just the sea surface temperature averaged over a little box in the sort of central eastern Pacific, subtract minus the average of that over the last 30 years. So, how different is Nino 3.4, is the sea surface temperature in that little box from what it's been over the last 30 years. And what the relative Nino index, the relative Nino 3.4 is, instead of subtracting just the average over the last 30 years, you subtract the sea surface temperature in the whole tropical oceans around it. So in that way, you sort of take out some of the global warming, because Nino 3.4 is going to go up a little bit just over time, just because of climate warming, but that's sort of not really telling you about El Nino. So you want to take out the global warming, and there's also other reasons to do it, and this is where the weak temperature gradient stuff comes in. You want to take out the relative Nino index, which is subtracting the average warmth. It's sort of how much warmer is that little patch than the rest of the tropical oceans. It's what it's asking. Instead of comparing it just to itself in the past, you're comparing it to the ocean around it, and that gives you a better measure of how the atmosphere is going to respond, the clouds and the winds and everything. So that's the difference between Nino 3.4 and relative Nino 3.4. I think ONI, gosh, I don't even remember exactly what. There's different Nino indices, and some of them involve the atmosphere, and some of them, are multivariate. And so you put in the relative thing, in combination with other predictors in different ways. But the basic difference here in that example is between sea surface temperature and relative sea surface temperature. So it's just whether you're subtracting the average. It's a very simple thing, but there's sort of a deep thought process behind it that many people have contributed to, and it has important, pragmatic value in terms of how we analyze and predict these major, globally important events.
Thank you for digging in so deep. We've got a comment from Michael who asked the original question. I've taught or tried to teach ENSO in the ENSO forecast and Climate 101 classes before. I was excited to have something clearer to use in the future. So I appreciate you putting that on this recording, which Michael can come back and reference again. We've got a couple more minutes. I want to ask you at least one more question. This one is from Arcturus729. They've heard a lot of claims about the impact of generative AI and LLMs on the climate. Do you have any comment there? And they mentioned there's big socio-cultural impact in addition to climate. But let's start with that first question. Do you have any comment on the climate impacts of the LLMs?
Yeah, I mean, so the LLMs use a lot of electricity, and there's big data centers being built everywhere to do it. And so, that's a strain on the energy system, and to the extent that that electricity comes from fossil fuels, which certainly a lot of it does at this time, excuse me, that is a big climate impact. So that is a major downside of, the AI revolution. It's a big, it just burns a lot of energy, and it's also a strain on the grid. So, this is a legitimate concern, and I think we have to, the problem would be solved if we had a cleaner energy system, a cleaner and better structured energy system. It wouldn't be a problem. But given the one that we do, it's a legitimate harm and risk of AI. I mean, I don't know what else that's the truth. I don't have numbers, but maybe somebody will provide those during the course of the live stream.
Again, I appreciate you engaging with the AI stuff. I love that part of what we can do here is provide a bridge between anybody who hops on the stream and you and your personal experience and your perspectives. And so you're right that we could look up numbers and put them into this video, but it's great to hear from you because that's the beauty of what's happening right now. Thank you so much for joining us. We are nearly at the top of the hour, so I just want to pause there and say, Adam, it's been great to have you. If you want a last word, now is your time. Otherwise, please enjoy your snack of eating the rain and popcorn potentially.
No, thanks for having me. And just the thing I forgot to say, if anybody is interested in some of the people I mentioned, I did interviews with some of them, and you can find them on our podcast. That's there. It's deepconvection.org. And I've written about a lot of this stuff, and also about my crazy uncle on Substack, and also about science and politics. So I've given the links there. But thanks to you guys for doing this and for having me on. And I'm excited to watch the rest of the 50 hours.
All right. Thank you, Adam. I want to check back in with the chat because we have got our first person who came a bit after the beginning who said this was their first year watching. Most of you are coming back for your second year. Let's see. It's Chelsea Shermantine 8153. I'm just going to go with these names as they come up. Thank you so much for joining us for your first time. It's so nice to have you. And then Arcturus729 asked what Andrew knocked over when Andrew was running from right here next to me to down in the basement, because Andrew, who was on in the beginning, and I are in the same place, which is such a treat. Andrew slammed, I believe, the door at the top of the stairs, which is why I was freaking out that he was going to tumble down the stairs and we would have our first on live stream accident, but we did not. So that was the slam you heard, was the door slamming. Okay, and I also wanted to call out, there was a landscape architect somewhere in the beginning, and most of y'all who were on here in the beginning were scientists. And I just, again, thank you for joining us. For even if science is not your thing, we aim to make this a fun celebration of what science does and who scientists are. So thank you so much for joining us from all over with all of your snacks and, with all of your backgrounds. So we are just about to bring in our next speaker. I do want to pause and remind you that the point of this live stream is to get you to contact your representatives. I know that we are bringing speakers at you really fast, and so you may not want to leave the live stream to do that right now. that's totally fine. We have information on our website about to help you call and make that easy. So you can use our suggested background information and script so that you know exactly what to say. And you know that when you do call your representative, it will be an effective message or a chat that you're going to have with whoever it is that answers the phone. Especially because we are, oh my gosh, look at that, hour 2 already. We are hearing breaking news that a judge has issued a ruling in the NCAR case, and several of you brought up NCAR. So I just want to say, if you do not know, NCAR is the National Center for Atmospheric Research. It does a lot of work that many different climate scientists rely on to do their work. And one of the discussions that we had at the Weather and Climate Livestream team is, with the judge issuing that ruling, should we not call our representatives? Can we just say, check the box and like, oh, we're good now? And I want to point out 2 things. Number one, a ruling is not, I think this ruling in particular is not necessarily the end of the line for that particular case. So please do keep calling your representatives. Please mention NCAR if it's important to you. Again, I know lots of you in the chat were talking about NCAR without us even bringing it up. So if it's important to you, please do still call. Please do bring it up as something that is personally important to you. And then number 2, you are calling your representative in Congress, you're calling your member of Congress to tell them what you think that they should be doing. And so when a judge issues a ruling, we still don't have action on that ruling from members of Congress. So your voice saying, Congress, I want you to know, is still a unique contribution that can help secure the future of science in this country. And in this case, what I'm talking about, particularly this national center that so many climate scientists rely on. So please do use our help to make a great call and an effective call whenever you decide you're done listening to the live stream. It will only take you 3 minutes last time for me when I did it. At this time, I would like to bring up our next speaker. I am so excited to have Jen K. Oh, I think maybe talking about NCAR, so this is perfect timing. Jen is a professor at the University of Colorado Boulder. If you were mentioning NCAR in the chat, I guess even if you weren't, please stick around because Jen, pardon me, I'm gonna let you take it away and see what you have to say for us. Thank you so much for joining us.
Yeah, thank you so much to the organizers. Virginia, can everyone see? Are we good? Can you see okay? Yep, okay, great. So yeah, I was talking with the organizers about what to speak to you all about, and we settled on NCAR, and I realized that this is an acronym that many people don't know. So the title of this talk is just, what is NCAR? Simple. But it turns out it's not such a simple story, and there's a lot of history in it and a lot of accomplishment that's benefited you, the public, in understanding the atmosphere and reducing risk and really keeping you safe. And so I want to tell you about that. So the National Center for Atmospheric Research is operated by the University Corporation for Atmospheric Research under the sponsorship of the National Science Foundation. So what does all that mean? Well, we've defined NCAR, and NCAR is this national center that's managed by UCAR. Well, what the heck is UCAR? Well, UCAR is a nonprofit. It's a consortium of more than 129 North American colleges and universities who are focused on research and training in earth system science, atmospheric and related sciences. And UCAR, this nonprofit consortium, manages NCAR on behalf of the National Science Foundation. So that sounds a little complicated, and you might wonder how this all started. Why does UCAR manage NCAR? Why doesn't somebody else manage NCAR? Well, UCAR was established in 1959. 14 universities in the US got together, and they said, we need to get together to collaborate on atmospheric and related sciences. And our first action that we want to make as a new collaboration, a new nonprofit, is to establish NCAR. And we're going to establish it as a federally funded research and development center. So in order to do that, you have to have a very specific need, a very specific thing that you're doing. And so they defined the purpose of NCAR. And that purpose was to conduct research on a scope beyond that yet attempted. Pretty lofty. Research facilities to be open to all scientists. And these facilities should be beyond the capacity of an individual university. So big facilities that answer big questions, things not yet attempted. And also to provide a center for collaborative goal definition and to plan programs. At the center of this was, of course, these 14 universities, but also Walter Orr Roberts, who was the first president of UCAR, the first director of NCAR, and came from the University of Colorado. So we have UCAR, we have NCAR. The next thing to do was finding a site to situate this institution. And so they looked to Boulder, Colorado, where the University of Colorado is, and they found there were some lovely sites that required thinking a little bit and actually some political action and motivation from the people who lived in the state of Colorado and the city of Boulder. And in particular, the city of Boulder had a rule that you couldn't build above a certain line, and you couldn't build there because it was the open space. It was an area they didn't want development in. But despite that, the Boulder voters actually approved an exception to the city charter, and the exception was just for NCAR to allow water to the proposed NCAR site. So you're probably thinking, okay, NCAR must be in like a really beautiful spot, you know, up above the mountains a little bit, because this was a place that basically only for science would any building happen. So yeah, so here's the site, the undeveloped site for the Mesa Lab. And the great thing about that was after the city said, okay, we'll allow building, we'll allow water, the state of Colorado used money to purchase the land, state money. And the state then donated this land to the National Science Foundation and to the federal government. So Colorado was making a big investment, a big push to have this national center in the backyard right here in Boulder, Colorado. And it got developed. A very famous architect, I.M. Pei, did the design. And actually, I live pretty close to this building these days. And I would say, aside from the NCAR building, there's very little that's changed in the open space. It's basically still all protected land, except for this one building for science. And now it's been 60 years of science at this facility. And so these are some pictures I took in an early morning in December of the Mesa Lab sunrise. And yeah, this is 60 years since the dedication and since scientists started working in the lab in September of 1966. So we have a picture here of Walter Orr Roberts and I.M. Pei, the architect, at the commissioning. So NCAR had some lofty goals. How did this all go? I would say it went really well. I would say NCAR has really benefited every person in every state in the US. It's really been critical for atmospheric and related research and teaching. It enables shared access, so access for all, to state-of-the-art infrastructure, so these really big resources, large computers, community models, observations, and things that are well beyond the capacity of really most individual entities and certainly any individual university. So it's very efficient and it enables innovation by many, many people. And the topic here, weather and climate forecast, because NCAR does both, weather and climate, is really a huge value to the nation. It's a $31 billion annual value. That's what the estimate is. The National Science Foundation these days funds NCAR about 123 million, so a small fraction of that 31 billion. And actually, NSF only funds about 50% of NCAR's budget. The other 50% comes from foundations, from other federal agencies, from states. So, I mean, a question I have for the live stream is it in our national interest to invest more in this NCAR infrastructure? It's super efficient. It enables so many people to do great science. You know, maybe we should just be putting more money into this. Some of the things that NCAR has done that you as a citizen in the public, any person in our nation feels, making air travel safer. So that includes forecasts for turbulence and microbursts, which can take down planes. Really understanding extreme events like fires and heat waves and snowstorms and floods and droughts. So all of these things cross that weather-climate interface. And I really, you know, personally don't like to make some strong claims that weather and climate are different. For something like a heat wave, that's basically a meld of the two of those when you go to something more extreme. And NCAR doesn't just stick to kind of surface climate and surface effects. They produce space weather forecasts for power grid and satellites. So there's a high altitude observatory. There's a lot of different parts of NCAR. NCAR really does it all, a full range of atmospheric and earth sciences. And it really puts us in first place. It keeps us safe, and it keeps us safe in an environment in which we are increasingly reliant on things like, you know, space weather not going wrong, or knowing that there's going to be a hurricane or a heat wave and preparing adequately for that. So NCAR has some strategic planning that they've done to try to figure out, you know, where they're going to be. It's 60 years. They're not using the same playbook as Walter or Roberts today, but I would say the same general structure that was outlined at its foundation, at its beginning, is still working really, really well. Back to these microbursts. So yeah, this used to be a real problem when you would fly. So if you went into a severe thunderstorm, you could basically have a plane crash like the Delta Airlines Flight 191. These are small features. They're concentrated downbursts of violent wind, and they typically impact an area that's pretty small. And so you need some ways to detect that. And NCAR researchers really were at the forefront of developing that. And this was highlighted in a really nice article by Marshall Shepard, just talking about the different ways that NCAR helps you. NCAR does weather and climate together. So while in the news you may hear that NCAR is a climate institute, I think, again, separating these is super artificial. And this is just showing the water vapor on a given hour and day in March. And one of the things that you'll notice from this is that there's more water vapor in the tropics than there is at the higher latitudes. And that's because the water vapor depends on the temperature. This is just the basic physics. And weather models, climate models, any numerical model of the Earth system will know about this basic physics and need to take it into account. And I know we were talking about the AI revolution, but you know, the AI is learning this too. The AI knows about temperature. So I think there's some ways that we need to think about what processes dominate on what timescales and things like that. But I think it's much better to think of this as a continuum than a this versus that when we're thinking about weather and climate. NCAR is also really famous for its community modeling. And so modeling, for those who don't do it regularly, this is just basically taking a bunch of equations, putting them on some sort of discretized grid and solving them so you know in space and time what the answer is to the equations you're trying to solve. And whether or not you're using physics or AI, you know, those could be statistical equations or physics-based equations. It's, you know, the same general concept. And so you want to solve these equations fast. You want to make some of the approximations that Adam was talking about if you don't have a lot of computer power. But once you know what the equations are that you're solving, you can use those to test hypotheses, to really understand the relative importance of different processes. and to make forecasts, which, we see all of the time on our iPhones or our computers or wherever we're looking at the weather forecast. All of that is done through a computer model of this kind. So NCAR has made really efficient and effective ways for long-term investment by many scientists. By being a community model, many people contribute to it. So it's not one person's intellectual property. And a lot of people like to credit Manabe, with founding climate science and a lot of the forecasts, and that's great. There were a lot of other people involved at that time, but certainly a leader of that time. But at this point in time, we're like 5-6 decades later, the number of people who've contributed to some of these models it's hard to identify a single person. It's like an entity all of itself. And that's really cool. And something that a national center can do, can keep the code, can keep the ideas, can test what works, test what doesn't work, and make it useful for the long term. Observations and models together. This is another thing that NCAR does really well, and that is actually just a really hard thing to do. And maybe I'll just explain for those who aren't thinking about this, in particular in atmosphere and ocean and other related sciences. So I'll give an example for the atmosphere. NCAR has some planes. Those planes are well equipped, for example, to measure cloud particles in the atmosphere, precipitation particles. So you can go fly around and make some really detailed measurements of clouds. But just a reminder, the models that you're writing, these are all equations, and they don't know how to take the information from the planes you flew around in the atmosphere and turn it into something that you can write down and solve on a supercomputer. So this is where the ILO science really comes in. You really have to think about how to combine these different sources of information to make the most of this. It's hard and it's fun. And the atmosphere has a lot of variability, a lot of processes on a lot of different scales. This is just a real-time US composite satellite for the last 7 days. And you can see, convection, these large-scale waves. There's so much detail here. And it doesn't matter if you're in, for example, the state of Oklahoma or the state of Illinois. Both states are going to be affected by the same system. And so it doesn't really make sense for any individual state or any individual country in that way to make their own model. It's really nice to be able to share this information broadly because the information that you have in one place will propagate to another. NCAR also just supports so many scientists, training and education for Earth system sciences, from early career through faculty, through the public. This is really something that was at the ground level when NCAR was built and has continued as it's been around. And through that, NCAR brings together so many scientists through meetings, more virtual meetings, this kind of Zoom, all the different faces we're all used to at this point in time, but also the in-person meetings, which I think can be super important for sometimes identifying big elephants in the room that you don't see in a virtual meeting, or that you think you understand what someone's saying, but then you see them eye to eye and something kind of clicks in a different way. So I think both are really valuable and needed for 21st century science. Okay, so that was kind of a broad view of NCAR and some of the science that it does, the value that it provides, not just to individual scientists, but to the whole country, and just the ethos of it, which is that it's very community-oriented, it's science for all, doing really big things that no individual university or entity can really do. So I thought after doing that, I would talk a little bit about my personal connection to NCAR and just how NCAR has been a part of my career. So I wasn't a weather weenie when I was a kid. I really didn't discover atmospheric science until I was a graduate student at the University of Washington. And my PhD advisor, who's pictured here with the red shirt, Marcia Baker, along with the community there, really introduced me to the wonders of ice and clouds and weather and climate. And that foundation, that scientific foundation, really means a lot to me. along with the support of my family, it really has been one of my passions of my life. One of the things that I've done the most of my time with. During my PhD, I built my own cloud physics model. This was something I just did on my own computer. But I also used the NCAR community models, in particular, one of the weather forecast models called MM5, and the supercomputer at the time. And I did this all just from my desk in graduate school. I actually never went to NCAR in graduate school. I just looked at their web pages and figured things out. And it was also well documented, and it was really easy to do. So yeah, I don't need to go through the details, but like, this is the model I built, this parcel model. And then what I did with the NCAR models was kind of run these trajectories so that I could see how the air was moving over most of the Western US. And I had some observations in Oklahoma. So I was particularly interested in kind of high resolution over Oklahoma. But the point was I used the NCAR models, and I didn't need like a really high level of sophistication. It was really well documented and really well explained. After I finished my PhD, I actually moved to Boulder, Colorado. I did a postdoc at NCAR, joint with Colorado State University, just up the road. And that time was especially formative for my early career. My sphere really expanded at that time, beyond just kind of my desk in graduate school and my friends in graduate school, to include scientists from around the world as mentors, as collaborators, as friends. And I keep in touch with many of those people today. One of the things that I did at NCAR was one of these really big projects that Walter Orr Roberts kind of dreamed of NCAR doing. I co-led the CESM-1 Large Ensemble project to study climate change and variability. And just as Walter Orr Roberts and kind of the folks who founded NCAR had wanted, we had a planning meeting with a number of people from the university community and from NCAR to make the experimental design for this large project. And then we ran the simulations on one of the largest supercomputers on the planet. It took over a year to run them all. And we had our final experimental design, this time with the real data instead of just what we were writing with a Sharpie. And this project has really been a foundation for research and economic decisions ever since. I mean, it's kind of a decade old now, so it's kind of maybe on its downturn, but it's been cited a lot. The data are used by actuaries to figure out pricing on home insurance. They're used by private companies. It was requested that it be put on the Amazon cloud to be used in some of the newer formats for cloud computing. So it's been a super impactful project, and I think very much in the spirit of what NCAR was designed to do, involving the university community, involving NCAR, and doing something that was way too big for a university to do alone. I've also hosted workshops and students at NCAR. One of the meetings was the CFMIT meeting, which is a cloud feedback meeting, 130 participants at the NCAR Mesa Lab in 2018. Due to COVID, we had to pivot and not have a meeting in person during 2020. And NCAR just jumped at that and was willing to host us for one of the first large virtual meetings in September 2020. We had all these different time zones figured out. And I mean, it worked relatively well despite a complicated time. I had students come visit me, and that was actually really one of the things that inspired me to become a professor. So Ben Hillman visited me through NCAR's graduate research program, and he's now working at Sandia National Lab, so for the Department of Energy. Finished his PhD. I was on his committee after that. And now I'm a professor at the University of Colorado. I've been there since 2014, and I've been really fortunate to work with many talented and caring scientists, students, and educators. We still make good use of NCAR's resources. They're way more than any university can provide on its own. And so it really enables, an entire research group at a university to do really cool science. Okay, so I'm wrapping up here. I wanted to just say something about this because I think it's kind of unique. I am a 4th generation PhD scientist in the United States. And my great-grandfather, who's pictured here, he was a professor at the University of Iowa and did a lot of work in soil science, kind of establishing the basis for kind of agriculture and soil quality in the state of Iowa. My grandfather did a lot of work in kind of the precursor theory to plate tectonics. And my parents are both geologists. They work a lot on volcanoes and the evolution of the Andes and the Aleutian Islands, things like that. So I've come from a very rich background of science, and it made me think a lot about like kind of the generational aspect of things, like what it means to go back to something like 1960 or even earlier, and just how important it is that an institution like NCAR is still around. And so I'll just close by saying that for generations upon generations, NCAR has really existed and exists to enable research and education in atmospheric and related sciences. And we in the community, we love NCAR because it enables us to do so much. We can't imagine science in the US without it. And so I just want to really thank the organizers for giving me an opportunity to share what an amazing resource it is. So thank you. Oh, Virginia, I can't hear you. One second. Virginia is working on some technical issues. So yeah, I'll just mention here that the person who's in this photo here is actually Sel, who's our walker, who started in New York and is walking towards DC. And this is just a picture of him when we were at the American Geophysical Union meeting. The organizers of the Weather and Climate Livestream got many of us together to make a video about why we love NCAR. And so that's still sitting at our point where we were meeting people who we were gonna interview for the video. Yeah. Oh, great. We can hear you. I think something.
Okay, great. Testing out the sound now. Perfect. My face will come back momentarily. Enjoy the break, viewers, as I am not on screen with Jen. Thank you, Jen, for explaining that that's still in the photo. I thought that person looked familiar. I have been watching a little bit, but you see Sil outside of the giant walk he's doing from New York to DC, and you're just not sure. So I was, when I was talking to myself, thought I was talking to camera. I was reading out the last comment in the chat to you, which is from Sydney Kramer. It says, "You did such an amazing job conveying how Table Mesa is the global home base of climate scientists and so important to all of us." And there are several comments in the chat about the community aspect of your presentation, which I was honestly thinking about a whole bunch of myself as well. So I'm going to ask you, I just want to start, this question is mine because we've got some time, with, what do you do work differently if you know that you're going to be able to do it in community and potentially with enough funding to support a lot of people working together? Does it help you do science differently?
Well, something like the CESM-1 Large Ensemble project is not something that any individual at that time could have done. I mean, it was really a big data project for its generation. And so, yeah, I think you do things differently. You talk to a lot more people because you want to make sure what you're doing is useful for people. So you're saving the right field, enabling all kinds of people to do science. So, yeah, I think Clara Dessler, who's a senior scientist at NCAR, and I was co-leading this project with her. That was really our ambition, and really our vision for that. And, people really stepped up. A lot of people in the community said, hey, I need this daily field. I've never had a daily field of CI610, or I've never had a daily field or a 6-hourly field that I could use to drive a regional model that then I could look at this extreme event with. And so, yeah, you take your time a little bit. Yeah.
Perfect. Thank you. I have a comment in the very bottom of the chat right now from Arcturus729. Thank you. I hadn't heard of NCAR before this, and it was really interesting to learn about. And then I want to skip backwards to a question that Arcturus asked not too long ago. Does NCAR, again on this community theme, does NCAR work with international agencies? What does international collaboration look like in the climate sciences, particularly with the US's current political scene?
Yeah, I mean, NCAR doesn't work with international science agencies because NCAR is largely funded by the US government and by US resources. Increasingly, private foundations are starting to step up a little bit for NCAR. I mentioned that 50% of the funding has come from the National Science Foundation and the other 50% from other sources, and how that's changed the nature actually a little bit of what NCAR does. It can't exist just to serve the university community if it also has to fundraise to do other projects. And so, that's kind of a balance that evolves through time, and everything should evolve through time. No one should want things to just stick in one place. But NCAR is really well known internationally. I mean, it's the envy of the world. It's a center that does it all. I mean, and that's where we need to be really careful with our language, right? When we just say like, oh, it's just a climate center that just does modeling. Like that doesn't do justice to what NCAR really does. It does weather and climate. It does modeling and observations. It does all of that together in one site from days to decades to centuries. Like, no other place in the world really has that concentration of resources, and it makes it kind of a magnet for people to come. Yeah.
Thank you. You mentioned in that last answer, you were talking a little bit about wanting and welcoming change because you should be changing with the times. And Cosmic594 actually asked, what's a big goal for NCAR in the coming decades as the climate is changing?
Yeah, I mean, the strategic plans for NCAR are under development. They do one every 5 years. UCAR, involving all of the universities, does that as well. And so that can help set the stage for things. I think some of the things that we've talked about already on the live stream are relevant here, right? Like, how do you know when the weather has shifted, when you're out of a specific regime, when you can't use the same weather forecast because the climate has changed? Those kinds of questions I think are really interesting ones. And, of course, with the political climate changing, we need to be careful that we don't just think about forecasts on days to weeks to a year. Like, people need to make decisions on much longer timescales. And in particular, if you go buy a house, or if you're building some major infrastructure, you need decisions and information that's relevant on a decadal timescale. So I think just thinking about those questions, it's really important.
So I am seeing, again, multiple people in the chat who are just relating to this so hard. My group, this is from Michael Diamond, my group published a paper using the CESM1 model that you co-led earlier this year. It's an amazing resource for the community. Samantha Kramer says, I attended the NCAR UCAR undergraduate leadership workshop in 2014. It was an amazing opportunity to dive further into research. I would love for you to talk about, it's so interesting because students are students have to go through universities, but they end up doing so much with these kinds of extra institutions. So, and I know that student to researcher and scholar pathways are being affected by, some of the stuff that we're urging people to call about now, some of this legislation. So I'd love to hear your take on, what it's meant to you to support students and how you feel like student support is evolving to prepare students for the current job market.
Well, so I'll give you an example that's quite relevant. So NCAR, of course, has a big supercomputer. Any student at a US university can apply for an allocation on that. Any student. You can be at any university and apply for an allocation on that supercomputer. Like, you don't have access to Microsoft's computers or Google's computers, right? You have access to NCAR's computers if you're at a university. And that's because of this model of a resource for all, right? Now, they don't give you access to the whole machine, but if you write an NSF grant or you collaborate with some of the scientists who are developing the model and you have a good idea for how to evolve the model, you can really quickly find yourself with some pretty big supercompute. And that pathway for students is so important. And private industry and other federal agencies, they just don't have that mandate. They don't have that interest in involving lots of students and lots of people in their science. Some places are much more of a closed door shop. There's the 20, 30 people who develop it. They hire some postdocs who work with them, but they're not really open to the community in the same way. And so I really credit the founders of NCAR for seeing that need, and also just say right back to the people who say, like, we need a more efficient model. Like, I can't think of a more efficient model. We're making this available and upscaling it if you have good ideas. Like, this seems like the way to enable innovation for everyone.
So I have never used a supercomputer or a large-scale model in my own scientific work. I'm gathering that there is a line to use the supercomputer, that space is limited and you have to wait your turn. What is that like? Is there an application process? Are you 50th in line and it's just like customer service where you slowly move up? What is that like?
Well, most computers have like a queuing system, right? And so if you run a short job, like let's say you just want to run a weather forecast for 3 days at like a pretty low resolution, you're fine. You'll get right in the queue. If you want to run something that takes like half of the machine and keeps out, half of the users, then you need to really have a special allocation, and you probably, need to wait more or have some priority that's negotiated. Sometimes you can get early access on new supercomputers. So when they first come online, this large ensemble project that he mentioned, NCAR, had just completed a very large set of simulations in support of some kind of international activities. And so actually the computer was relatively free, which enabled this large ensemble project to kind of go forward. So your timing can also matter.
Okay.
Yeah, you have to get in line.
I was just imagining some really massive Google sheet that's really messy. Everybody trying to inch their name up. Thank you so much. We're pretty much at time, and I really appreciate you. The timing was just perfect for talking about NCAR and then shifting straight into your talk. Thank you so much for being with us, and enjoy the rest of your day.
Thank you so much.
Okay, I see lots of comments in the chat about how y'all would be investing $1 trillion into supercomputing capacity and into NCAR. And if you feel that way, I really want to urge you again to call your representative, to tell them that you want support for NCAR specifically, if you like, for scientific infrastructure that helps weather and climate science and all science, all research in the US work. It is very effective when you add your own personal perspective to the messages that you are giving to your members of Congress. And so even if it feels silly, if you are able to say, I just saw a research talk and it makes me feel like we should be investing $1 trillion into this, you are a constituent, and it is your right to be able to let your representative, your member of Congress know how you think they should take action for our country. So again, if you want to stay and hear more talks, please do. But when you are done, it takes about 3 minutes. There's a link on the bottom of your screen right now. We've done everything we can to make this very easy for you. If you go to that link, it will have some suggested words you can use. It will fill in your representatives information, your members of Congress information, if you put in your zip code. So hopefully it will not take you very long. Hopefully you will go and do it, because the future of science is at stake here. We have a couple minutes before I want to bring on our next speaker. And I know that we were talking about AI in the last talk before Jen's talk. And I wanted to call back to a comment by Mark Alessi in the chat after that one, because I think it's a really cool way to talk about how AI works in climate science, at least for some people. Mark says, recently attended a roundtable on AI, and someone described LLMs as elephants and smaller AI models as bees. Climate scientists usually use bees. We don't need the data centers associated with the elephants to do our science. It's interesting, you know, my job as a science communicator is to talk about the process of science, and talking about the differences, the different ways that AI is employed by different people is a real challenge because people have such strong feelings about it. So Mark, thank you for sharing that metaphor. I really appreciate it. Before we're about to bring on the next speaker, but before I do, I've mentioned a couple times that I am not by background a weather or climate scientist. I am a science communicator now, but my background is in marine ecology. I work with weather and climate scientists now as a communicator to share what they do with you, with people who will use it to make good decisions and to make life better. And I have been supported by federal funding in my training years, and then also in the work that I'm doing right now. I'm on multiple grants from the National Science Foundation. So I just want to highlight that it's not only weather and climate scientists that are supported by, you know, this kind of funding that we're urging you to contact your members of Congress about. It is the entire scientific community is very interrelated, and people who get started one way might move another. And we all work together because we want science to serve all of us. That's what we're trying to do. I do want to bring up our next speaker right now. Zach, please come onto the stage with me. You are, I believe, a climate scientist at Climate Central. And with that, I will let you take it away. Thank you so much for joining us.
All right. Does everything look okay?
Everything looks great, and I can hear you well.
Sounds great. All right. Thanks for having me, and thanks so much to the organizers. Thanks for all the viewers. It's really a great opportunity for us to all discuss the wonderful ways science and communication is influencing our life. So I'm Zach Labe. I'm a climate scientist at Climate Central. A little bit about me is my work. I sort of am at this point in my career where I'm at this bridge where I don't know if I'm still early career anymore, but very much, you know, it's thinking about ways climate change is influencing regional climate variability up into the Arctic, extreme weather, all sorts of things like that. And today I am also going to be talking about sort of the second hat that I often think of wearing, which is the science communicator part of me that I become increasingly passionate about over the years, about how important it is to communicate our science and different strategies we can do so for making that effective. So I'm going to be talking about why we should be thinking about communicating our science. And I think this Weather and Climate live stream is such a unique opportunity to share all the amazing work that's being done to understand our planet. And I'll also start off by saying, you know, I was one of those kind of classic weather weenies. So I, for unknown reasons, like have been fascinated by the weather since elementary school. I was giving weather forecasts in the morning announcements in like middle school. There's a picture of me. I was super excited to like measure a 50-mile-an-hour wind gusts at the top of Mount Washington, up in New Hampshire, home of quote unquote world's worst weather. And there's also a picture of me of one of my like original diaries. So like for me, a diary as a kid consisted of tracking the weather and recording like hourly observations with a little weather station. And I'll just mention, I'm going to mention it multiple times, that without, you know, the support of federally funded research, I would definitely not be a scientist today. And I think it was so exciting to also hear from Jen Kay's talk just a minute ago about, you know, recalling my time in interaction with NCAR where a lot of the work that I've thought about for my own research is how do we distinguish climate change versus what I call the noise. So the signal versus the noise, climate change versus weather. And one of my first research projects back in graduate school was, of course, using the CESM Large Ensemble, which you just heard about, designed to really better understand the signal of climate change versus that noise of interannual variability, internal variability in the climate system. And then my second research project was one of those grad student allocations to use the supercomputer by NCAR. So I think every single person that you'll hear over the next 50 hours can relate to many of those stories about how NCAR is the foundation for so much of our work, even at the very earliest stages of our careers. And so nowadays I still work and think about this research problem, but I become just increasingly passionate about how do we improve the communication of our science. And I want to first state off by saying, I'm a trained physical scientist, climate scientist, and not in communication. And so I'll say that, this is my way of communicating science. It's not necessarily the right way or only way. And the way I've done this is actually allowing data to tell this story, these climate stories. And I thought I'd also start off by grounding our audience. So one of these wonderful collections of data is these surveys by the Yale program on climate change that comes out annually with these surveys trying to get a better assessment of how the public thinks about global warming. And they ask all these wonderful sets of questions to really get insights and track changes in sort of public opinion around global warming related topics. So I'll start out by showing this graphic, which is the estimated percentage of adults who think global warming will harm future generations a moderate amount or greater. So take a look at the map. This is showing county level data where the national average is 68% of adults across the United States. And another thing to note about is the color of those counties. They're all yellow or red for almost all the counties, except for a few spots, meaning that the majority of adults think that global warming could potentially harm generations into the future. Now, compare it to this survey, which is the question is the estimated percentage of adults who discuss global warming with friends and family just occasionally or often. In this case, everything's blue, less than 50%, and the national average is 35%. So we have the far majority of people who are worried about climate change and global warming, but they don't often talk about it. And then another interesting result is what's the estimated percentage of adults who hear about global warming in the media at least once a week? In this case, the national average is only 19%. And again, this is showing a county level view with those dark blues showing that the percentage is very low for the percentage of adults who even hear about climate change at least once a week. And so what I will suggest here is that I think communication, effective science communication, is a solution to climate change. And so all of this is grounded in visuals for me and the way I communicate climate change. And to me, this is one of those classic visualizations that you probably all have seen before, which shows atmospheric carbon dioxide levels for over 800,000 years. So you can see there's ups and downs, periods of interglacial periods, there's ice age periods. So we see increases, decreases naturally in the climate system. But there you can see on the right-hand side, that dramatic spike, that unprecedented rate of change of increasing carbon dioxide that's really connected to human-caused climate change. And all of this amazing data to reconstruct 1 million years worth of data is all put together, very much of it from federally supported data. Scientists from all over the world working together to collect this information and present it for our understanding of our changing planet. And all of this, all of these fancy graphics that I'll be showing today, they all start with just lots of numbers. So, something that scientists need to do, as our day job is take millions and billions and trillions of numbers and make sense of them. And we can't, look at all these numbers and understand what the patterns and the trends are in the data. So we run, computer science techniques to analyze, make graphs, calculate statistics to try to understand this data. And we turn this data into a story. So here's just an example showing output from a climate model of what temperature change might look like going forward into the future to 2100. And so this data visualization is a story of our changing planet, how climate change is influencing changes in temperature, where anywhere in red means that that region is warming over time. Anywhere in blue means it's cooling. So you can see a lot of interesting patterns that tell us all about the climate system. So we can see deep, dark reds over land areas because the land areas are warming much faster than over ocean areas. You can also see at the very top of the world, there's this big blob of red over the Arctic, and that's Arctic amplification, where it's changing the fastest of anywhere else in the world. And so, like I mentioned earlier, one of my research focuses has been the Arctic and trying to understand why is the Arctic changing so fast? What are the implications of this rapid warming, both locally in the Arctic, also sort of far-reaching across other parts of the world? And so oftentimes when we talk about the Arctic warming so fast, we might show something like this, which is a very like stereotypical graph where, you know, you have the x-axis is time. So it's showing the annual temperature change from 1900 on the left to present day on the right-hand side for the Arctic versus global land and global ocean areas. And so this is fine. It tells the story that you can see that this really steep slope of the change in Arctic temperature is happening much quicker than global land and ocean areas. But what if we visualized it in a different way to tell that story? And so instead, I will often show this visualization, which is completely different than that very typical line graph, where now you're looking at changes in Arctic temperature from 1979 on the top. So each little circle is a map. You're looking downward at the North Pole. So at the bottom of each map, that's northern Canada and Greenland. At the top of each map is Siberia and Eurasia. And what it's showing is the changes in temperature by year from 1979, that top left, to 2025, the bottom right. So this is the satellite era where we have really high quality observations of temperature across the Arctic. And so this, to me, tells a really also equally important story where the color of those maps is really sharing the story, where you can see blues and reds at the top, but a lot more red at the bottom, that rapid Arctic warming. But we can also see that not every year is it going to be red, more red and more red. And there's also a lot of regional variability. So some years the hot spot might be over the Siberian side of the Arctic, and other years it might be over Greenland, capturing that natural variability in the climate system. So for me, I'm always constantly thinking about how do we break down like very traditional, stereotypical visualizations of the data and try to think of creative ways to tell that same story while sticking true to the science. And I also just want to point out that, you know, for Arctic amplification, we've known about it for a very long time. We heard about Manabe earlier in Adam's talk in the beginning, and this is one of these, you know, seminal papers from 1980 from one of the first global climate models, which also showed that the Arctic was warming faster than anywhere else in the world. And I also think this is a really interesting view of showing what visualizations have changed over time. And so for me, this idea that we can use data visualization for storytelling, taking different ways of using the same data and visualizing in compelling ways for different audiences to, again, try to effectively communicate the science, both for the importance of the science and also how the science can be used for informed decision-making on topics such as important as climate change. And something I always recommend and try to think about myself is to stop thinking like such a scientist. However, we're all data scientists. So keep in mind that everybody here is data scientists. You're familiar with working with data, running statistics, visualizing it, and how to use these two ways to think about them together for communicating our science. And it doesn't necessarily have to be through like these traditional graphics. It can also be through other forms of media. Here's one of these great examples of taking actual real data. So this is an artist by the name of Jill Pelto, who visualizes climate data through watercolor paints. So this is the cover of an American Meteorological Society magazine from now almost 10 years ago, showing actually changes in data of sea level rise, glacial volume decline, global temperatures and visualizing it in this artistic way. So when I talk about visualizing data in science, it can be in very, very different forms because we're always trying to reach different audiences. And so I want to take you through also sort of my role. What does a typical day, or in this case, almost years, look like as a scientist working on a research problem versus communicating it? So typically, when I'm starting a new research project, we are trying to identify a problem. There's some sort of topic of interest, some sort of hypothesis we're thinking about. And so for me, I'm a climate scientist analyzing and running climate model data. So I work with those supercomputers you just heard about. So this is actually a picture sort of what those supercomputers look like. And so initially, you start finding data. You find real world observations. You might compare that to climate models. You might then also work to identify statistical and data science approaches, and that might take several months. So again, at the very top here of this slide, it's showing actually the time frame it took me to complete one of these research projects. So several months of sort of gathering, processing all of this data. And then, you might evaluate it in different ways. You might start to run experiments. So then it might take half a year to a year to run experiments, run those supercomputers for climate models, or write different types of code to analyze it, or build machine learning models to, again, identify the signal and the noise. So that takes an extended period of time. And so, again, this is encompassing, you might use computer programming languages like Python, evaluating these massive data files. And then eventually you get to the point where you're starting to really refine your analysis. You're starting to create visualizations and graphs that tell the story about your hypothesis and your findings. You might begin starting to write a paper. In this case, this particular project, it took 5-6 months just for this step of this research. And so you'll visualize it in different ways, again, trying to figure out what are the key results for this work. You'll then start to interpret the results and eventually go through a peer review process. And that can take a long period of time. That can take anywhere, if you're really lucky, maybe 3-6 months to sometimes over years to get a paper through the peer review process. So that takes time. And eventually the paper hopefully comes out, and that's sort of the end of that research component of the work. And then there's a whole additional component of how do you communicate your research? What is that plain language summary, going out to conferences and presentations, or talking about it on social media? So as you can see, just for one research project, the whole cycle takes a significant amount of time. So what I've done here is I've taken that amount of time for that particular research project I did, and I started, again, it started maybe summer 2022 and finally wrapped up February 2024. And I've annotated on this graph that's showing temperature departures for the Northern Hemisphere. So each year is representing monthly temperatures from 1940, the blue lines, all the way up through 2024. So as you can see, that sort of gradient of those blue to red lines is indicating that long-term warming trend across all months of the year for the Northern Hemisphere. And what you might notice is that yellow annotated line is really above those other lines, suggesting that during 2023 and 2024 for Northern Hemisphere temperatures, they were really an outlier. And so during that amount of time, they were, and climate scientists were talking about it nonstop, trying to understand what was going on, what are the implications of it. One of the big headlines that came out of this was gobsmackingly bananas, talking about the extreme warmth of September. And so why I mentioned that entire process of my research project, contrasting it with sort of what was going on in the real world, is that for very good reason, the scientific process takes time. It takes time to evaluate our work, go through the peer review process for feedback, working with other scientists. But the rate of change for climate science and climate change is also very quickly. And so this is really, to me, very urgent reason of why we should think about the importance of communicating our work and tracking real-time changes in our climate system in real time. And so I want to encourage everyone to revisit your creative side for thinking about data. And I'll show some examples of creative ways of how we can better track real-time climate information as well. So for global temperature, there are multiple data sets that we use to understand changes in yearly, monthly global temperatures. So if you just took the data from multiple of these data sets and you plotted something default into Python, it might look something like this. So it's just, again, on showing change in annual mean global temperature. But what if we tried to visualize it in a completely different way? So it's taking basically the same data, but it's just changing the story behind how we visualize it. So this is something that probably almost everyone has seen, which is the climate change spiral by Dr. Ed Hawkins, and showing different ways of how we perceive visualizations to understand our changing planet. Where in this case, each year is still showcased by each individual line, but it's growing outward over time as our planet warms. And so to me, this is just an amazing way of, taking the same data, but visualizing in a creative way to reach new audiences. And it was so well received, and it was actually featured in the opening ceremony of the 2016 Summer Rio Olympics. And to me, I would have never believed years ago that a visualization of climate data could be witnessed in such a venue as powerful as an opening ceremony of the Summer Olympics, really showing the power of creatively thinking about communicating all of the data we work with in weather and climate science. And if you're interested in sort of the story behind the climate spiral, I really encourage you to check out this piece called "The Climate Spiral Demonstrates the Power of Sharing Creative Ideas," which is in the Bulletin of the American Meteorological Society, is a short piece, again, talking about the challenges behind communicating climate change and how something creative, like through data visualization, can really be so impactful and far-reaching. I also want to show you that there's an entire literature in scientific community in cognitive psychology that thinks about how can we better understand visualizing data in the power of different interpretations of it. So I want to go through this example, this exercise. So again, we're going to take global temperature data. And for this case, they did a survey where they took 6 maps, all using the same data of changing surface temperature. And all they did was change the color of the visualization for the map. So just change that color scheme. And then they went through and asked people different questions about these maps. And I just want to highlight a few of these questions, again, to show that even though this is the same data and all that was changed is the color of the data, how it can actually influence people's decision and understanding. So in this case, the first question I want to highlight is, how severe would you estimate the global temperature increase with respect to the appeal of colors? So in this case, they picked that map that I've highlighted in the blue box, so the upper left-hand one. So for this one, at least my interpretation is that people most frequently associate the one that was really sort of bright, the higher color contrast, with being one that they would associate with climate change being more severe. Again, this is all using the same data. Now contrast it with this question. So which color scheme appeals to be the most intuitive one for the topic? In this case, they didn't pick that same map. They picked the one below it, which in my at least perspective of it is a little more subtle blues and reds. We can maybe more see some of that regional variability in temperature trends. And then another question that I thought was really interesting was, which map would you choose to affect policymakers to take more action in climate protection? In this case, they picked again that upper left-hand map, the one that was more brighter. And so my takeaway from this study is showing just by changing the color can influence something even as much as decision-making and policy-making, showing the importance of how we think about visualizing and communicating all of the data that we work with. And color is a big part of it. It's not the only part of it, but it's a big part. And one of them is related to sort of accessibility of colors. So there's a whole field thinking about how do we make the color schemes that we use more accessible. So thinking about people with different color visual impairments, color blindness. And I think there's a really interesting study in this field of cognitive psychology going back from the late 90s. And this wasn't specifically about weather or climate science, but what I thought was really interesting when they talk about the challenges in making our color schemes more accessible is they actually call out meteorology as being one of the sciences that is most problematic for having colors that are not accessible for all audiences. And over the years, there's been more and more studies that have shown, specifically in our field of weather and climate science, how important it is to think about improving colors to make our visualizations more accessible. So here's one again from the early 2000s that goes into thinking about more accessible color schemes. So even though often we hear about more and more, I feel, about accessibility for color and visualizations, there's a whole long, many decades worth of literature that talks about the importance of thinking about these types of topics. There's also different ways we can visualize graphs, not in addition to color. And I think this is a really interesting study that took a look again at climate data. And they asked a series of questions to really understand people's interpretation of an interactive visualization versus a static visualization. And I'll read sort of the key result here is the results indicate that the interactive visualization held higher potential for drawing people in and maintaining audience interests, whereas the static visualization was more useful for users wishing to gain a more detailed understanding of the data. So my takeaway from these examples, again, is that there's many different ways to visualize data and tell our story. And I think there's a lot of potential here to use it, again, as a powerful communication tool. And it's so important because, again, as I mentioned earlier, with that contrasting with the long scientific research process, is that the climate is changing in real time. And for me, this is an opportunity to communicate the data. Like I mentioned earlier with my Arctic example, another case study of sort of communicating our data in real time is thinking about Arctic sea ice. So Arctic sea ice has this seasonal cycle, meaning that it grows during the wintertime and reaches its maximum extent sort of around March. And then it melts during the summertime and reaches a minimum extent in September. And sort of this seasonal cycle is normal. The problem is we're melting more ice than we can grow. And that's sort of the long-term trend. But for many years, when we thought about media mentions talking about changes in the Arctic, specifically for sea ice, they might only talk about Arctic sea ice changes maybe twice a year at that maximum and minimum. But we know that all throughout the year, there are extreme events happening in the Arctic, and they're happening more and more. So we're seeing unusual temperature extremes within the Arctic, melting sea ice, even during the middle of winter. And so by tracking Arctic sea ice in real time and communicating that data to the public, I found it to be a really powerful way to talk about the Arctic changes, not just twice a year, but all throughout the year. And for me, this is an opportunity to share stories about human stories, about impacts. One of these examples happened a few years ago, back in 2018, where during the month of February, there was a very dramatic extreme event in the Bering Sea. So right on the right-hand side is a map. On the right-hand side of that map is Alaska. On the left is Russia. And in between is the Bering Sea. And what you might notice in this animation, where the white area is sea ice, is that it's moving northward. And that's not normal during the month of February. Sea ice should be expanding much further south in the Bering Sea. And so this is one of these extreme events that was happening, and it was impacting communities all along the coastline. I mean, there were countless examples of severe impacts happening. And this is why it's important, I think, to talk about how do we communicate all of this climate data, again, in real time, to tell stories about the impacts that we're seeing across ecosystems, across people and communities around the world. And so I think a lot of my way for thinking about this real-time communication of climate data actually comes from my background in meteorology. So we're all used to checking the weather forecasts. Here's an image of the National Weather Service forecast for Washington, D.C. And so every day on the news, you can find your local weather forecast. And it's just a very frequent topic of conversation where you can find the latest and current data and interpretation of it. So I've often wondered, is there something similar we can do for climate data to talk about it, again, tell these stories more frequently? And so over the years, I've thought about how do we visualize all of this complex climate data and update it in real time? So someone can go and find what's the current rate of loss of glacial ice, or what's the current changes in ocean heat content, and how do we share these visualizations in a way that breaks down the complexity behind the science, but stays true to the science and introduces it to new audiences. And I've started off over the years something small, just comparing something like global temperature versus greenhouse gases, or just looking at things like changes in temperature across the Arctic, so an Arctic dashboard versus changes in Arctic sea ice. But all of this visualization and communication of the data relies on a very important foundational observational data resource. And so over the last year, we've had challenges with that. So right now, there's a challenge for gathering the sea ice thickness and Arctic sea ice volume for one of the key data sets. There have also been changes for the satellite observations for monitoring Arctic sea ice concentration, or monitoring changes of the surface melt balance of the Greenland and Antarctic ice sheets. And so this really has shown the importance of supporting our data resources and the funding that goes along with it, as well as all of the scientific community and research behind it. And again, the Arctic is one of these areas that is changing so quickly, where we need more support to understand these data challenges over the course of the upcoming years. And so in addition to, I think, visualizing the data, it's also important for us to share, where does the data come from? So one of the things that I think is really important is, how do we talk about understanding this data that we're now visualizing in different ways? So what's the interpretation of the data? Where does the data come from? And if you're curious about what that little graphic was, this is just a mosaic image of showing changes in temperature across the summertime for the lower 48 United States. And interestingly enough, the story behind changes in summer temperature is not really that easy to communicate. There's something called the summertime warming hole, and it's a longer scientific story. So this is an opportunity for us to also talk about the complexities of the data and uncertainties behind the data for understanding our weather and climate system. And of course, always pointing back to, where does the data come from, and why is it so important that we support these federally supported data sets? And for me, all of this about communicating our data is built around trust and transparency, as well as making our science more open, breaking down those barriers, because to me, I think that is just so important for innovation, particularly around a topic like climate change. I'll also highlight there's some amazing resources that break down this climate data to make it more accessible. One of them is from NCAR, and it's the NCAR Climate Data Guide, where you can go up and look all of these types of different observational-based data sets and better understand where they come from, what's the science behind it, what are their advantages, limitations. And I really recommend this as a resource for whenever you hear one of these, complex data sets in the news, to go and check out this resource, where a network of experts has written these wonderful summaries to talk about it. And here's one of these examples. We have lots of different sea surface temperature products. So you can go here and can compare all of these against each other. And again, as I come to a conclusion here, I just want to keep reiterating about how effective communication really is a climate change solution. And to me, another example of this, we saw the climate spiral earlier, but the climate stripes are another, where it's visualizing global temperature change with these vertical stripes, blue, colder years going to red, warmer years. Again, finding creative ways to talk about our science and our data and communicate it in real time. And there's another wonderful piece by, again, Dr. Ed Hawkins, that talks about how we can utilize these visualizations to share climate change conversations and stories. And so my go-to tips, always stick to the science. I always suggest anchoring the science based on the evidence, and then simplify it, personalize it, and localize it. And so this really connects what can be this, all this a mess of data we work with to analyze climate models and observations and communicate that to the public for how it's affecting them in their backyards. And we really need everybody working at the table. So we don't just need scientists, we need educators, innovators, communicators, and so on, working to understand our science and communicate it. And I'll mention again, as I said earlier, that my career just would not have been possible without federally funded research and support, as well as amazing mentors and colleagues that have supported me along the way. And the science communication that I'm passionate about would also not be possible without all of this amazing open federal data. And this live stream is just a wonderful opportunity to share that all with you over the next 50 hours. And so we know that the impacts of climate change, they're accelerating. They require faster, more effective responses. We're seeing these impacts every day. And so again, to me, communication is such a powerful solution for breaking down barriers. And currently where I am at Climate Central, that's something we really work to do, is make the science clear, stick to the evidence base, and make it local. How does it impact people? So if you're interested in this across a wide range of topics, you can visit our website to find all of these different stories about climate impacts, weather impacts all around the world. And one other thing we do is we have this sort of monthly briefing where we talk about these types of changes at a monthly basis. So I encourage you to join that. And I will end here and happy to take any questions. Thank you.
Hello. Hi, Zach.
Hello.
What a treat. What a treat to get a talk from you. Zach is literally one of the best climate communicators on the planet. And I would highly recommend following his BlueSky account, which is just full of some nice climate treats. So thank you, Zach, so much. And we do actually have a lot of questions in the chat to get through because your talk was so fascinating.
Also, I always talk too long. Sorry about that.
No, that's fine. No, it was great. It was full of amazing material. Let's see, our first question from Arcturus has to do with Arctic amplification. What are the leading causes of Arctic amplification?
Ooh, yeah, that's a great question. So one of the ones I always start off with, which I think is one of the ones a little easier to explain, is something called the ice albedo feedback. So imagine the Arctic, especially during summertime where it's getting 24 hours of daylight. It's this bright reflective surface covered by sea ice, covered by snow. So when you have all that incoming sunlight, that heat, a lot of that heat and that radiation we bounce back into space. You're thinking like of a white t-shirt on a hot summer day versus like a black t-shirt that absorbs heat. The problem is, instead of having this really bright reflective surface covered by lots of snow and sea ice, is that we're seeing decreases in the amount of this icy surface. So more and more of that heat is now being able to be absorbed into that dark ocean. So the ocean is continuing to store more and more heat during the summertime. And then as the ice starts to refreeze during the fall, a lot of that heat gets released back out into the atmosphere, causing that additional warming, which then leads to more ice melting, which then you see more heat being absorbed. And so we often call this a positive feedback loop, where it just contributes to an acceleration of climate change in the Arctic. There's other really important feedbacks as well that influence changes in the Arctic that cause the warming. But yeah, I'll just point to some resources perhaps in the chat to sort of dive into those technical details as well.
That would be awesome if you could post that in the chat for us. We do have other questions. Thank you, Arcturus, for that question. And thank you, Zach, for your response. Our next question is from Infinity Chaser. Zach, what advice do you have for someone who wants to get better at data visualization?
My advice is to try different things. So for me, I post a lot of my visualizations, at least on social media. And one thing I have learned over the years is, one, to be very patient, but two is that is one of the best ways to get feedback. People are always willing to give comments. They're especially willing to say when they don't like something. So for me, it's a way I do a lot of tests where I take the same data, let's say Arctic temperature, and I create maybe 4 different visualizations of it. And over time, I'll post all 4. And then I'll see the types of comments and feedback people give, what they like, what they don't like, what's really working, what's effective for engagement, what's not. And I found a lot of surprises along the way. So I think trying different things is just such an important way of experimenting with visualization, especially for science communication. And for me, social media at least has been one way where I can get lots of really helpful feedback to refine my visualizations over time.
Awesome. Thank you for that answer. And I just a side comment to this question is Zach was actually my senior during undergrad in college. So the number of times I've texted Zach being like, hey, how should I visualize this figure or something has been very helpful for me, especially. Okay, let's take, we have time for one more question. This is from All Things PI. How do we differentiate daily weather variation from climate signals when calculating climate attribution on a short time scale, such as with recent extreme events?
Ooh, that's a great question. So I didn't get into it today, but one of the research areas that we actually work here at Climate Central that I do now is actually thinking about trying to understand daily attribution of climate change versus weather. And so I encourage you, we don't have time to sort of dive into the methods right now, but I encourage you to check out our website. It's called the Climate Shift Index, where it actually takes a look at, you can sort of distinguish the impact of climate change, human-caused climate change in real time versus the noise of the background of weather, and see how much human-caused climate changes influence the likelihood of, let's say, the temperature today in your area. And it updates daily, so you can track it there. And there's a whole rich literature field behind things like extreme event attribution and real-time climate attribution that has developed all these advanced statistical methods to better, again, distinguish the signal from the noise.
Yeah, the Climate Shift Index is really amazing by Climate Central. I would recommend that to everyone. Whenever we talk about extreme heat, or let's say warm ocean temperatures fueling a hurricane, we'll always reference the tools from Climate Central from that. So thank you for that really good question. Zach, it's been such a pleasure to have you on the live stream again this year. We really appreciate your time. I hope you'll stick around to watch some of the other talks.
Thank you.
Have a good one. Thanks, Zach. All right, everyone. Hello, my name is Mark Alessi. I am a climate scientist with the Union of Concerned Scientists. We just saw an incredible talk from Dr. Zach Labe at Climate Central. Really an incredible climate communicator as well as a climate scientist. Earlier, your host was Virginia, but she is now taking a break. She had to go. She wanted to go get some tea. I think she'll be back on hosting at a later time. The live stream, and I'll be here hosting for the next 38 minutes until 7 p.m. Eastern time, when I have to skedaddle to cello rehearsal. But I'm really excited about our next talk, which will actually be a panel. But before I introduce the folks on our panel, I want to just remind our viewers that we do have a 5 calls script. You can see it scrolling across the bottom right now, wclivestream.com/call. Please take the time. This is literally why we're doing this. Please take the time to go to that website, look at the 5 calls, call your representatives in Congress, your 2 senators and your 1 U.S. House representative, because this type of feedback that the lawmakers receive from you on the importance of weather prediction and climate research and climate prediction, they actually use that when they're figuring out how much to budget for the next year. So they're going through the financial year 2027 budget right now. The federal government has proposed a budget that slashes NOAA, NASA, National Weather Service, all of these very important weather and climate research agencies. However, Congress, right, they are the ones that control the power of the purse. They control how much money goes to each agency. So it is very important that all of us pick up the phone, call your representatives, be like, please don't listen to the federal government's budget. We need funding for the National Weather Service, NOAA, NASA, and the National Center for Atmospheric Research, of course, which Jen gave an excellent talk on earlier in the evening. Another point that we want to mention is we need people to specifically say, hey, we need to make sure that this funding is protected and distributed according to the law. While Congress controls the power of the purse, the federal government is the one, the executive branch is the one to distribute those funds, and sometimes they will hold them back despite the fact that that is against the law. So we need concrete language in our budget to say, hey, NOAA needs this funding, they better get it. NCAR needs this funding, they better get it, etc. All right, so that's kind of our ask that we want you guys to do, you excellent viewers. But now we're actually going to move on to the next part of the live stream, as we're in hour 3 now. We have a panel, 2 fantastic guests. They are both, one is the current American Meteorological Society president, and we will also have the president-elect of the American Meteorological Society. So I'll introduce both of our guests really quickly, and then we're going to do a nice little Q&A and hopefully take some questions from the audience. Starting with Alan, who is the current president of the American Meteorological Society. Alan is a retired broadcast meteorologist based in Mobile, Alabama. He holds a Bachelor of Science Meteorology degree from Cornell University, go Big Red, and an MS from FSU. He is the current president of the AMS. As I mentioned, Ellen went viral on YouTube for his 2017 coverage of Hurricane Irma, which I'm sure some of you might recall. He teaches weather broadcasting at the University of South Alabama, writes a weather column for his local newspaper, and serves as a weather consultant and expert witness. Ellen has authored 3 weather books and produced over 100 weather videos used domestically and internationally by K through 12 educators. Thank you so much. We're so glad to have you on here, Ellen.
Happy to be back.
Great. Yes, I should mention Ellen was on the stream last year when we had the previous AMS president, as well as Ellen, who was the president-elect at the time. Our next guest is Dr. Rick Spinard, who is the president-elect of AMS. He's an oceanographer with more than 40 years of experience in the public, private, academic, and nonprofit sectors. From 2021 through 2025, he served as Undersecretary of Commerce for Oceans and Atmosphere, and the 11th Administrator of NOAA, or the National Oceanic and Atmospheric Administration, overseeing a $7 billion agency with more than 12,000 employees. An elected member of the National Academy of Engineering, Dr. Spinard is Professor Emeritus of Oceanography at Oregon State University and previously served as the university's Vice President for Research. Throughout his career, Dr. Spinard has held senior leadership positions with the U.S. Navy, academia, and the ocean science community, earning numerous honors, including the Navy's Distinguished Civilian Service Award, and serving as the U.S. Permanent Representative to the UN's Intergovernmental Oceanographic Commission. He holds a bachelor's degree from Johns Hopkins University and a master's and doctoral degrees from Oregon State University. Thank you so much for joining us, Rick.
Glad to be here. Thank you.
We are glad to have both of you in our third hour of the 50-hour live stream. So I think we're going to go ahead and dive right into some questions, but we'll kind of start mixing in questions from the chat as they come in. The first question I think is very important for scene setting, for audience members, for those of you viewing on YouTube who don't normally follow federal weather and climate agencies closely. What parts of the nation's weather and climate enterprise are most vulnerable to current budget and staffing reductions? We'll go ahead and start with Alan.
Yeah, I'll kick it off. Every part, every single thing. What's interesting for me is that most of my career was as a broadcast meteorologist. So I was an end user of products like forecast models, satellite, radar. And I knew it came from the government, but I never really put in context how it got to me as a user. Now, we all get that now on our smartphones, online. And it's the government that has provided the foundation for these tools that we take for granted. They've provided the foundational research for these tools. So whether you're talking about weather balloons, dropping instruments from Hurricane Hunter aircraft, looking at your app and knowing that it's going to rain in 15 minutes, all of that is impacted by research. And I think that the big disconnect is that research is something you do now for what comes later. It's almost like exercise. You're exercising now so you'll have a healthy life down the road.
That's a great metaphor, Alan. Thank you. Rick, do you have anything to add?
Yeah, it's going to be very similar to Alan's answer. And I would say what is most vulnerable is 2 things, people and data. And the fact of the matter is that you can't predict the weather without the data, translating that into information, translating that into intelligence, if you will. And you can't do all of that with the people in the loop, whether it's the person launching the weather balloon at a weather forecast office or the person driving the computer models that yield the very highly accurate guidance used by the broadcast media, used by emergency managers, used by everyone who takes the weather into account. So right now, those that are most those pieces that are most vulnerable are the ones that are being cut, and largely it's the people in critical positions, and it's the means to collect and interpret the data through the observations and the model output that's used for forecast guidance.
Yeah, no, great response. I will say briefly, I think one of the silver linings that has kind of come out of all of this, these potential budget cuts, is the fact that meteorologists and climate scientists, I think, are starting to get better at communicating to the public, like, hey, we definitely need these observations. They feed directly into the models that, give the forecast to your phones. So I think that's been something that has been kind of a breath of fresh air, I will say.
Oh, Mark, let me jump in if I may.
No, please.
Quick introduction. A lot of folks may not actually know what the American Meteorological Society is. So
Yes.
We're here talking about climate. And I think a lot of people know meteorology is basically weather. It's atmospheric science. And climate is simply the average of weather. It's the average of atmospheric science. So the American Meteorological Society, we are coming up on 107 years old. And I know we don't look a day over 60, but we are a group of nearly 12,000 meteorologists, hydrologists, climatologists, oceanographers, climate scientists. It's not just about the weather, even though the weather and climate and everything is integrated. People may know the AMS, that we go by those initials, by watching your local forecaster on TV. If you still watch TV, you'll see across the bottom of the screen the letters AMS. And that's a certification, one of many certifications that the American Meteorological Society offers. And we just started a new one, and that one is a CCSP, Certified Climate Science Professional. I had to remember what that was. It's brand new. It just started this spring. So we are all engaged with education, educating ourselves as professional, learning how to better communicate to the public. And these are all things that are what the AMS does. In addition to, we do publish an annual climate summary. And then, of course, we have boards and committees, some of which are related specifically to climate communication. And we also publish a journal of climate. So we go everywhere from the highest level researchers to kids in elementary school who are interested in the science of weather and climate.
And if I can add, one of the points Alan made, which I'm particularly focused on, is that it's not just meteorologists. I'm an oceanographer, and the mission of AMS very much captures all of the environmental sciences, which makes sense because Mother Nature doesn't discriminate between the ocean and the atmosphere. And everybody knows, I think, that, for example, tropical cyclones, hurricanes, you got to have observations in the atmosphere and in the ocean. So AMS has really brought all of these capabilities under one roof.
Yes, and I'm loving this talk of also the connection between all the different components of our climate system. It's been really interesting lately because I feel like a lot of people have been focused on discussing the potential development of the super El Nino, which, it's just a warming in a small patch of the ocean in the East Pacific. How is that going to impact the weather across the rest of the world? But it does, because the climate system is so interconnected.
And the last thing I'll add, Mark, if I didn't explicitly say it, our membership is open to folks of many different levels. So we've got educators, K-12 educators, we've got students, and we also provide educational materials, textbooks, for example. And then on our website, we've got webinars. We've got a whole bunch of stuff. So just do a search for American Meteorological Society and also include the word climate, and you'll see a ton of stuff.
Great. Thank you. Thank you both for that. I should have definitely taken the time to define the organization. All right, let's move on to more questions. We'll also be taking questions from the audience. If any of you viewers have questions, we'll be sure to field them for our guests. Next question is, the US has long been a global leader in atmospheric science. How do research funding reductions affect our long-term scientific competitiveness? And we'll start with Rick this time.
Yeah, they affect our competitiveness in any number of ways, one of which is the ability to lead and direct international activity. So we get to go to major organizations like the World Meteorological Organization, or even just other nations, and work on a one-to-one basis and make agreements, for example, to exchange data, to share data, and also to share research findings. And in the US, we do a lot of collaboration, a lot of training, and we also send a lot of our researchers overseas to areas of expertise. The Meteorological Office in the United Kingdom, the European Meteorological office, all of these offices represent places where we can do collaboration. If we pull out of our investment in research, a lot of those international partnerships go down the drain effectively. And so consequently, down the line, we won't be able to discuss as an even partner things like data exchange or personnel exchange. So I think one of the biggest problems is just being able to work with our partners overseas effectively, and any cuts to our research is are going to directly affect that engagement immediately.
I'll add to that. People may not think about it, but the weather we experience across North America, it comes from somewhere else. And when it leaves here, it goes somewhere else. And the sharing of weather data is so critical to all nations to be able to know their own weather. So it is something where you can't just try to live in a bubble. You do have to keep those avenues of education, research, and collaboration open for everything.
Yeah, I I think when I'm also thinking about this, I love to mention just our rich history in weather and climate modeling. Like modern weather and climate science that was developed in the US, you know, in the 1950s, 1960s. We were the first to develop these weather and climate models to make weather and climate predictions. And we've kind of been part of that, you know, foundation ever since the founding of modern prediction. And I think that's, to just take, you know, a hammer to that is just kind of crazy. So it's really just it's so full of history here. Yeah, Rick.
Yeah, I'm glad you brought that up, Mark, because a lot of people don't realize when the modern era of high performance computing was just starting basically right after the Second World War, the people who worked in what we call information technology nowadays effectively said, hey, what are some tough problems that lend themselves well to high performance computing? And the first thing they identified was weather prediction and climate projection. And so consequently, weather research has been kind of a test bed for a lot of new modeling and computer capabilities, for a lot of new sensing capabilities as well. So we can think about your question in the context of more than just weather and climate prediction. It's been a foundational base for the development of a lot of information technology, for example, as well.
Yeah, no, that's a really good point. Yeah, it is interesting to follow go back to the history and know that, you know, high performance computing, or just computing in general, developed with weather and climate forecasting, which is really fascinating. Okay, we're going to move on to our next question. How important is the connection, and we've kind of actually already touched on this, between federally funded research and the operational forecasting systems used every day? And we'll start with Alan this time.
Yeah, so you said it, we touched on it. Federally funded research provides a baseline. It provides equal access for individuals, for entities, for private businesses. So from the investment our tax dollars create within the weather, we call it the weather, water, and climate enterprise, everybody benefits either directly or indirectly by the products that are further developed within the government or within private industry. We further benefit by those resources making our science industry attractive to people from other countries who come here to help us do better and be better at what we do. And then sometimes they'll stay, sometimes they'll go back to their countries. They go back to their countries, they take the information there, they get better. So everybody grows and everybody benefits when you have a good foundation for your science.
Yeah. Rick, do you have any follow-up points?
Yeah, I spent a lot of my career working on managing research for the federal government. One of the things that is quite obvious is that research is a risk reduction tool. It's where you get to say, what if? Can we try this? Where you can fail. I often point out to people it's called research for a reason. You try to do things over and over again and try to improve on them. And so consequently, some of the most dramatic improvements come out of a heavy investment in research. Right now, for example, we have over 120 Doppler weather radars at the weather forecast offices around the country. Those are called WSR 88D, Weather Service Radar. 88 means they were put in place in 1988. I'm venturing a guess that many in the audience here weren't even alive in 1988. And the D is for Doppler. So that's the current standard. The way we're going to get to the next generation is by doing research on really new, exciting radar technology. So that's the role of research. The role of operations, I think, is to define the requirements. We're seeing it right now. One of the consequences of climate change in the world of hurricanes is that we're seeing a lot more rapidly intensifying hurricanes. Hurricanes that increase by about one category in 24 hours. So go from a Cat 3 to a Cat 4 in 24 hours. And we're seeing quite a few of those. So the National Weather Service Hurricane Division, Hurricane Office, National Hurricane Center rather, is saying we need more research on what causes these to rapidly intensify. So that's a requirement. The operational side says, whoa, we need an improvement here. Hey, research guys, look into this. And then the research folks can start doing higher risk, higher payoff kinds of things and failing and trying another approach. And that's how the two work together. But it requires a very close coordination and communication between the operational folks and the research folks.
Yeah, no, that's great. It's so great to hear both of your answers because I think it really shows how connected kind of the U.S. research and operational enterprise is. And, you know, sometimes I think there's kind of a small disconnect between climate and weather communities, but I feel like we're trying to kind of bridge that gap more too. Okay, this next question is actually, I think, really appropriate for the live stream because a lot of the talks that we've seen already, and then probably all of the remainder talks of the next 47 hours, every person will talk about how federal grants, federal funding has benefited their career, their research, their drive and motivation to participate in weather and climate sciences. And this question has to do with, you know, how, or I should just say the question is, do you both think that budget reductions could create a sort of lost generation effect for graduate students, postdocs, early career scientists? How does this impact people coming into the field? And will we feel this, you know, for 10, 20, 30 years to come?
I'll start. The answer is yes, but specifically, I think our initial hit is what we call talent in TV. It's the performer, the person who does something. I teach a broadcast meteorology class. I have students who are not necessarily going to target broadcasting, but in this semester, I hear so much concern in my students of should they even consider working for the federal government. And that's an awful thought, that people would not want to work for the government, to serve all of the country. So if nothing else, by perception, the amount of change is creating fear amongst, I think, younger folks as to their careers, as to what they can do and where they can go. The timetable, boy, it could be a year, it could be 10 years, it could be 40 years. We just don't know.
Mm-hmm. Yeah, Brett.
Yeah, and there's another, I guess I'd describe it as insidious element to this, and that is, I'll give you an example. Just about a year ago right now at NOAA, 1,000 people were basically pushed into retirement on one day. 1,000 people left. That's not the significant statistic. The significant statistic is that those 1,000 people collectively had 27,000 person years of experience. So you had 27,000 years of experience walk out the door in one day. The Weather Service and NOAA, I know, are trying to hire back hundreds of people. So there are going to be positions for some of Alan's students, for folks who are mid-career and may want to move from the private sector to the government sector. But the challenge is going to be the steep learning curve. People are going to walk into positions where they're going to have to get up to speed pretty quickly with regard to the operational capabilities for doing the role of something like a warning coordination meteorologist who works with emergency managers. So we're going to have to find, this is a place where AMS is focusing a lot of attention. How can we help? How can the community help get these people started quickly and advancing quickly, give them the training and the tools and the mentoring needed to get up to speed?
Yeah. Something that I think is kind of related to this, and two of my friends have done this. Both, we all got our PhDs at around the same time. Both of them took opportunities in Europe for postdocs instead of staying here in the US, and that's because there wasn't really anything available for them. They were scared that, you know, these budget cuts could affect them in some way, and I think the kind of brain drain of scientists from the US also plays into this a little bit as well.
I'll add, there's one silver lining to this, and that is, and we see this in AMS, and that is the growth in the private sector. So if you looked at AMS membership in the private sector, say 20 or 30 years ago, it's a pretty small component.
Yeah.
And when I say private sector, I'm talking about those who are offering services or building equipment in support of the weather, water, climate enterprise that Alan alluded to. But now there are a lot more players. There's companies that didn't exist before. There's also more opportunity for contracts with the government through private sector. So this workforce we're talking about may have more opportunities in the private sector than they did before.
That's true. No, I agree. There's, especially from the climate science, I think there's a lot of people going into the private sector, which is still a great thing as well. Okay, we actually have some questions from online, so we'll take one of those in between the other questions we have prepared. This first question is from All Things PI. How can we make a stronger impact with open public comment opportunities, such as the one currently available for the absolutely horrendous federal grant overhaul proposal?
Comment. I guess there's some things in that question that a lot of people may not be aware of. And again, I'm learning. That's one of the cool things about being a part of the American Meteorological Society. The federal government issues statements saying, we are planning to do blank, and they open up what's called a comment period. And you can comment as an individual, as a company, as an organization. So the short answer behind that question is we all have a voice, and our representatives, our senators, our congresspeople who work in Washington, D.C. are the speakers of our voice. They need to hear what we are thinking. So that's the short answer to that question is we shake our heads and we say, oh, that's terrible, that's awful, but you've got to raise your voice and vote your voice as professionals and as citizens.
That's so cool.
One anecdote, if I can share it. One of the jobs I had was a vice president for research at a major research university. And at one point I told, there were about 1,000 researchers at this university. I said, you all are going back to Washington on a regular basis to talk to your program managers at NSF or NASA or NOAA. I said, I will pay for you to stay an extra day and go talk to your member of Congress. And very few people took me up on that offer. And and that was a long time ago where I don't think it was quite as critical. So kind of launching off Alan's comment, in addition to reaching out and writing letters and making phone calls, many of the folks here may be, if you are an active scientist right now, you're probably going back to Washington to talk to your program manager with some frequency. Take a little bit of extra time. Go talk to the staff on Capitol Hill and the members of Congress. Let them know what you're working on, why it's important that government keeps supporting research.
Yeah, and something I will add to this, and Virginia, the last host, was touching a bit on this when she, in between talks, but it is also very important if viewers on the live stream, right, many of you maybe can't go to Washington, D.C. to speak to your representative or senator. It's really important that you go to the 5 calls link we have set up. And if you do call your representative or senator, a good thing you can do is actually kind of personalize the statement, because they'll take it a little bit more seriously if you just don't read verbatim everything we've written there, but to say directly, why are you interested, why does this affect you, things like this, that's very important. And they do look at these, they do take these things seriously in Congress. Okay, great. Well, we had a great question from online. Let's go back to some of our other questions. The next one is, weather information is often described as one of the highest return public investments. How should policymakers think about the economic costs of underinvesting in weather and climate services? Maybe we can start with Rick.
I love this question because there is no aspect of your life, your livelihood, your lifestyle that is not impacted by weather information. The Weather Service did any number of studies. AMS has done studies. The National Academies have done studies. And the return on investment is somewhere in the neighborhood of 80 to 1. For every dollar we spend on the weather, climate, water enterprise, there's an $80 return. If you think about it, agriculture, energy, public health, transportation. I remember meeting with the senior leadership at Amazon once, and I said, tell me, when I order a toaster and it gets to my house the next day, how much of that is a consequence of knowing the weather and optimizing the shipping? And they said, oh, it's integrated. It's a critical element of that, being able to figure out whether we need to ship it from San Francisco or Chicago. And I said, then what we need, kind of like the Intel Inside when you used to buy a laptop and it would say Intel Inside, what we need is when you get that toaster from Amazon, on the side of it, it should say weather inside. You got this toaster in part because of the weather support. So every aspect of the economy and your lifestyle is impacted by weather and climate.
Well said. Nothing further to add, Your Honor.
was a great talk. Yeah, no, weather information benefits everything, and it is one of the highest return public investments. I think there's a paper about the National Hurricane Center forecasting with a new hurricane model. It improved like safety outcomes and money saved and lives saved, things like this, by a significant margin, and that's something you can't get back. That's because of U.S. weather and climate research.
Actually, I will add one thing, and that is that we are so successful at what we do in a sense that people take it for granted. No one questions, well, how right now on your device, you're probably seeing a temperature display, which happens to come from probably the nearest airport to you. No one questions how we know it's going to rain. No one questions how we know that we'll likely see a powerful or strong El Nino this year. All of it is about so much that we do, whether it's research, study, that is an investment into something that prevents something else negative from happening. Mm-hmm. So we don't see that negative part because we're doing all these positive things up front. And that's what we've got to continue doing as scientists, and being supported to continue doing things up front rather than pay the price down the road.
Agreed. And also stressing, I think, the communication aspect. We need to be communicating. This is all the things we are doing behind the scenes so that everyone has a safer and, the economy can prosper and things like this. That way people can know, your tax dollars are really going to something special here. Okay, next question. What outcomes 10 years down the line would convince you that the nation successfully navigated this period of uncertainty with the budget and staffing cuts?
I can't think that far.
I can think of one, and it's so obvious. It's seamless data. I mean, right now there are threats to, for example, the Mauna Loa carbon dioxide data, which is a keystone data set for climate. And yet, can you imagine, for example, going to your doctor, not going to your doctor for 5 years, then you go to your doctor and they say, man, your cholesterol's way up. When did that happen? And you say, I don't know. 5 years of no data. Who knows how it happened, when it happened? And that's the risk we're at right now. So I think if that doesn't happen, if we continue to have this seamless flow of authoritative, quality control accessible data, then we will have succeeded. It's a low bar, but it's one of the most important elements.
Yeah. Ellen, do you have anything to add?
No. Yeah, only because it's almost a question of saying what bad things won't happen in 10 years that would make you happy, I guess. So it's hard to process.
That's true. Yeah. And something that, Rick, something that you said, very important to have continuous observations, because I know they have threatened the Mauna Loa, but they've already cut certain data sets like.
Absolutely. Absolutely.
Yeah.
The $1 billion disasters database is a really good example.
Yep. And also the satellite that was measuring ice thickness in the Arctic, which I think Zach may have mentioned briefly, I'm not sure. But that's another example. And they were about to cut one of the satellites through the defense program that looked into like the thickness of a hurricane structure, which I think would have been devastating. DMSP. So hopefully we can get these things to stay or get them back online as soon as possible.
Yeah, I mean, even more coarsely, keeping the satellites, keeping the observations. Gee, wouldn't it be nice? What was your time frame? 10 years from now? 10 years from now to see that NSF has a $25 billion budget. NOAA is at $15 billion. NASA has 10 more satellites doing things like ocean color and carbon as a regular operational capability. Right now, that's pie in the sky, but I think we can do it. It's just going to take a lot of the effort we've been talking about here.
Yeah. Well, thank you for that. Okay. We're actually, all right, we have 4 minutes left. I think we have time for one more question. Let's take one from the audience. It looks like we have one from All Things PI again. Do you have any advice for students who currently feel like we can't rely on not only the federal government, but federal funding grant institutions such as the NSF for future research? Kind of going back to a previous question.
My short advice is don't give up hope, never give up hope. Follow, and this may sound cliche, but follow your dream, follow your passion, because in the best case, you'll be doing it for your entire life. But with all that, have a plan B and have a plan C, and make sure that you are networking, learning from others, the pitfalls they may have faced. Not living in a bubble, but being realistic about what we're seeing, that it may become an obstacle, but even more importantly, what we're seeing happening now in the federal government is cyclical. In broadcasting, and we've always had cycles of hirings and firings and layoffs. So there's really no career where there are not cycles of really good and really bad. So that's just a part of life, not a happy part, but be prepared for those cycles, but don't let them deter you.
I can't add to Professor Siegel's excellent response. I agree.
No, it was really great. We actually have another question from the audience. Actually, this question is really interesting because we had Zach on before, who is a self-proclaimed weather weenie, like me as well. We've been obsessed with the weather since we were in elementary school. But then Jen had mentioned that she had not gotten into atmospheric science until she was in college. So this question kind of has to do with that. Did you guys start in the weather and climate field? If not, where did you start? They're curious. Maybe we can start with Rick.
I decided in 7th grade I was going to be an oceanographer, and I never veered from that course. And then about 20 years ago, one of my coworkers said to me, you really need to join the American Meteorological Society, and you need to learn a lot more about meteorology. And he was absolutely right. And so I considered it an expansion. I went from very dense fluid to much less dense fluid, from the ocean to the but I started as.
Excellent. Alan.
And for me, I started where I ended up. As a little kid growing up outside of New York City, I was fascinated by snow, by hail in the summer. Third grade, I was fascinated by the fact that clouds float. And if you never thought about it, they are made of water, which is heavy, and it falls, and then the cloud disappears. You have to get into the molecular weight and updrafts and downdrafts. But either way, it was in high school that I settled on weather as a career because it combined, actually broadcasting, because it combined community service, the science of meteorology. And I was wise enough as a young man to know that, as Rick mentioned, weather controls everything. And if you go into the atmospheric sciences, you're guaranteed a job. It's a question of where, what part. But weather, just like all the geosciences, we can't live without it.
Excellent. Yeah. Thank you both for some more information on your background. So we're actually just entering our 4th hour of the live stream, which brings an end to our incredible panel. Thank you both, Alan and Rick, for taking the time to represent AMS and to answer these questions and to hopefully inspire some action on the part of our viewers to call their representatives in Congress.
You're welcome.
But thank you for coming. Yes. Have a
Thank
good
you,
evening.
Mark. Thanks for doing it.
Yep. Thanks, Rick and Alan. Okay, so I think we're bringing on a new host now. I'm not sure. There he is.
There he is.
Okay, well, I guess you will take over. I will pass the hosting duties to you.
Are you going to pass it? How do you?
No, because remember last year when I tried to high five Stella and it was like the wrong side of the screen?
Go on, high five me. We can do it. I believe in us.
It's this side for me.
Oh, really? Okay.
Okay. It's going to be another terrible photo.
It's going great.
We're doing okay. We're doing okay. But yeah, well, thank you all for having me, and you're in good hands with our leader of the live stream, Andrew Williams. Thanks, everyone.
Bye, Mark.
Bye.
Oh, okay. We lost someone for a second, but thank you all for being here at the 4th hour of the live stream. We have 46 hours to go, and we just had this amazing panel with the AMS presidents, with Alan and Rick. That was a fascinating conversation, and really engaging about issues that are important for all of us, right? So I think it's important that we take time between these talks to just remember why we're here. And really, the key reason is that every person on this planet needs actionable weather and climate information, whether it's the weather forecast on your phone or whether you're a farmer trying to plan for the upcoming harvest. And as a result, I mean, it's lucky for us that the US has built up this incredible infrastructure around weather and climate forecasting. We are really world renowned for what we can do in the weather and climate space. And thanks to this work, we can now predict the weather conditions, as I said, days in advance. And we can also predict in years in advance the impacts of human-caused climate change. And this is not just something that happened out of nothing, but it's only made possible because of decades of investment by the federal government, paid for by you, the taxpayer. But now the current administration is, I would really say, destroying the foundations of this miracle that we've brought together. And one of the things that has really hit me over the past few days, and particularly today, hearing the talk from Jen, was about the National Center for Atmospheric Research, or NCAR. Now, we've already heard a talk about NCAR, but I just want to remind some of you guys what that is and why it's important. Like, basically, most of the weather and climate research in this country depends crucially on the work that's done at NCAR in Colorado. And the administration is now attempting to break up the critical lab, not because of any scientific issue with the lab, or even that it's actually inefficient, but because its research doesn't align with the administration's political priorities. And this is crazy because breaking up NCAR not only undermines all the scientific research that Jen was telling us about earlier, but it also hurts the economic health of the nation. It will raise housing prices because insurers will not be able to access NCAR's crucial information, and will also leave us, the American public, ill-prepared for what's coming down the pipe in a warming world. But it doesn't have to be this way. You can go to the link at the bottom of this page, wclivestream.com/act, and it takes you to a page which looks something like this. So this is the 5 Calls website, and you put in your zip code. It tells you, for me, I have 3 representatives to call, 1 in the House, 2 in the Senate. It gives you a script, what you can say to them, and it's actually really easy. I was nervous doing this the first time, but it makes it really straightforward. And so, yeah, I believe in you guys. You can go out, you can call your representatives, you can tell them to stand up for weather and climate science in this country. And with that, I want to bring on our next speaker, who is Dr. Jeff Masters, who Jeff is, as I was talking about earlier, Jeff is a famous hurricane hunter and the co-founder of Weather Underground. And he's going to be talking to us today about his life as a hurricane hunter. I think we'll put up his slides now. Sorry. And yeah, Jeff, over to you. Thank you so much.
There we go. So a lot of the stories I know about weather that I'm telling today were made possible because of federal funding from the National Science Foundation and other organizations. It's been indispensable in my career, and I'm going to go through the 45 years of stories that I have accumulated. And something important to realize when you are trying to do outreach, trying to do communication, storytelling is critical. Start your message with a story that draws the attention of your audience. And then after you have their attention, then you can give them those facts that you want to get across. So start with a story. That's the key thing to do. And I got a lot of stories, let me tell you. My career as a meteorologist really began in 3rd grade when I co-founded the Birmingham, Michigan chapter of the Mad Scientist Club. I was always fascinated with science. I had 3 magazine subscriptions. I had Weatherwise, I had Rock and Gem, and Sky and Telescope. And I was sure I wanted to be a scientist. I just didn't know which kind. So when I founded the Mad Scientist Club, we set up some criteria for how you could go about getting a career going in science. You could write down 50 pages of facts about any scientific topic and get a bachelor's degree. 100 pages would get you a master's degree, and 200 pages would get you a Ph.D. Now you can see in this slide a few of the facts that I wrote down. I wrote down a fact page for every single planet and their moons, and it had little helpful things like, have I seen it? Here's the moon of Jupiter, Io. And I said, yes, I have seen it. I had a telescope so I could see this thing. And of course, I was very fascinated with the tornadoes, having grown up in Michigan. So I did a lot of fact pages on tornadoes. But I found out I really padded my dissertation, my master's dissertation with the Mad Scientist Club by having 10 pages devoted to a Fahrenheit to Celsius table every 2 degrees. So that was kind of, I don't know, pre-AI, how you would kind of game the system, I guess. I got a lot of, pages there. I never did get a PhD with the Mad Scientist Club. I got a master's degree, which is appropriate for somebody with a last name Masters, but I fell short of getting my PhD. In 1974, when I was 13 years old, a very historic weather event helped launch my career as a meteorologist. It was a F4 tornado back then that devastated my father's hometown of Monticello, Indiana. And here is a video that we took a couple weeks later. We went into Monticello and saw his boyhood home that got damaged by the tornado. And the church that he went to was destroyed. The house he grew up in eventually had to be torn down because it was too damaged. So this had a big impression on me as a young boy interested in science, seeing this place, my father's boyhood home destroyed by an incredible tornado, by the biggest tornado outbreak in history, the super outbreak, which was categorized by no other than Mr. Tornado, T. Theodore Fujita, developer of the F scale for tornadoes. He became my boyhood hero after this, and I followed him. And you see there the map that he made of all of the tornadoes from that event. There were 5 in Michigan near where I grew up. So it had a big impact on me to follow his research. I actually sent in $1 worth of stamps in the mail to University of Chicago to get this map from Dr. Fujita himself. 1974 was also the year I started tracking hurricanes. I didn't do a very good job of it because it was hard to do back then. All I had was the Detroit Free Press articles. And of course, you know, they're not going to cover hurricanes in great detail. Much easier nowadays when you've got the internet. So I went on in high school being interested in science. And when I got to the University of Michigan, I thought I would be a physicist, but it didn't really work out that way. I didn't do very well in my first physics course. So I decided, you know, I'm going to do applied science. I'm going to pick meteorology. I thought about geology, but it just moves on timescales too slow. I want something that changes day by day. So I picked meteorology, got my bachelor's degree in '82, got my master's degree in '83. So now I had 2 master's degrees, one from the Mad Scientist Club and one from the University of Michigan. And during my master's research at the University of Michigan, I got my first 2 co-authored published papers, peer-reviewed papers. Both were on air pollution. I began to realize when I was in college that, you know, the planet needs a little help here. We are, as a species, dumping our waste gases into the atmosphere. And back then, the big topic was acid rain. So I did 2 acid rain research projects, actually. One as an employee of Ford Motor Company for the summer. I worked with their excellent atmospheric chemistry division, and we did a Pennsylvania-based field project studying acid rain. So I wrote my master's thesis in 1983 on air pollution around Detroit. And then after that, I decided, well, I'm going to go off to Ph.D. school. And I decided to go to the University of Arizona to look at, again, air pollution. This time I was going to study trace gases, I mean, very low concentration pollutants made by lightning. How does lightning affect the atmospheric chemistry? It turns out that it makes pollutants in very trace concentrations, nitrogen oxides, which then I studied by looking at wind patterns across the desert Southwest. And it was really awesome being down there in Tucson. I saw some incredible meteorology. The Arizona monsoon was just spectacular. But getting a PhD there was not meant to be. I was feeling too burned out from working through my master's degree in just a year and a half back at the University of Michigan. And after just a year at the University of Arizona, I decided I needed a hiatus. And I took a year off. I quit school and spent 1985 traveling the Northeast US, playing ultimate Frisbee and hanging out with friends. And while I was in Boston, I happened to see the first and only hurricane I've ever seen on the ground, Hurricane Gloria, which blew through Boston, bringing basically category 1s to where I was here on the coast. We're doing what we call body sailing here underneath an overhang at Marblehead Beach. After that experience, I went back into meteorology. I was convinced I was never going back to school. I wanted to enter the job field. And I got a job in 1986 as a lecturer in weather forecasting at SUNY Brockport in Brockport, New York. And while I was there, I worked on this story that eventually got published in Weatherwise magazine on, well, what it was like to get an education in Brockport. And it was while I was at Brockport that I met 2 mentors of mine, Ira Geer and Bob Weinbeck, who both worked for the education program for the American Meteorological Society. And Ira in particular stimulated me to become a communicator. He envisioned me as being the Carl Sagan of meteorology. And I said, okay, right, that's not going to happen. But he was instrumental in helping me be, open to communicating to the public about weather and climate change in particular. One of my jobs at Brockport actually was to maintain their climate records. And here I have a humorous video about that.
Once around is a day. And I had to pick off the high and low temperature for all 8 days. Not an easy task, considering the red line is not the temperature line. The actual temperature line is virtually invisible. You can maybe see a faint little trace here. Yes, climatologists have nightmares about this kind of thing. However, after just a mere hour of diligent work, I managed to puzzle it out. With a little help from my friends here. I mean, what does it matter what the high and low was anyway? Who cares?
After that experience, I moved down to Miami, Florida to join the hurricane hunters. I applied for this job thinking there's no way I'll ever get this. It's a meteorologist's dream job to go work with the world's top weather scientists and fly all over the world studying the world's most incredible weather. But they wanted me, so I flew down there. And for 4 years, I worked as a flight director for NOAA's P3 aircraft. And what the flight director does is you act as the interface between the crew of the aircraft and then the scientists. The scientists will hire out the aircraft for a period of a month or two for a field project, usually with foundation funding, National Science Foundation. And then the aircraft will supply all the equipment and the crew to fly and make the mission happen. So I acted as the interface between the crew and the scientists. And it was my job after the flight to analyze the data and make sure that instruments were calibrated correctly. And it turned out that my very first field project was with Mr. Tornado, my boyhood hero, Dr. Fujita. He hired out our aircraft to go study microbursts. And he was one of the pioneering scientists about microbursts and downbursts and straight line winds that cause damage. And it was just a thrill to be able to participate in a field project with him. And he invited us over to his apartment after some of the flights, and we got to have beers with him and hear his funny stories. Just a wonderful human being. And I really picked an amazing person to be my boyhood hero. And I was so lucky to be able to have this as my first experience with the hurricane hunters. To pull this project off, we used our Doppler radar, which is one of the only Doppler radars in the air in the world. So when I was with the hurricane hunters, I published my first story that was intended for a general audience. It was the story of my first flight as a flight director into a hurricane, just a Cat 1 off the coast of Mexico in the Pacific. It was called Hurricane Pain. But my main work for writing at the hurricane hunters was to do research, and I was co-author on 3 or 4 papers on how to measure winds and pressure and temperature and humidity from aircraft. Not an easy thing to do when you're flying 250 miles per hour, as it turns out. In the summer, we'd fly into hurricanes, but in the winter, we would fly usually in the Arctic. So my first winter program was in Alaska, 1986 to 87. And here's the plane here in Cold Bay, Alaska, near the Aleutian Islands. We were flying over the Bering Sea studying winter storms. Here's the plane getting de-iced before a flight. And here's a shot flying over the Malaspina Glacier of Alaska. You can see a trail of clouds coming off the glacier, very cold wind called a Bora wind that's condensing out when it gets over the relatively warm Gulf of Alaska. One of our projects, we were studying gap winds blowing through the gaps in the mountains between the Aleutians and the Gulf of Alaska. And it was during this flight I had my first day where, well, I usually tell people driving to work in the morning was the most dangerous part of the job. Not this day. We were flying at very low elevation over the ocean in 80 to 90 mile per hour winds. And this was the state of the ocean, pretty mixed up because of the high winds. And we were getting sea spray on our window, which normally isn't a problem. You just push the button and the windshield washer washes it off. But in this case, we did that and the windshield washer didn't work. So here we are over the Gulf of Alaska, salt spray building up on our window. So the pilot's having trouble seeing. So, okay, we're going to climb higher and do the mission at a higher altitude. Well, it turned out we had to climb to about 4,000 feet before we stopped getting salt spray on the window because it was such an intense windstorm. And we ended up flying back to Anchorage then with a nearly opaque window, and the pilot asked me to find a rain shower to rinse that off. Well, there weren't any rain showers to be found over the Gulf of Alaska, just snow. In fact, it was a blizzard. And that blizzard was helping drive these winds of 89, 90 mile per hour we were seeing. So here we are needing to land in Anchorage in a blizzard with a windshield that only has about a narrow 2-inch thick strip, kind of cleared away by the windshield wiper, which was able to scrape a little bit of the salt away. And the winds are blowing 45 mile per hour at the surface in this blizzard. And our pilot, who is one of the best, Bernard Mandelker, he just put us right down on that runway. And as soon as we pulled to a stop, the ice-covered runway was so slippery that the plane started blowing sideways. So the ground crew had to come out, put these heavy steel cables on the plane to keep it from blowing across the runway. And that was my first terrifying experience with the hurricane hunters. My second terrifying experience was in a hurricane. That summer in 1987, we flew into my first major hurricane, Category 3, Hurricane Emily. And during that flight, we hit 3 Gs of acceleration when we hit an updraft that was 53 miles per hour, followed by a downdraft of 21 miles per hour. Stuff started flying around the inside of the cabin, which isn't very safe, of course. And we did that a couple of different penetrations. We went in and out of the eye several times, and the turbulence kept getting worse and worse. Finally, on our last pass through the storm, the pilot came back to me after we finished that pass, and he said, Jeff, we just had an aerodynamic flutter on the left wing that I had to break by rolling the aircraft. I suggest we abort the mission and go home. I looked at the chief scientist on board, and he looks at me and he says, if Jim Gano says to go home, we're going home. So we aborted that flight, and it's the first flight I'm aware of that we had to abort because of extreme turbulence. And as it turned out, the No Hurricane Hunters have only ever aborted 4 times for extreme turbulence in a hurricane, and I happen to be on 2 of those since 1976. Okay, my third terrifying flight with the hurricane hunters occurred in another Gulf of Alaska winter storm project in Seattle, as it turned out. We were just completing the project where we were studying a winter storm off the coast, and we were riding a 200 mile per hour jet stream wind home. We were flying at 25,000 feet, incredibly intense jet stream winds, which was really exciting for the scientists because they hit a jackpot for an intense winter storm, which is what they wanted to see. But when we went to land at Boeing Field, which is owned by the private company Boeing, we were having to deal with this situation, mountain wave turbulence. When a strong wind hits the Olympic Mountains, which is upstream from Seattle, you get these undulating motions, which causes turbulence. When a plane tries to fly through that, you can get very high wind shear, which is very dangerous to fly through. So we're flying towards Boeing Field, experience this incredible turbulence, 70, 80 mile per hour winds. The plane is just gyrating all around because of these crazy updrafts and downdrafts. But we're listening to the weather report from the tower at Boeing Field saying, winds are 20 knots out of the west, gusting to 30, barometric pressure, blah, blah, blah. So they didn't sound concerned about it at all. So we were getting our directions actually from air traffic control in Seattle, not from Boeing Field, the private company field. And we went to land at Boeing Field, and still, this recording that we're listening to from the tower saying winds are 15 or 20 knots out of the west, blah, blah, blah. And as we're just a wing length away from the runway, we hit this really strong downdraft, and we almost scraped our wingtip right on the runway. And the horizontal winds were still blowing 50, 60 miles per hour. So we did a go around. We said, let's go land at SeaTac at Seattle Airport. And we did that, and the winds weren't too bad there. And we found out what had happened is Boeing Field had abandoned the control tower and left the recording in place of the winds that were present an hour before we landed. So in reality, the winds were crazy dangerous to land in, 50, 60 mile per hour winds and extreme turbulence. So we just dodged a bullet there. My fourth terrifying flight with the Hurricane Hunters occurred based in Norway. We were flying over the Norwegian Sea and off the coast of Greenland. Very spectacular flying in this environment. But as we were flying over Greenland and night came upon us, we were having trouble communicating. Our HF radio went out. We could not talk to anybody. And here we are flying in an incredibly remote part of the world over Greenland where there's no communications. Nobody would know if we went down. And we didn't know what the heck was going on. The pilot wanted to abort the flight and go back. The chief scientist talked him out of it. And eventually we compromised and did just one more hour of the flight, cut it short an hour and went home. And we didn't know, why did our communications go out? Well, this is the reason. We hit the third strongest geomagnetic storm in history while we were out there flying. This storm took out the power grid in all of Quebec because it was such an incredible current that started flowing through the lines to the hydropower plants. So I'm sure I got a crazy dose of radiation flying at high altitude during this geomagnetic storm. And we did see an incredible display of northern lights and St. Elmo's fire on the bright side. Finally, well, this was not a terrifying flight, but I managed to fly through the strongest hurricane on record at the time, Hurricane Gilbert, 888 millibars, and did my first interview ever.
It's right in the eye wall. That's just like Alamo.
We're looking awful high that far away.
That's true. Yeah.
But it looks a lot like Allen on the 8.
Yeah.
Which makes sense. And it was a piece of cake at 5.
But Hugh Willoughby, lead scientist, and flight meteorologist Jeff Masters are concerned that today it might just be too dangerous. Should they chance 5,000 feet to get the best data or climb up to 10 for safety?
We climbed up to 10 for safety. So fortunately, that did not turn out to be one of my terrifying flights with the Hurricane Hunters. But my next major hurricane I flew into in 1989 was another one of those terrifying flights. And that was a subject of last year's live stream I did. And I've written up a whole account of this you can read online, and I'm not going to go into it here. Suffice to say, we hit extreme turbulence in the eye wall. The number 3 engine caught on fire. We plunged out of control into the eye where it was calm and pulled out above the waves 900 feet high. So that was my last flight with the Hurricane Hunters. I went on to get my Ph.D. at the University of Michigan in air pollution science. Third time's a charm. I finally got my Ph.D. this time. And while I was there, I founded this crazy weather company called the Weather Underground. And it started off just as a text-based telnet session that you see here. The Weather Underground actually got its name from a Bob Dylan song. And it was a tongue-in-cheek reference to the radical group, which also got its start at the University of Michigan. The radical wing was called the Weathermen or the Weather Underground. So kind of a crazy history. We became the most popular service of any kind on the entire internet worldwide in 1991 and 92, just this little text-based system. So using that, we got National Science Foundation funding, several $1 million, and we set up a text and image-based service using the client Gopher. This was back before the World Wide Web, and we trained a bunch of teachers on how to use the World Wide Web and do science education. So we did some cutting edge stuff. We had a cable TV show we did, and we hired a puppeteer and a comedian to help us out.
Hurricane Opal, depicted in this picture, has hit.
We are in the eye of the hurricane. Clouds to the north, south, east, and west of me. Blue skies up above. Relatively calm. This is Walter Eagle, apprentice weatherman, reporting.
After doing that for a few years, the National Science Foundation encouraged us to go commercial, and we did. The Weather Underground became a very successful private company, and it would not have happened without the National Science Foundation, in particular the Unidata program, which helped us out considerably. So we steadily grew in popularity. In 2005, I started blogging, and the hurricane season of 2005 really helped launch my career, particularly Hurricane Katrina. And my blog, which initially started off getting like 10 comments per post, now is getting thousands of comments, getting a lot of media attention. And I've been blogging ever since. So I've been blogging for 22 years now, ever since my Weather Underground start in 2005. The comment section of my blog was a crazy place to be. And one of the proudest things I have to say about the whole blog thing is it helped found a disaster relief charity called Portlight, which is now called the Partnership for Inclusive Disaster Strategies. So a few tips on climate communication I've picked up over the years. Use awesome and colorful images. Use images with people in them. They attract the most attention. And don't be afraid to take a break if you get overloaded. You don't want to overdo it. It's easy to do in this profession. I'll skip over this one. In 2012, we sold to the Weather Channel, which I really didn't want to do at the time. I wish we'd gotten a little mediation in our group of 4 that were controlling the company. We had a lot of disagreements, which ended up in us deciding to punt and sell the company. And well, the name lived on for 10 years.
Yes, Weather Underground is coming to television. And yes, I'd love to be the host. But those people are so proud of their brand, so protective of it. I've been going through a pretty rigorous screening process.
Mike, as you know, at Weather Underground, we're obsessed with the science of weather. So we want to have a host that shares that passion, and I've prepared a little test for you. I just want you to look at these cards and tell me what you see.
I see a hurricane eyewall replacement cycle.
Okay. And this one?
Discrete supercell with an inflow notch.
I'd go along with that one. And finally, this one.
I see a perfectly cylindrical hodograph.
Now, cirrus lacanosa cloud form, clearly.
So eventually, Weather Channel sold us to IBM, and IBM showed me the door in 2019. And ever since then, I've been blogging for Yale Climate Connections happily, and I hope to continue doing that for the foreseeable future. One final tip: you should end your communication efforts on a positive note. And I wrote this post in 2024 on what you can do to prepare for the climate change storm that's coming and is already here in a lot of respects. A lot of things that we can do to prepare. Certainly the revolution in clean energy is a great, wonderful thing that's unstoppable. And we need to understand, yes, things are dire, getting more dire, but there are things we can do. And I suggest you visit this post and then my previous one I outlined here about when I think that the world's going to be turned upside down. So that's all I have, and let's take a few questions.
Fantastic. Thank you, Jeff. I think me and a lot of people in the comments section were kind of getting sweaty palms when you were hitting your 4th near-death experience of the talk. I think you're probably one of the few people I know who can have a top 10 near-death experience list. Pretty awesome. Yeah, I gotta say this as well. I think you used the term you used the blue skies thing before it was cool, right?
Yeah.
Now blue skies is like the Twitter takeover, but you guys were using that before. Also, I almost share a birthday with Weather Underground. I saw from that thing.
Awesome.
But we have a lot of comments, a lot of questions. One of them that I thought was great was just someone. So Cambrian Anomala Karis said, "How high up are you compared to space and compared to fog when you all are flying to measure hurricanes?"
It's standard now to go in at 10,000 feet if you're in a Category 1 or stronger hurricane. We did Category 5 Hugo at 1,500 feet and got in a lot of trouble. Ever since that flight, no, you can't do that. You have to go in at 10,000.
Awesome. Yeah, when you were like, we'll go to 10,000 to be safe, I was like, yes, please be safe. We had another great question. You were bringing up a lot of great things that I think people want to protect about the National Weather Service, NOAA, and so on. One question that we had from Confused was, what can we do outside of the US? What's something that people can do, do you think, if they're not able to call their own representatives? Maybe.
Just the education aspect. The more people know all over the world about climate change, the better we'll all be. So it's just a matter of getting out the word, spread the word, get people's attention on what's going on, share some of these great researchers and the fantastic work they're doing on what are the big threats that are happening now.
It's a really great point. I think, yeah, just having those conversations around the dinner table as well, super important. Another question from Cosmo, who has been super active in the chat, thank you, Cosmo, is if someone wants to get into weather and climate today, specifically something like your work, what advice would you give to them? I have a friend who's really interested in hurricane science.
You need to be good at math and chemistry. Those are, and physics. The hard sciences are important to do well at. And the prerequisites for getting a meteorology degree are, a couple terms of calculus, or 4 terms of calculus, 2 of physics, 2 of chemistry. And you also should be a good communicator, learn how to use the internet, learn social media, practice getting in front of a camera, maybe talking like I'm talking, just go out and film a weather event going outside your window and learn what makes that weather event tick and maybe share that on social media. So I see social media as key, probably AI as well now too. It's a new world.
Yeah. Did you have any, was there someone who was like a mentor to you when you were starting to do this outreach stuff, or like, your first interviews and things? Was there anyone or any resource that you were using at the time to like get into that?
Nobody really. It was pretty crazy. Right after I got off that flight in Hurricane Gilbert, the strongest hurricane of all time, I went straight to the National Hurricane Center and did an interview live with Larry King, and his other guest was Chuck Yeager, the test pilot. So I'm just like, shivering in my chair saying, I don't know what I'm doing, but I got through it. And, you just trial by fire is how I did it.
Mm-hmm. That's pretty cool. I basically view you as a test pilot, given all of these stories at this point. Like, I feel like Top Gun 3 will have Jeff Masters in it. So people were really excited about hearing like the way that you didn't just go like straight through at every stage, and you've had this really like, maybe it's not non-traditional is maybe not the right word, but you've taken breaks at different points in your career. One question from Infinity Chaser was your gap year helpful for burnout? You touched about burnout at the end, but how's that been something that you've dealt with, when you've got all this crazy stuff you're balancing in your career?
Burnout is something you have to respect. If you find yourself not wanting to do something, pay attention to that. What is behind that? The past 6 months or so, I found myself not wanting to sit in front of a computer because I've done that so much of my life. So I stopped doing it so much and I was happier. So happiness is very important. If you're going to be a grumpy blogger, you're really not doing your audience much of a favor. You have to be into it. If you're feeling burnt out, hey, that's your soul telling you that you need to explore other ways to express yourself. Respect burnout. I mean, yeah, we really need people to be doing communication on weather and climate change. It's so critical right now. But if you find yourself not happy doing it, then let somebody else do it. You can go back to it later if it's appropriate then.
I think it's a great point. And also it kind of ties back to what Adam was saying at the beginning about science and art. And in a sense, when I think about my own work, there's, what we do, a lot of what we do as scientists is inspiration based. A lot of the work that we do, you have to, like you're saying, you have to be psyched about it. You have to really want to do it. And so you've got to give your body and your mind the space to get inspired, Another question from, I don't know how I'm going to pronounce this, but Tivra 6760 is, have you mentored others who want to follow you or maybe have followed in your footsteps over the years?
I've done a lot of Zoom mentoring sessions, particularly with students at the University of Michigan. I've done things both via Zoom and in person. And I've also done students who aren't living in Michigan at all either. If I'm open to requests for mentoring, if somebody wants to shoot me an email, I'm weatherman.masters@gmail.com. I'd be open to doing a mentoring for anybody interested in becoming a meteorologist.
Well, thank you very much, Jeff. And yeah, for those wondering, I can confirm he responds to emails. So we're gonna have to move on to our next speaker now. But Jeff, I want and for my fourth terrifying experience, I want that on a T-shirt now. So I don't know if you
on my Climate Science Legal Defense Fund shirt. That's my other hat I wear. I'm a board member on the Climate Science Legal Defense Fund. Donate well.
Go for it. All right. Thanks, Jeff. Put some love for Jeff in the chat, everyone. All right. Thank you all for tuning in, and the chat. You guys have really been hyping it up. I love this. Cosmo, All Things Pi, Infinite Chaser. You guys are really keeping things going. There's also been some what do they call them when you reunite? I forget the word. But we've had some people from last year who've met each other again on the stream. We love bringing people together here in the name of weather and climate science. But before we move on to our next speaker, who I'm super psyched about, let's just take a second and we're going to think again about why we're here. So, as I said before, everyone needs actionable weather and climate information. We just saw from Jeff the lengths that we've gone to over the years in order to get that information, to initialize our forecasts, to make better forecasts, to protect lives. And this has been something that we've built up over the decades as a result of sustained federal funding for science. But now that foundation of this success is under threat. And one thing I want to highlight is that the administration has just proposed a budget for the next year. So the way it works is the president proposes a budget, Congress talks about it, and maybe rejects it or accepts it. The president's proposed budget is really drastic and would decimate US science. So the president's FY27 proposed budget would gut the agencies that fund and conduct crucial weather and climate work. And the cuts in this budget, if they're enacted, would shut down entire programs that Americans depend on for their weather and climate information. And as I was saying, it doesn't have to be this way. If you like what you see here, if you think that what you're seeing on your screen right now deserves to be protected, we ask you to use the link on your screen and contact your representatives, tell them to save our forecasts, and to vote no on these drastic cuts that are being proposed to weather and climate science. And also spread the word. We'd love to have more people here. We'd love to, bring your friends, post it on your Facebook, put it on your WhatsApp groups. Let's get our families, our friends here, and enjoy all this wonderful science together. So yeah, with that, I want to introduce our next speaker, who I'm really excited to share the screen with. This is Lily Dove. Lily is an assistant professor at Georgia Tech, where she studies biological and physical interactions in the ocean using observations and numerical models. And she's going to be talking about exploring our blue planet using underwater robots. So, Lily, well, #1 ocean stan, excited to have you here. Take it away.
Thanks, Andrew. I am very excited to be here too. I do have to warn everybody that I have fewer near-death experiences than Jeff did, but that's okay because we're going to talk about the ocean now, which I'm going to start a little war in the chat, hopefully, that ocean is the best fluid. Atmosphere, they just aren't as cool as us. So I have the honor of having an amazing job where I get to explore our blue planet and our oceans using underwater robots. And I want to talk to you about a very specific one of these robots today. But first, I want to talk to you a bit about my journey to get where I am now. So I grew up on the coast of the Atlantic in this small town called St. Augustine, Florida. And St. Augustine is famous for being the oldest continuously inhabited European settlement in the continental United States. And I just think that is a ridiculous title with a lot of qualifiers, but it is really special because this town was founded in 1565. And it's a pretty cool place to grow up. But as you can see right there where it is, there's a lot of weather impacts in this location. Impacts by hurricanes, you get stormy seas, you get storm surge. So there's a lot going on. My journey into science was really backed by the federal government. From the very time I decided to leave Florida, I got the opportunity to go to MIT for undergrad, where I studied Earth, atmospheric, and planetary science. I received Pell Grants from the Department of Education in order to attend college. And so Pell Grants are grants given to low-income students. You don't have to pay them back, but they help you, succeed. They are part of your financial aid package. And so the Department of Education helped me get my foot in the door in terms of becoming a scientist. After MIT, I decided to do my PhD, and I went over as far as I could to the other side of the country to Los Angeles, where I attended Caltech. And I had the honor of receiving a graduate fellowship from the National Science Foundation. Several other people have talked about how fellowships were really important for them because it allowed them to explore different directions. And that was also true for me. I got the opportunity to explore a lot of different topics and try things without the risk of losing funding. So after my PhD, I went to Brown University to do a postdoc, and I was funded by a fellowship through the National Oceanographic and Atmospheric Administration, which we also call NOAA. And so again, having this fellowship allowed me to become an independent scientist and to be responsible to myself and to my own science. And now I have the great joy and honor to be a faculty member at Georgia Tech. So I've come kind of back to home, back to the South, where I know best, and working with amazing students here at GT. So I think what maybe stands out from this whole journey, kind of around the states, is that the federal government has been my scientific colleague my entire career. From my first day at college, through grad school, through my postdoc, and now I have been lucky to receive federal assistance and also worked hard to write grants that have been funded. Because my ideas have been confirmed by my peers to be among the best and should be funded. And so I'm really grateful to be an American scientist and to have the federal government as my colleague. So before any of this even started, I mentioned I grew up in St. Augustine. And so this is a picture of the beach where I grew up. And you can kind of see maybe from this picture, how somebody like me who was raised here would get interested in ocean sciences. And so it's kind of just a beautiful place, but this is a nice and calm day. You can get really choppy seas, and you can get really dark and stormy seas as well. And I was really interested in the fact that you had all of this energy within the ocean and exchanging with the atmosphere and understanding how those processes worked. And so that was one of the guiding questions that led my journey, my scientific journey so far. And so I learned in college about ocean temperature rise, which is correlated with atmospheric temperature rise and global warming. So on the x-axis here is time in years. So I've also put some important highlight years on here to orient you. And on the y-axis is temperature anomaly. So when I say temperature anomaly, this is not the absolute temperature, like the temperature you get if you looked at a thermometer. It's the anomaly of the temperature, so meaning you're subtracting out a value. And here we're subtracting out the value of temperature in 1880. And so we're looking at how temperature has changed in the ocean since 1880 or so. So you can see that there was this dip here and this rise, and the classic pattern we kind of see in climate data and climate time series is this rise in temperature. And so now we have the ocean has warmed approximately 0.76 degrees Fahrenheit, which if you're more used to thinking about, or degrees Celsius, which if you're more used to thinking about Fahrenheit is about 2 degrees Fahrenheit. And so I got really interested the first time I saw one of those plots about how do we actually make measurements of the ocean. We have these data back from 1880, and these data through today. Are the methods we're using the same? Like, how accurate are these measurements? And so just to answer that question briefly is that we can and often do measure properties aboard ships. And this is one of my favorite parts of my job, is going out to sea and making measurements of all different kinds about the ocean. And so I put a collection of pictures here, including down here at the bottom, the RVIB, Nathaniel B. Palmer, which until recently was the US Antarctic icebreaker. This is a collection of people aboard a small boat, a Zodiac ship, going in to collect some data about sea ice. This is a group of Coast Guard folks who are deploying an ocean instrument here. This is me. I'm collecting a sample to measure salinity. And then this is a group of people from up in the Arctic. You can tell that sometimes it gets really cold up there. And so we do measure properties aboard ships. But you can tell there's an ellipses there. So I'm about to say something else, which is that sometimes making measurements aboard ships can be a bit precarious. And so this is a video from the Sir David Attenborough, which is the British Antarctic Survey's icebreaker. And they are kind of headed into a storm in the Southern Ocean. And so you can tell that they are inside taking this video, but that, making these measurements aboard ships is not always easy, and it's not always safe to do. So because of that, scientists in the last 30 years or so, 40 years, have taken the step forward in kind of automating some of the processes that we use to make measurements of the ocean. And so since the 90s, we've been taking the vital signs of the ocean with autonomous instruments called floats. And so I like to call floats 90s kids. I'm also a 90s kid. And so I'm going to show some schematics here of these floats, and I'll show real pictures later on. But we start with what we call these core Argo floats. And so this is an instrument that measures temperature and salinity in the ocean. More recently, in the 2010s, we realized we're doing a great job measuring temperature and salinity of the ocean. What if we measured other things as well, such as biological and chemical properties of the ocean, like nutrients and oxygen? And in addition, we decided to not only broaden our range of things that we could measure, but also go deeper in the water column. So hence the introduction of deep Argo, which measures properties of the ocean below 2,000 meters. And so just to put that in perspective, the deepest point of the ocean is about 6,000 meters deep, about 6 kilometers, which is, on the order of 4 miles deep. And most of these floats only measure the upper 2,000 meters. And so if you only look at the upper 2,000 meters, you're only telling 1/3 of the story. And so deep Argo is really necessary for us to tell the rest of the story about what's happening in the ocean. So I promised I'd show an actual picture of a float. This is me and my colleague Bailey, and we are with a biogeochemical Argo float here. And so there are a couple of key points I want to point out about this. First is there's a bunch of sensors up here at the top of the float. And so there are these sensors that measure temperature, salinity, oxygen, other properties of the ocean, things that are really important for us to know. In addition, there's a transmitter, and this allows floats to be able to make a satellite connection. And I'll talk more about that in a minute. The main body of the float, the majority of this hull, actually contains a battery, which is pretty heavy duty, and as well as what we call a buoyancy bladder. And so that buoyancy bladder is what allows a float to move up and down in the water column. And finally, you'll see here at the very bottom, there are more sensors. This one in particular is used to detect biological signatures, such as chlorophyll in the ocean. So the actual lifetime of a float looks something like this. First, we deploy the float off the side of the ship. We try to do it pretty gently, but these floats are pretty sturdy. They're made to withstand a long time in the ocean. And so we try to be gentle with them, but they are pretty hardy. They then will sink in the water column to about 1,000 meters. That's what we call their drifting depth. That's where they kind of just hang out for a while. And they'll drift along with the currents for about 10 days. Then the float will sink to about 2,000 meters and then come back up to the surface. And on its way up to the surface, it's collecting data. It's collecting that temperature data, that salinity data, oxygen, chlorophyll, all of those fun, exciting data points that we are amped to look at. And the most exciting thing is that it doesn't just hold on to that data itself, it calls home. And so it's able to connect via satellite, which will then beam the data right back to us so we can look at it right away. And so this is a picture of us, definitely not staged, looking at data from the float as it sends it back to us right after we deployed it. That's always really exciting. It's good to know that it's happy and healthy. And this is a picture of me at home looking at float data as well. Our, oceanographers, we're people too. We have families and pets and friends who want to see us. Many of us would love to be out on the ocean all the time, but it's nice to be able to spend time at home and get the data back to you as well. So you can probably tell that I'm pretty amped about Argo. And you might be thinking to yourself, okay, she said this was a 90s technology. The oldest floats are kind of 90s era. Like, why am I still so excited about this? Aren't there other more exciting, more recent things that I could be talking about? The answer is yes, there are more recent things I could be talking about. But I think that I want to really hammer home how important and exciting Argo is, because in my eyes, Argo is an observation superhero. I hope you can tell I did not use AI for this. This is a proud Lily Dove creation. So the reason I say that is that Argo is the dominant source of globally distributed subsurface temperature and salinity observations. So what that means is that if you go and like look into like a data set of like all subsurface ocean observations, 9 out of 10 of those observations are going to be from Argo, at least in the current day. Historically, that's not true. It is true today. And of course, other instruments are still important. Buoys, moorings, shipborne data, animal-based data, other data are really important and key aspects of our ocean observation system. But Argo really has this like really important role in that it just is so good at getting really effective data and really high quality data. And I want to show kind of what that number means to you in a different way. So what I'm plotting here is a map of all temperature data collected by non-Argo sources between 1999 and 2025. And each of these dots represents a number of data points. And so 1 is represented by a black dot, 20 to 50 data points is represented by a red point. And you can see here that there's a bit of a discrepancy in where we have data from these like non-Argo sources. We have a lot of data near the coasts, especially in the Northern Hemisphere. But there are whole sections of the ocean. Look at here in the Pacific, in the Southern Ocean, in the South Atlantic, where we don't have even one data point in a given grid cell. So I'm now going to change this plot from being non-Argo sources to being just Argo. And I'm going to keep the color bar the same. I think that's pretty impressive. You go from having these areas, these data deserts, to being full of this pink and purple and red colors, which means we have multiple data points in one location, purely from Argo data. So you can see that there are definitely some points where it's like hard to collect data in the sea ice, marginal sea ice zone of the Southern Ocean, up in the Arctic. But we as a community are definitely working on that problem. So I mentioned for temperature and salinity that Argo isn't for the primary source of data nowadays. And that's also becoming true for what we call biogeochemical properties, such as oxygen, nitrate, and chlorophyll in the ocean. And so what's plotted here on the x-axis is time since 1970. And on the y-axis is total profile count, so number of vertical profiles in the ocean. And the different colors represent different methods of collecting that data. So you can see from the 70s to the 2000s or so that the predominant way of getting oxygen data in the ocean was from ship-based measurements. And now we are moving towards this era, and I would say even we've entered this era where Argo is the predominant source of this data, especially for oxygen and also growing for other data as well. So I'm clearly excited about this. I hope I've convinced you that Argo is an ocean observation superhero. But it's very valid if you're asking yourself, okay, how do we actually benefit from measuring the ocean? Why should I, as a person who famously doesn't live on the ocean, I famously live on land, care about collecting all this data in the ocean? So I'm hoping to give you 3 different reasons. And I'm going to frame them as a scientific reason, an operational reason, and also a societal reason. So scientifically, one use of Argo is that it is really good at detecting changes in the ocean because it collects so much data and has been in the water for such an extended period of time. We're now able to begin detecting changes. And one of those changes that we're able to see is deoxygenation of the ocean. So Argo is really good at detecting deoxygenation. And deoxygenation is something we care about because it has major impacts on marine ecosystems and marine organisms. So what's plotted over here on the left is the trend of oxygen in the global ocean. you can see that's overall blue, meaning that the ocean is overall losing oxygen. And that's primarily because warm water holds less oxygen than cold water. And you can see that there are some real hotspots of this deoxygenation too, especially up here in the North Pacific. And the reason we care about this deoxygenation, one of the big reasons, is that fish and other species need oxygen in order to survive. And so we're seeing that we are moving away from this state where we have a certain distribution of species at a given latitude. And those species are moving either northward in the northern hemisphere or southward in the southern hemisphere in order to stay at a region where they have the same amount of oxygen that they're used to using. And so Argo is giving us kind of the first clues to detect this deoxygenation, which then we can go on to use to make other discoveries about how the climate system and also marine systems are responding. An operational use of Argo harkens back to Dr. Masters' talk just before me about hurricanes. And so the National Hurricane Center and the US Navy both use Argo data to improve forecasts of hurricane intensity and also landfall. And so I put here a picture of Hurricane Ian, which made landfall in 2022. You can see it kind of encompassed the entirety of my home state, which it's a little terrifying to look at that projection, honestly. And the reason I chose Hurricane Ian, I could have chosen many, many other hurricanes, was because Hurricane Ian was the reason my hometown made the front page of the New York Times. And I wish it was for something, more positive. But this is actually the main street of my hometown. You can see that there's probably 2-3 feet of flood water coming in from the ocean, from the inlet onto the main street here. And you can also see how windy it was. And so Argo not only collects this data for interesting scientific reasons, but it allows us to make more accurate hurricane forecasts as well. Finally, one societal benefit of Argo, and this is maybe my favorite, and this isn't even about the data, but about connecting with students. So Argo is really charismatic because these floats are about my same height. I like to say they're about as blonde as I am. And we have each float is adopted by a different classroom. And so you may have seen on the previous picture of a float that there were drawings on that float. Each float is adopted by a class, and we draw the mascot and also the name of that school on the float. And to the extent possible, we go make visits to these classrooms in order to, educate students about ocean observations, ocean technology, and just generally about how amazing our planet is. So this is me talking to a classroom in South Colony High School. The students got the opportunity to see this demonstration float, which you can see isn't yellow, it's actually clear. And so they can see inside of the float. And then this is a collection of floats that I have decorated out at sea before deployment. So I framed this as scientific, operational, and societal, uses of Argo, but I think the real argument is that all of these intersect, and that Argo is really at the heart of all of these. And so I hope I've convinced you that Argo isn't just cool for science, but also cool for our society as well. So a question that might be you might be asking is, okay, this is cool. Clearly, it has demonstrated value. Why should I care about it specifically right now? And one reason is that Argo is an awesome example of US scientific leadership. And so what I'm plotting here is a map of all of the currently deployed Argo floats in the ocean. And they are colored by national contribution. So each different color is a different country. If you look at this, you can see, wow, what an amazing international program this is, right? All of these different countries contributing floats and contributing to this data. you'll also see that the dominant color on this is green, and that represents the United States. The US has contributed 50% of Argo floats operating now and also historically throughout Argo's lifetime. And so the US is really an awesome example of the US leading the way in science. And I think that's important to note because without the US contribution to this ocean observing system, our assessment of ocean conditions could be really, really off. And so let me walk you through what's being plotted here. So on the x-axis, this study investigated what would happen if you removed a certain percentage of data from your ocean observations. How accurate would your model be if you didn't input all of that like actual real data, which you assimilate into the model? And so on the x-axis here is the percentage of data that they removed from the training of their model. And on the y-axis is the error that they experienced. And so you can see here, generally, there's this kind of linear trend of percentage of data removed and error, which kind of we expect. If you remove more data, you're going to have less training and your model's more likely to be wrong. Each of these colors represents a different contribution by a different country. So you can see France, Japan, Germany contribute significant amounts to the ocean observing system. But if their data was removed, you wouldn't have much of a change of error. Meanwhile, the United States contributes about 50% of the data to ocean observing systems. And if it was removed, our error in our models would be massive. It would be really, really large. And so what that means is that the US has done a really good job of collecting a lot of data and also a lot of data in places where we don't already have data and that are really important for helping us lower our error. And so US leadership in Argo has been traditionally and historically steady, like it's been good due to steady investment. But maintaining that leadership kind of requires that renewed support. And so the US commitment to maintaining the Argo system, the funding that we need has increased, but the funding to actually make that happen has not. And that's been true across a lot of different political administrations. But it is additionally a major challenge now where we are experiencing times where we might not be going from a stagnant budget to a budget of zero, which would mean 0 new floats in the water. And so I want to encourage you to think about the fact that we have this amazing observing system of the ocean, and we really should fight to maintain it and fight to maintain this awesome resource that we have, not just for Americans, but for all of our international colleagues. So I want to conclude by saying that our healthy and safe society really depends on understanding our changing ocean. From hurricanes to the Coast Guard to understanding potentially harmful algal blooms and maintaining the biodiversity of coral reefs. All of these things contribute to our society, and we really want to understand them. And Argo moves the ocean from being this kind of unexplored, unseen frontier to being an observable and explainable system. And it's pretty amazing. And so I am really excited that I got the opportunity to share about Argo with you. I'm going to put this final image up here just to give us some peace in this time. Just look at the ocean and breathe in the salty air. And I'd love to answer any questions that you have about Argo, about ocean observations, or about anything else.
Awesome. Thanks so much, Dr. Dove. And although I may look like Andrew without glasses, we did have a bit of a hosting handoff in the middle of your talk. So I've taken over for Andrew.
That was an amazing talk. Thanks so much. And we have a bunch of awesome questions from the chat. I wanted to start with potentially the most wholesome comment that I've seen in the stream so far from David Steinauer. Said, "Hello, Lily, throwback to the Nice High School Robotics Club. How did your career path differ from what you expected / planned for in high school?"
Wow, this is so wholesome. Hi, David. It's so good to see you. Goodness, I do not have like a prepared answer here because I'm so thrown off in a good way. But let's just say I went to college not with a big plan in mind. I was like, I know I like math. I know I like physics. I know I like chemistry. I know I like biology. I am just going to go and figure it out from there. And being at MIT is a heck of a place to do that. And it was an amazing experience. And I learned pretty quickly that I liked all of those fields, but I liked applying them to something I cared about. And that's when I really began to reflect on the fact that, you know, I grew up in this amazing and dynamic place with the ocean right next to me and, you know, an amazing turbulent atmosphere. And so that really was what pushed me in the direction of looking at fluid dynamics and atmosphere and ocean research. And so, David, I would say that my career path differed in that I didn't have a career plan and I still don't.
Amazing. Just building nothing but community here at the Weather and Climate live stream. Okay, our next question is from Cosmo Conjurer, who's wondering, does oceanography also apply to the Great Lakes / have you worked with them, coming from someone who lives near one?
That is a fantastic question. And absolutely, a lot of oceanography definitely applies to the Great Lakes and also like other large lakes. There's a fine line between what you define as oceanography and what you define as limnology, which is the study of lakes. And there's way more in common than there is different. I have not personally worked at studying the Great Lakes, but I've worked with colleagues who have. And the main person I have worked with actually looks at sea ice in the Great Lakes and how its formation processes differ from sea ice formation in the Arctic.
Awesome. Okay, our next question is from Helmendorf, who is wondering, do these Argo floats capture only chemical data or also biological data?
Wonderful question. So they collect what we call generally biogeochemical data. And so that's a general catch-all term for everything bio, geo, and chemical. But the specific things that we measure are on a biogeochemical float are oxygen, nitrate, chlorophyll, fluorescence, and backscatter in the ocean. Backscatter is a good way to measure kind of the turbidity or kind of how much stuff or organic matter is in the ocean. And some are also able to measure what's called downwelling irradiance. And that's important because it tells you how much photosynthetically available radiation is around and available for biology to use. So yes, absolutely, we are measuring biological properties as well.
Awesome. Yeah, lots of big Argo fans in the chat.
That's my goal.
Okay, we've got another question from David, who's wondering, what about Argo's form factor / size is optimized, and how would it be, or I guess possible or impossible, to cut hardware costs in the age of cheap and small hardware?
It is a great question. And so a lot of Argo kind of is optimized for the fact that you, one, don't want to take up a lot of room on a ship. So ship time is really expensive. Shipping things to kind of ports in the middle of nowhere often is often expensive. And so you want to take up as little room as possible while also maximizing, how much lifetime you get out of a float. So I didn't mention this, but a typical float with recent improvements lives on the order of like 4 to 5 years in the ocean. And so it's collecting data every 10 years or every 10 days and sending that back to us. And will often live 5 years, maybe even 6 years. And so, yeah, you saw that most of them are kind of that like tube shape. A lot of that's because you want to like reduce space. It's also because that's kind of the shape that moves up and down in the water profile the most efficiently. If you had a lot of things poking off of it, that would really could add a lot of drag and actually even potentially mess up your measurements. In terms of cutting hardware costs, the actual most expensive things in a float aren't the body, it's mostly the sensors. And so there actually has been a lot of development in the private sector alongside the academic sphere in developing like small and less power hungry sensors for floats and for other ocean observations and measurements. And so definitely it's something on our mind of how do you cut costs while also maintaining the quality of data. And so we're always going back and forth on like, okay, we could use this cheaper sensor, but like what would that mean for our data quality? So you're always trying to ride that line.
Definitely a difficult optimization question. Okay, we're going to do one last question from Cambrian. I think Andrew might have answered this in the chat already, but I think it's important to go back over so everyone can hear it. Cambrian's wondering, does a warm ocean get more acidic?
It's a great question. So there are two kind of competing factors, two things going on here. The ocean is getting warmer because the atmosphere is warmer, and therefore the exchange between the ocean and atmosphere, the ocean takes up some of that heat and stores it. The reason the atmosphere is getting warmer is because of emissions of carbon dioxide and methane, among other greenhouse gases, into the atmosphere. The ocean also likes to take up carbon dioxide. And so, and that carbon dioxide is an acid. So when it dissolves in seawater, it dissolves into carbonic acid, or that's the form it takes. And that is actually what's leading to the changing acidity of the ocean. And so it's difficult to like decompose these two things. They're caused by the same thing, which is carbon emissions, but warming and acidification don't necessarily go hand in hand.
Awesome. Thanks so much, Dr. Dev. Really appreciate it.
Thank you, Shane. Thanks, everyone.
Have a good one. All right. Thanks, everyone in the chat, for the warm welcome. I want you, if you've been here since the start of the stream, a little bit over 4 hours ago, drop an emoji in the chat. We love people sticking around. We've got just a little bit under 46 hours left to go, so lots of fun left to be had. Yeah, we've got amazing speakers coming up. I'm super excited. But before they join us, I just want to take a little bit of time to remember why we're here. Weather and climate forecasts are so important. You know, whether you're picking out clothes to get dressed for the day, or if you're thinking about an upcoming El Nino, everyone deserves actionable weather and climate information. And the United States have been world leaders in weather and climate science for decades now. You know, from our unparalleled network of observations, you know, the Argo floats that we were just talking about, weather stations, satellites, weather balloons, to developing weather forecasts. The US has been on the forefront of this field. But this success was only possible because of decades of investment by the American public, and the current administration is really challenging these foundations that we have for our science. And one challenge that I really want to highlight is the political interference in research funding. That is a really big threat. Currently, last week, the Office of Management and Budget proposed rules that would let political appointees, rather than peer reviewers, make funding decisions for the science that's approved to be funded, which limits the type of science that can receive support if it doesn't align with the administration's goals, and it restricts how scientists can share their work with each other and the public. So we really need you, everyone watching the stream, to help us defend weather and climate science. Call or write your representatives at the link in the ticker below me, wclivestream.com/act. And these decisions are happening right now, and now is the time for us to make our voice heard. All right. So with that, just want to remind everyone that all speaker views are their own. And next up, we have Nadir Jeevanjee, who is a federal climate scientist speaking as a private citizen, and who's going to tell us all about Manabe's climate forecasts.
Great. Thank you, Shane. I assume everyone can hear me okay. So indeed, I want to tell you a story reaching back decades here about Manabe's climate forecasts. And I'll tell you about who Manabe was and exactly what these climate forecasts were. And they're sort of symbolized by these different images up here, which you'll get to know as the talk goes on. And the motivation here is that the forecasts I'm going to tell you about, I think, are shining examples of scientific prediction made decades ago and confirmed only in recent years. And for me, they're a big part of where my own confidence in climate science and climate modeling comes from. And I think especially at this time where the funding for science and the integrity of science is in doubt, I think it's important to turn back to this history and remind ourselves of what we've accomplished. And I'm actually going to talk to you about 5 very specific forecasts. You can count them on your hand. And I believe that these 5 forecasts should also be part of the mainstream narrative about climate science, that anyone who's interested in this subject, even just the interested layperson, should know what these are, because I think they are understandable, even to the non-scientists. And that's what I'm going to try and do here. So the story, and if you guys have been tuned in since Adam Sobel's talk, he hinted at this. The story of these climate forecasts actually has a common origin with weather forecasting, which started right here in Princeton, New Jersey, where I am, with polymath mathematician John von Neumann, who after the end of the Second World War at the Institute for Advanced Study in Princeton, built one of the first digital computers in the basement of this building. And he had a variety of projects in mind, but one of them was digital weather forecasting, electronic weather forecasting. And so they spent several years putting together using these simplified equations that Adam mentioned, put them on one of these early computers. This isn't even showing half of the computer. It takes up a whole room, and successfully made the first weather forecast based on the laws of physics. And that technology quickly got transferred to the National Weather Service and became the weather forecast that we all get on our phone today. But John von Neumann was a genius and a polymath, and so he didn't want to stop there. And he realized, well, if we have these atmospheric models on the computer that can simulate the motion of the atmosphere, we don't just have to run them for a few days to predict the weather. We could keep running them for days, weeks, months, and years and get the long-term statistics of weather around the globe. That's climate. But he also knew that to do that, you'd need to add elements to the model. You'd have to have the sunlight coming in and the infrared radiation going out and the clouds and the hydrological cycle. So he knew that performing the so-called infinite forecast would take some work. So he wrote up a 7-page proposal, which you see here in the center, submitted to the federal government, got it approved. And that is what led to the Geophysical Fluid Dynamics Laboratory, now a part of NOAA, housed here in Princeton, New Jersey. And we heard earlier from Jen K about NCAR and how NCAR is under threat. And you could think of GFDL and NCAR as sort of sister laboratories. They came online around the same time. Maybe GFDL was a little bit earlier. And both just played critical roles in early climate science and in climate science to the present day. And the founding director of GFDL was a man named Joe Smagorinsky, who had actually worked for von Neumann at the Institute and then became GFDL's first director. And while this was very much team science, there were 2 critically important leaders, scientific leaders in this effort, and they're also pictured here in the lower right. And they are oceanographer Kirk Bryan, seated, and then Syukuro Suki Manabe, who's going to be one of our main characters, standing here in the center. And as I mentioned, to simulate the long-term statistics of weather or climate, you have to get Earth's energy balance right. Otherwise, the Earth will be cooling down or heating up unrealistically. So you have to model the sunlight coming in, you have to model the infrared radiation going out. And of course, that infrared radiation going out is what's intercepted by greenhouse gas molecules. That interception is the greenhouse effect. And so you have to include the greenhouse effect in these calculations. And so the first thing Manabe had to do was build a radiation model, including the greenhouse effect from carbon dioxide, from water vapor, even ozone, to get the stratosphere right. And I'll have more to say about that. So Suki builds this radiation model, but then he wants to test it. And testing it by putting it in the full global weather model was going to be too expensive. And so he wanted to do was create a little mini model, a test case that he could use to kind of exercise this radiation code that he built. And so he added a very simple model of convection of thunderstorms and mid-latitude weather systems. And he created a very simplified model that had a simple representation of convection and was globally averaged. He averaged across all longitudes and all latitudes to get a one-dimensional model where the only dimension is in the vertical height. And he called this his radiative convective equilibrium model. And so what that means is that it's got these radiative processes of sunlight coming in, infrared radiation in the red hours going up, being intercepted by greenhouse gas molecules, but eventually being released to space by these same greenhouse gas molecules. But then you also need this convective process to get the energy from the surface all the way kind of aloft, up high in the atmosphere, so that the greenhouse gas molecules can then send that energy to space. And convection is what does that, and it takes both heat and water vapor from the surface, and that water vapor is evaporated off the surface by the incoming sunlight, and it lofts that air high up in the atmosphere where it expands and cools, and that water vapor then condenses and actually releases the heat that the sun put in at the surface. And so every time a raindrop condenses, it actually releases a little bit of heat, and it's that heat that then these greenhouse gas molecules in the upper atmosphere release to space. So Manabe understood this picture and put it all into his one-dimensional model. And so this was the result. And so you can just focus on the black curve here for now. This is temperature on the horizontal axis, height on the vertical axis. And in the lower atmosphere, the troposphere, where you have weather, you have convection, you have storms, the temperature decreases with height. And you would know that from flying in a plane or hiking up a mountain. And the slope of this curve in the troposphere is actually set just by the thermodynamics of convection. And then in the upper atmosphere, in the stratosphere, the temperatures actually turn around and start to increase with height. And that's actually because of ultraviolet absorption by ozone. So Manabe ran these calculations, got this black curve initially, which was sort of his baseline, and he compared it to the global mean, and it looked good. So this was quite encouraging. And that gave him some confidence in the radiation model that he built. But Suki, and we've been talking in this live stream about how there's not such a fine line or such a stark line between art and science, and that scientists are also inspired in the same way that artists were. And I think that was very much true for Suki. And he just had this playful curiosity. So once he built this model, he wanted to play with it. And there were these different inputs into the model, like the CO2 concentration. And so he asked himself, what if I play with the CO2 concentration? What if I double it or halve it? And so that's what he did. He ran additional experiments. These are these other colors where, say, he doubled the CO2 concentration and got the red curve. And if you look down here in the lower right, you see that the temperature of the red curve in the lower atmosphere is warmer. And that was his first big result. And other people had explored this in other more simplified models using pencil and paper. But this was the first kind of calculation that was more comprehensive, that included all the factors it needed to, the convection, the different greenhouse gases, that it was really trustworthy, and the results would stand the test of time. And those results were published in this paper in 1967. And he found that when he doubled CO2, that the temperature increased by about 3 Celsius, something like 5 to 6 Fahrenheit. And it turns out that that number is still our best estimate for how much the Earth will warm due to a doubling of CO2. And in fact, if we look at the present day, we're about halfway to a doubling. And the amount of warming that we've had is about half of this, maybe a little less, of this warming that Manabe predicted. And there's a lot of other factors that go into the warming that we have now, heat uptake by the ocean, other greenhouse gases. But the larger point is that Manabe got global warming about right. So that was his first forecast. But the other striking thing about this figure is what's happening in the upper atmosphere, in the stratosphere. And here, when he doubled CO2, the red curve, the opposite thing happened, and the stratosphere actually cooled. And this was a surprise, but Suki had kind of already studied the stratosphere a little bit, and he trusted his model of radiation up there. And so he had some confidence that maybe this would be, something that we would see. And it turns out that that confidence was well justified. And over the satellite era, starting in, say, the late 70s, early 80s, we've observed the stratosphere. And here's a plot from a very recent paper showing temperature measurements from satellites in the upper stratosphere, but about 45 kilometers in height. And you just see a steady decrease in temperature over the decades. The observations are in blue, and then climate models are in black. And you see both excellent agreement and a strong downward trend. And if you actually do the math on this trend, you find that the magnitude of the trend is just in line with what Suki predicted. And if you're able to stay up late tonight, there's going to be a great talk by a young scientist explaining this trend, why CO2 cools the stratosphere, and why it has the magnitude that it does, using just chalkboard physics. All right, so those are the first two forecasts, but Manabe is just getting warmed up here, right? I mean, that 1D model was his warm-up model. What he and his collaborators were really aiming towards was a full comprehensive global simulation of atmosphere and ocean. But that took decades to come to fruition. And I'll say here that, consistent federal funding was key to this, and that they were all federal employees at the GFDL, where I also work. And so another kind of halfway point along the way of model development was this quasi-global model. And the domain of the model is pictured here. And again, to kind of save computational resources, they only modeled about 120 degrees of the globe. So they didn't go the full 360 around. And what's pictured here is actually only the northern hemisphere, from the equator up until not quite the North Pole. And there's a very artificial distribution of continents. It's just the western half is land and the eastern half is ocean. And this ocean isn't even really a proper ocean. It doesn't have the full depth and it doesn't circulate, but it has the thermodynamic properties of water. So in many ways, this is kind of an idealized or maybe even artificial model. But the thing that it did do was that it simulated the circulation and flow of the atmosphere, which the 1D model didn't do. And it also, it's not shown here, but it also modeled the effects of snow and ice and the reflectivity and reflecting sunlight and changing the energy balance of the planet. And so this was now a model where Manabe and collaborators could, again, run global warming experiments. And this led to the third forecast. So the result of these experiments are here. What's shown here is the temperature difference when they doubled CO2 as a function of height in the vertical and now latitude in the horizontal. And there's a few things to notice. One, in the upper part of this plot is the stratosphere and the shading. And if you look closely, you can see the shading denotes negative numbers. Again, the stratosphere cooled. And this is part of where these early forecasts really turned into confident predictions, because we tended to see the same results again and again in simulations. There was consistency. So he saw, Manabe and collaborators saw stratosphere cooling again, but then they saw a new feature if you look in the lower left of the plot. And here it's not shaded, it's actually hatched. And something different is going on if you kind of peer closely. The numbers here are positive and very large. And so it turns out that up here in the Arctic, the high latitudes, the warming is enhanced. It's much larger than over the rest of the globe by about a factor of 3. And if you then look at observations that have come in since Manabe published these results over the last 40 years, that's exactly what you see, is warming that is most enhanced over the Arctic. And these are observations from surface temperature measurements from weather stations. Okay, so this is the ground truth right here. And in fact, there's been papers published since, and even just in the last couple of years, that have assessed, the degree of this amplification, and again found it to be about a factor of 3. And so Manabe was right on, both in predicting this kind of generally, but also in terms of the numbers that they were finding. And this Arctic amplification has real consequences that we can see. And one of the most dramatic and notable is the decline in sea ice. And so if you look at in this right-hand plot, the light blue curve shows the percentage change in the sea ice area in September, when the sea ice is at its minimum after it's melted all summer long. And you see that just over the satellite period, from 1979 onwards, we've had a decline of something like 40%. Very noticeable. And this has implications, geopolitical implications. That melting ice opens up routes for maritime navigation for commercial and military purposes. The fabled Northwest Passages are opening up. And if you're wondering why, our country's been so interested in Greenland lately, it's because they know this is true and they're trying to get ready for it. All right, so now we're ready for the final phase of Manabe's modeling with collaborators, where they make a fully global model and they couple it to the ocean. And of course, the modeling the ocean is a whole separate endeavor. And that's what Kirk Bryan, pictured here on the left, he was the oceanographer who led the development of the ocean model. And what we're talking about here is the world's first model of the full world ocean, full depth, thousands to tens of thousands of feet deep in some places, covering the whole globe. And then coupling that to the atmospheric model that Manabe and Smagorinsky had been working on. And they started collaborating on this in the late 60s. By the mid 70s, they kind of had a first working model with a, very coarse, but, kind of realistic looking geometry. With this first version of the model, they weren't yet ready to run global warming experiments. They were just exploring how the ocean atmosphere behaved when they were coupled to each other. What kind of interactions did you get? How did the model behave? And so there's lots of work to do in working out the kinks of coupled ocean atmosphere models. But after 10 years or so of this, they were ready to run global warming experiments, which finally came to fruition in the late 80s and early 90s. And you're already getting a sense of just the long timescales of this effort that, again, was only made possible by stable, committed federal funding to these efforts. And what I'm showing you here now is the temperature change in the model as a function of longitude and latitude. After a gradual doubling of CO2, so they slowly ramped up the CO2 until it doubled, and they look at the temperature change. And so what do we see here? Well, if we look in the Arctic, we see the shading indicating larger numbers, and maybe you can see some of the numbers. And so you again see Arctic amplification. So again, these phenomena are repeating themselves. Now you see something new. Look at these land areas. The warming is actually enhanced over land relative to the ocean. So we have a land-ocean warming contrast. And again, if I pull up those same observations that we're looking at before, you can see that again in the observations. Look over South America or Africa or Australia, and you can see that the warming is enhanced over land relative to the ocean. And that matters. We live on land, right? And so if the average temperatures go up by a degree or two, then over land, we're talking about maybe 3 degrees of change, because it turns out that the land warms more than the ocean by about a factor of 1.5. And this is even easier to see if you just average the temperatures over all the land, average the temperatures over all of the ocean, and then plot these global averages as a function of time. And that's what's shown here, starting from 1850 and going till about the present day. And you can just see these land temperatures in orange just warming up faster than the ocean and kind of overtaking the ocean warming. And again, careful studies of both models and observations kind of verify that in both models and observations, this enhancement ratio is about a factor of 1.6, and it's consistent between the observations and the models. And this paper that I'm citing was only published in 2018. So again, decades, not only decades to develop the models, but then even more decades to wait for the climate to actually change and then confirm what the models predicted so long ago. All right, so this brings us to our 5th and final forecast. And for that, we're going to focus on this region of the globe, a region that not many folks think about. This is the Southern Ocean. So this is this vast body of water that encircles Antarctica. There's winds just whipping around this ocean west to east, unimpeded by any friction with land masses. And these strong atmospheric winds then draw strong ocean currents. And those ocean currents then interact with the rotation of the Earth and then draw up deep waters from the abyss, thousands of meters down. And those abyssal waters are very cold, and they haven't experienced global warming yet. So it turns out it's very hard to warm this part of the ocean because you're continuously drawing up these abyssal waters that haven't seen a warmer atmosphere yet. And so that's what the models were showing, is sort of suppressed warming or delayed warming over the Southern Ocean. And yet again, if I turn to the same map of observations and I focus your attention on the Southern Ocean, that's what we see. Delayed or muted warming or even cooling over the Southern Ocean. And here's just a cartoon from NOAA, actually. Again, describing how these surface winds then push water offshore and then draw up deep water from the abyss. So those are Manabe's 5 forecasts. Count them: global warming, stratospheric cooling, Arctic amplification, land-ocean warming contrast, and delayed Southern Ocean warming. Predicted decades ago, over years and years of model development, and verified in many cases, and all verified in many cases just in recent years. So to me, I hope this strikes you as remarkable. It strikes me as remarkable and as a remarkable example of scientific prediction. It's almost a Halley's Comet for climate science, predicting something decades out and then finding these predictions to come true. And so you'll be reassured to know that these contributions were duly recognized and that Manabe and other climate scientists were honored with the Nobel Prize in Physics in 2021. You'll also be happy to know that Manabe is still alive and well. He's in a retirement home here in Princeton, and I've had the opportunity to catch up with him recently as I was kind of digging into his work and his legacy, and that's been a real privilege. And just to close here, what is the takeaway from all this? For me, what right now is it's a fraught time in climate science and for climate scientists. The subject is controversial, and it's been controversial for a long time. It's particularly controversial now. And there are skeptics out there of the utility of climate science, of how much confidence we can have in climate science, of whether these models, which are complicated, right? It took Manabe and Brian decades to develop them, and we're still busy developing them at GFDL. And there's skepticism about how much these models can tell us. And the models aren't perfect, and there's lots still to improve about them. And skepticism in general is part of science, right? We have to be skeptical of our own results to stress test them, right? Manabe built his 1D model because he wanted to be sure that he'd gotten the radiation right. So skepticism is a natural part of science. It's an essential part of science. But sometimes some of the skepticism that we hear today, it's not always well-informed. It doesn't always know the history or all the facts. And so if you encounter that kind of skepticism today that doesn't know about these 5 forecasts, then I hope you'll share the story with these people. And, and if there's persistent skepticism, you can just tell them to talk to the hand and count the 5 forecasts that were made decades ago and have proven true. So with that, I'll leave it there, and I'm happy to take your questions.
Awesome. Cosmo was wondering with weather and climate science, or did
Yeah, I'm having a little trouble hearing you, Shane.
Oh, sorry.
But I can read the question there. Did I start off with weather and climate science, or did I have another focus before this? Boy, is that question a plant? I had a few lives before climate science. Actually, if you guys caught Adam's talk, and he talked about having musical aspirations before turning to climate science. I was also a professional musician. I played in several bands. I toured. And so that was a whole previous life. And so I think also for me, as for others who've spoken, science and art don't feel all that dissimilar. And it similarly engages a creative part of my mind. And then I actually went to graduate school in physics, and I studied theoretical physics and Einstein's theory of relativity and quantum field theory. And, just got way deep into these really theoretical subjects, and I loved it. But eventually found it to be a bit esoteric and wanted to do something more down to earth. And I actually was a teaching assistant for a course at Berkeley that was all about the physics of renewable energy and science. And that showed me that that the science of the atmosphere, of the greenhouse effect, of cloud formation was actually all the same physics, the thermodynamics and radiative transfer and quantum mechanics that I'd already learned and knew and loved. And so once I realized that, then I thought, well, all right, great. Let's take this physics and apply it to front page problems. And so I switched to climate science mid PhD, and that's been my track ever since.
How's my audio now? Is it a little bit better?
Yes, sounds good to me.
Okay, awesome. Well, as a fellow UC Berkeley alum, I think I'm obligated to say go Bears.
There you go. All right.
Love that. Looks like our friend Adam Sobel had a follow-up question. Tell them about writing the group theory textbook on the tour bus.
I mean, I could do that. Well, all right. I'll say briefly. Yeah, being in a touring rock band is super, super fun. You're driving to another country with like your best friends, but you're only really like, you know, being a musician for 3 or 4 hours a day when you're on stage and you're at the nightclub or whatever. And the rest of the time you're killing time in town or after sound check, or you're riding around in a van. And one thing I learned about myself is that I just need intellectual stimulation. And I did some of this while on break. I did some of my touring while on a break from grad school, and I had an idea for a textbook. And so one day I was sufficiently bored while, you know, on a 3-day break in Portland that I just started writing it, and continued to do that and eventually published it. And so the book is an introduction to tensors and group theory for physicists. And, you know, Google it and check it out if you are interested.
For some light reading.
Yes, exactly.
Okay, let's pivot back to Manabe now. Gray 9698 is wondering, what was the justification for the simplification in the second model, location, distribution, lat lon, etc.?
The second model, I guess he means the one where, and are my slides still up?
Looks like they're down, but yeah, they're there.
Okay, so maybe I can go to what I think he's talking about. We're talking about this one. Is that what we think?
I would assume so.
Yeah. Okay.
Phase 2.
Yeah, that's a great question. I don't know if justification is the right word. I mean, Manabe and Brian and collaborators, they were just pioneers, right? I mean, at this point, this was, you know, terra incognita, so to speak. And so they're just trying to figure out, like, how could they stepwise add more and more realism, but really do it a step at a time, without making things like so complicated all in one fell swoop that A, the computers couldn't handle it, and B, they wouldn't understand what was going on in their model. So there's actually a beautiful paragraph in this paper where he includes these caveats, and he says, you know, this model's so idealized, it has all these artificial things. We're just kind of trying to probe the basic dynamics of how the atmosphere flows and how that flow and how the heat transport might change under global warming. And so you should just think of these conclusions as preliminary. So, you know, in these original papers, Manabe wasn't coming on strong and making definitive predictions. It turned out that the phenomena that he saw, like the stratospheric cooling, like the Arctic amplification, they kept seeing in subsequent versions of the model. And so by the time, you know, a few model generations had passed, these initial results kind of became forecasts, because we just thought, boy, every time we run a model, whether it's simplified like this or more comprehensive like the later ones, we see this stratospheric cooling, we see this Arctic amplification. So we're really expecting to see this when global warming becomes a reality. So I hope that answers your question.
Great. We have a question from Cambrian. Which is your favorite model? I don't know. Does one come off as particularly elegant?
Yeah, you know, so I personally have actually done work following up on the 1D radiative convective model, because it really, and I wrote a whole article about it and what was particularly elegant about it. In fact, we used the word elegant in the article that we wrote. It's called Manabe's radiative convective equilibrium. Adam Sobel mentioned it. And yes, that model really allows one to focus on the greenhouse effect, because that's the main thing going on there. The convection is so simplified, you wouldn't study it. It's kind of just specifying the slope of the temperature profile. but all the greenhouse gas radiation is in there. And so when I was a postdoc in Princeton, I actually did a lot of work kind of almost elaborating on Manabe's 1D calculations and showing, why does the presence of water vapor have such a big impact? And how can we write down on a chalkboard the effect of doubling CO2? And it was basically 1D models like Manabe's that I used to really kind of delve into those questions.
Gotcha. One thing that I was wondering that wasn't in the chat was about the lag time to verify these forecasts. Do you think Manabe predicted a similar amount of time would pass before these forecasts would be shown in observations?
That's a great question. I don't know that he's on the record about them, but I don't think he would have been surprised because, I think it was well understood that there was a signal to noise problem there, that there's internal variability and just the climate system is noisy and you have to wait for the signal to get strong enough. I'll just mention one particular story that I think is pretty phenomenal. But for instance, this verification of stratospheric cooling was only published in 2023. Why was that? Well, it turns out that the satellite data from the upper stratosphere, there's a lot of questions about it and inconsistencies, and it took them a long time to sort those out. We had data from lower down in the stratosphere, the mid and lower stratosphere. We've had that data for decades, or for maybe 10, 20 years now. But you don't see as strong of a cooling signal here for a couple of reasons, one of which is that in the lower stratosphere, the cooling from CO2 is then confounded with cooling from ozone loss and then heating from ozone recovery. And all of that is happening right during the satellite period. I mean, the ozone hole was discovered in 85 and then Montreal Protocol, and you don't have recovery until really starting in 2000. And so you've got this just complicated climate system. And so getting the data that you need in the part of the atmosphere that you need it and a long enough record and sorting out all the technical issues, in addition to just the pure signal to noise problem, can really take a long time. So yeah, there's kind of neat stories associated with each of these verifications.
Gotcha. Yeah, the short observational interval is definitely playing a role there. We have another question from JLee2733. In the slab ocean model, I assume there were no sea ice or albedo effects modeled. If not, what was responsible for the enhanced Arctic warming?
Fabulous question. So in fact, there were albedo effects modeled. There was no explicit simulation of sea ice per se, but when the temperature dropped below, I forget if it was actually freezing or a little bit colder, the albedo both over land and sea changed and became more reflective. So it was a very crude representation of the climate impacts of sea ice, and very crude. So that was one factor. The other factor that appears to play a dominant role is the fact that as you warm, you get a sort of enhanced accelerated transport of moisture from the lower latitudes to the higher latitudes via the usual mid-latitude storms that we see, say, in the Northeast where I am. And these storms, part of what they do, their role in the climate is to transport heat from the equator to the pole. And in a warmer climate, they're able to do that more effectively because there's more moisture in the atmosphere. And that's kind of one of the main sources of the heat that gets transported. So the two main ingredients in this Arctic amplification that you see here are the ice albedo feedback, which was crudely incorporated, and enhanced poleward heat transport in a warmer climate because of additional water vapor. And so the two essential ingredients for Arctic amplification turned out to be there. I don't know that, that we could have predicted at the time before running the simulations that would have given Arctic amplification. But looking back now, it does make sense.
Awesome. Okay, I think we have time for one more question. This one is from Cosmo, who is wondering, all this Arctic talk has me thinking of the polar highs. Have those been affected at all? Correct me if I'm wrong, but I think they apply to these models as well.
I guess I'm not, I wonder if this is a question, this is a little bit outside my bailiwick, but I wonder if this is a question related to the polar vortex. I'm assuming that's maybe what he means by polar highs. I don't know that I'm the best person to answer this question. Obviously, the polar vortex and its sort of quote unquote breakdown is a big part of cold snaps and extreme weather that we see. And I think the impacts of global warming on that, and certainly on whether on the incidence or frequency of cold snaps, is still very much a subject of research. I don't think there's necessarily consensus points of view, or if there are, I'm not well versed in them enough to say them here.
Gotcha. Awesome. Well, thank you so much, Dr. Jeevanjee. That was an amazing talk. Really appreciate it.
Thank you for having me. Thank you guys for doing this. Take care. Good night, everybody.
Have a good one. All right. Still going strong, everyone in the chat. Love to see it. As we move into night here. I'm on the East Coast of the US. Everyone I'm sure is experiencing this at different times, but for me, we're moving into prime time right now. We've had so many great talks, and I'm super excited for the talks we still have coming up. We're just wrapping up hour 5. So we're looking at 45 hours left of the live stream. And before we continue, again, I just want to take some time to remind us why we're all here. Weather and climate forecasts are super important. Everyone, whether they're a scientist or someone who is checking the weather in the morning on their phone, deserves actionable weather and climate information. And US scientists have been doing an amazing job at providing this information for decades on decades. But this success was possible because of decades of investment by the American public. And now that investment system is being challenged by the current administration. And there have been a couple of threads that we've been talking about throughout the stream. And one that I want to continue to highlight is the National Center for Atmospheric Research and the current attempt to dismantle NCAR, which is such a pillar, an essential part of weather and climate research. I know so many people that have worked at NCAR, are hoping to work at NCAR, are currently at NCAR. And this attempt to dismantle it and disband it is not because of any scientific reason, but because NCAR's climate research doesn't align with the political priorities of the current administration. We really need you, the public, to help us defend NCAR and protect it from being dismantled. Use the link below me, wclivestream.com/act, to call or write your representatives and tell them to protect NCAR. Again, these decisions are happening as we speak. It's really important that we act on this. Okay. Again, just want to remind everyone that all speaker views are their own. And I'm super excited to introduce our next speaker, Abby Swan, who is a professor of atmospheric and climate science and a professor of biology, 2 for 2. And Dr. Swan is going to tell us all about why plants matter for science.
Hi, can everyone hear me all right?
You sound great.
Great, thanks. I'm so excited to be here. Thanks for doing this. Thanks for having me. I'm going to talk about why plants matter for climate. So we just heard a great talk from Nadir about the atmosphere and the ocean and the Earth system in general, and I'm going to add land. And we're going to talk about why land matters in the climate system. I'll try to mention lots of collaborators along the way and all the ways that we've received federal funding to do this work to understand how our Earth system works. So this image in the background here is a satellite image of greenness, and it is showing us how plants are acting on the land surface. And what I like about this image is it shows us how much plants care about climate. You can just see that in dry places like the Sahara, there's not a lot of green plants. And in wet, warm places where plants grow really well, like the tropical forests, you can see it's really green. It's also northern hemisphere summer, so it's green in the northern high latitudes. And this image also shows the scale at which I'm thinking about plants and how they work in the climate system, is those plants acting globally in this system. and we're kind of agnostic to exactly what kind of plant is in each place. We care about how those plants work. So I'm going to talk today not just about how plants care about climate, but also how climate cares about plants. So how is it that where these plants grow and how they work, how does it actually make our climate system work differently? And if you get one thing out of this, I hope you'll take away that the uncertainty in biology, it matters for climate. So that we need to know how biology is working, in particular how these plants are working, to understand why our climate is the way it is and how it will respond to change. And I'm going to tell you a little bit about the tools that I use for a lot of this work. So I use a variety of different types of simulation models to do this work, but a lot of it is with Earth system models. And these are like the modern day counterparts of the models that Manabe was building, that Nadir was just talking about. And mostly I use the community Earth system model. It's represented here by this diagram, basically showing that it's representing all the fluid flows in the atmosphere, in the land, processes, things happening in the ocean, the transport of heat, transport of water, and the existence of sea ice and even land ice. I wanted to point out that this community Earth system model is developed and supported by the National Center for Atmospheric Research, which is funded by the National Science Foundation. And this is an open source community tool. And so it's accessible really to a wide array of scientists, and even any person who would like to run it could try to do so, but it's really the most accessible of these types of modeling tools. And so university researchers can use this and ask all kinds of questions like I've been able to do. And that's just really critical for advancing science. Okay, so with these Earth system models, we can ask a lot of what if questions. You know, Manabe was asking questions like, what if the atmospheric carbon dioxide was higher than it is now, or than it has been in the recent past? We could also ask other kinds of what if questions. So there's a cartoon called What If, some folks might be familiar with. And in this cartoon, they use physics to try to answer ridiculous questions. But some of those ridiculous questions maybe aren't so different from the kinds of questions we could ask with an Earth system model, like this one: what would happen if the world had the land masses spread out the same way but rotated by an angle of 90 degrees. And the cartoonist goes on to figure out where the dry places would be, where the wet places would be, where the plants would go, where it would be hot, where it would be cold, and ends up with crocodiles in Lake Wobegon. But this is like a simulation we could actually do in an Earth system model if it were something that we wanted to know the answer to. And so I like to be able to ask questions about what if something happened differently on Earth, because we only have one Earth, and this is really the only way we can try to investigate that with a complicated physics thought experiment. So I'm going to talk about 3 science stories today. I'm going to talk about some fundamental ways in which plants influence climate. Then we'll talk about how plants respond to carbon dioxide, or CO2. And then we'll talk about biological uncertainty and how it impacts climate. All right, first up, fundamentals. This work is done in collaboration with Marisa Legou and Gordon Bonin, and we had funding from the National Science Foundation. So let's start with just the basic ways in which plants influence climate. There's going to be 3. First up is color. So the color of plants determines how much sunlight they absorb. Darker plants absorb more sunlight than lighter plants. That might seem obvious when you say it out loud, but it's really true. There's a variety of different like colors of leaves out in the, if you look outside, and that leads to absorbing a different amount of sunlight. So this is similar to change, or is the same as changing the albedo of the surface. It's not as drastic as changing from ice and snow to no ice and snow, but it makes a difference. It changes the amount of sunlight being absorbed. So in this picture here, we have a picture from boreal forest in Alaska, and we have bright trees in the background and dark trees in the foreground. Here's another picture from Alaska showing us that the albedo of those plants varies by plant type. And these plants are both part of the same ecosystem, and so we could get changes between the different types of plants living in an ecosystem, as well as changes in ecosystems, and that will change the amount of sunlight getting absorbed by the surface. Plants can also change water fluxes. And so evaporation returns water from the land surface back to the atmosphere. But it actually comes out, we think of it as 3 different sort of flavors of evaporation. We get evaporation directly from soil surfaces. We also get evaporation off of leaf surfaces. So if like water rains onto a leaf and ponds on the leaf, it will evaporate back into the atmosphere. And finally, there's an evaporation that comes through plants that we give a special name called transpiration. And that's the water that goes up from the soil, through the roots, through the plant, and back out into the atmosphere. And plants regulate this water flux. So they do that with these little valves called stomata. So on plant leaves are these little valves that can open and close. And the reason they have them is because plants need to get carbon dioxide out of the atmosphere in order to do photosynthesis. And that's how plants are going to get their energy. So they have to get carbon dioxide into the plant, which means they need to exchange gas with the atmosphere so they can open their little valves, get the carbon dioxide in, do photosynthesis. But while they do that, water escapes because it's a moist environment inside the plant. The air is usually drier. And so transpiration is that pathway of water that goes through the whole plant system and out through these stomata. And what's really interesting about this is that it ties together the biological functioning of the plant really tightly with the water fluxes that are happening. And that has a lot of implications for how plants are going to be able to impact climate. And that matters for not just setting how much water gets into the atmosphere, but what happens with that water and potentially how clouds form and how rain falls either nearby or far away. This is a series of satellite images from over the Amazon forest showing the beginning of the rainy season. And so we have a dark green image at the top. We have sort of small scale, little popcorny looking clouds in the middle, and then we have larger scale clouds at the bottom. And what we find is that plants are actually initiating the small scale cloud features at the beginning of the rainy season. They're initiating those clouds through the changes in the way energy and water are being exchanged with the atmosphere. So they can initiate the beginning of the rainy season a little bit sooner. And there's even observational evidence that suggests in places where there's been deforestation, the rainy season starts later. And this looks like a small scale image, but this happens over large areas. This next picture is showing you a bunch of a chunk of Brazil, and you've got the Amazon rainforest, or sorry, the Amazon River going through the middle of the image there. And you'll notice that there aren't any clouds over the river, but those clouds are all over the forest. And so forests are setting the way that this water flux is being exchanged with the atmosphere, and that has implications for clouds and for rain, as well as for the way energy and temperature are moving through the atmosphere. Our final way that plants influence climate is through carbon. This might be the one you're most familiar with if you've learned about this before, but plants are going to take carbon dioxide out of the atmosphere through photosynthesis, and they're going to return it through a process called respiration. So I mentioned photosynthesis is when plants are going to take CO2, they're going to break it apart, and they're going to turn it into sugar. That's how they're going to make their energy. They use sunlight to drive that process. But plants also use a bunch of that carbon that they create, the sugars that they create. They use some of it to build their tissues, to build new leaves, to build branches, to build wood, to build roots. And then they have to burn some of that sugar in order to maintain those tissues and build them. And so that creates respiration, or the return of carbon back to the atmosphere. The pieces of the plant also eventually die. The leaves fall off, the branches will break, and those fall to the ground and eventually are incorporated into soils. And microbial communities decompose all that dead detritus on the ground, and they also respire that carbon back into the atmosphere. So there's this movement of carbon out of the atmosphere into the plant through photosynthesis, and then back out through respiration. And these are really large exchanges of carbon. The difference between them is small. That's the amount the plants, are removing. That's relatively small, but the actual size of the total arrows is really big. And we can even see this in global records of carbon dioxide. So this is a plot showing the measurement of carbon dioxide in the atmosphere made at the Mauna Loa Observatory in Hawaii since 1958. It's sometimes called the Keeling curve. It's a really famous graph in climate science. And it's famous because it's got this big increase over time. We see that the carbon dioxide in the atmosphere just keeps going up and up and up. And it's going up because humans are emitting carbon dioxide into the atmosphere by burning fossil fuels and deforesting the land surface. It's not going up as much as the fossil fuels we've emitted, because both the land and the ocean are taking some of that extra carbon out. They're doing us a favor and removing some of that extra CO2. But the thing that I wanted to show you right now is actually this little red wiggle. So superimposed on this increasing line, we have this wiggle that goes up and down each year. And that is photosynthesis and respiration, or the breathing of the biosphere. Basically, in the summertime, plants are going to photosynthesize a lot. They're going to pull CO2 out of the atmosphere, and that line's going to start dropping. But then when the summer season ends, plants stop photosynthesizing as much and respiration continues, then the carbon dioxide is going to go back into the atmosphere. And so we get this annual cycle up and down of CO2 in the atmosphere. And you can see that it is large even on the scale of how much we've been changing CO2 in the atmosphere. We can also learn a lot actually just from this data about what is happening in a global average or even a hemispheric average to photosynthesis and respiration just by measuring the CO2 in the atmosphere. So those are our three main ways that the plants are influencing climate. We've got energy, particularly sunlight, we've got water, and we've got carbon. So I wanted to talk next about what changes in plants can do to climate. And we're going to focus here on the energy and the water parts and not on the carbon, but I love to think about that too. So far I've shown you that the plants can alter the sunlight being absorbed, they can alter the water fluxes, which turn out to also exchange energy. And so we can guess that changes in plants, where they are, how they're working, are going to change energy and water fluxes, and that's going to have impacts on climate. So I've been wanting to know this question for a long time and been working at it in different ways of trying to understand specific changes in plants and also general changes in plants. And so we're trying to look at how much do changes in plants change climate and why does that happen? And this is important because we want to understand, for example, in a future climate, we need to be able to understand what might change about plants and what the implications of that might be. So let's return back to our Earth system model, again, the community Earth system model. And we are going to look at what's inside of the land in this model. So these are going to be complicated diagrams. The point is just to see that there is a lot of stuff in there. So first we have our energy fluxes. Each of these arrows represents an energy flux that has to be represented. But we're also representing water in the middle and carbon on the right. And each of these arrows is going to have a bunch of equations associated with representing that process in the land model. So it turns out, in order to ask a simple question about how the climate system responds to changes in the land surface, it's a little bit complicated because there's so many interacting things going on land. And so we actually decided that using the complex land model was going to be hard for that. So we took some inspiration from Matsuko Manabe and early climate model experiments to make a very simple land and test how the atmosphere responds to changes in the surface, changes in the land surface. So this is a diagram from the Manabe and Bryan paper showing that they had land in a very early climate model. We made a simple land model that's very similar to that, but we plugged it into the modern day community Earth system model in place of that complicated model. And what that allows us to do is to make simple changes to the land surface and actually try to understand what's going on with the atmosphere responding to that. This was led by Marisa Legou here. So here's an experiment that we did with this, this simple land, is that we painted the land surface different colors. So just like our two trees that had different albedos or different colors, we're going to change the land surface albedo and we're going to figure out how it affects surface temperature. So we can think about, is the brighter plant going to lead to a hotter Earth surface, or is the darker plant going to lead to a hotter Earth surface? And this is the temperature difference. So as we make the surface darker by a specific amount of a fraction of the light that gets reflected, this is how much warmer our system gets. And you can see that these numbers are all positive, so it gets warmer when we make the surface darker. That makes some intuitive sense. But this is just the land surface. So this is just reconsidering, if we bring in more sunlight and it gets absorbed, how does the land surface respond? But we know that the atmosphere is also going to respond to the land surface. It can respond in a bunch of different ways. There's a local response of the atmosphere. Just if you heat it from below, it's going to re-radiate long wave radiation back down. Could change clouds, which could also change the amount of sunlight coming in. But we could change circulation. If we're starting to change larger areas of the land surface, that could create gradients in the atmosphere, which could alter sort of medium scale circulation or even really large scale circulation. And if we start changing the atmospheric circulation, then we can have effects on climate that are happening pretty far away from where we make changes in the land surface. And so this is again, the same figure we just looked at, where it gets warmer when we make the land surface darker. And now I'm going to add the atmosphere. I'm going to show you how that changes temperature. When we make the surface darker, the atmosphere can respond to that. What does it do to temperature? And it turns out we get a lot more increase in temperature when we also let the atmosphere respond. And the main idea of this is that this feedback from the atmosphere, or the fact that the atmosphere is a really important part of this system. We can't think about the temperature over land as just something we need to solve over land, even when we're changing things on the land surface. We have to be thinking about the whole coupled system together, because the temperature that we get is actually a function of the fact that the clouds changed, the incoming sunlight changed, and the circulation patterns changed. So the coupled part of this system is really important. So our first take-home point is that plants can impact climate by altering the exchange of water and energy. And these atmospheric feedbacks are really large. We have to include the atmosphere. Okay, moving on to plant responses to CO2. And this is more collaborators on this work, and we had some funding also from the Department of Energy as well as NSF. So I want to start by getting on the same page that temperatures on Earth are increasing because of greenhouse gases, because those gases trap heat and they make Earth warmer. And mostly it's due to CO2. These different colored lines are representing possible scenarios of the future, and the ones that have higher increases in temperature have more of these heat trapping gases in the atmosphere. And since a large part of it is due to CO2, it's important that we think about all the things that carbon dioxide is doing in the Earth system. This is the temperature that you get from increasing that CO2. So a more modern version of the increase in temperature that we saw in Nadir's talk just before this. And so when we double CO2, we get an increase in temperature, we get some more warming over land, and we get some more warming at high latitudes. But it's getting warmer everywhere is the main point. But the other things happen associated with carbon dioxide. And in particular, plants care about carbon dioxide independently of how they care about temperature. So if we come back to our tree, and we come back to the fact that the tree have these valves called stomata, and they open them in order to take carbon dioxide out of the atmosphere, and that's when they lose water. If we cut a cross section through this stomata, it looks like this, and these little stomata can open and close, and the carbon dioxide will diffuse in through the stomata into the inside of the leaf. And two things can happen when carbon dioxide changes. First, there can be a faster rate of the CO2 going into the plant, and that allows the plant to potentially deliver more carbon dioxide to the photosynthesis biochemistry. Or the plant might decide to lose less water because it can get plenty of CO2, and it might be able to close its stomata a little bit, which would lead to less water flux. So when CO2 increases, plants can lose less water, or they can photosynthesize more, which could allow them to grow more leaves. And we're going to lump these together and call them the physiological effects. So we've got our warming from the radiative effects of CO2, the fact that CO2 is a heat trapping gas that makes Earth warmer. And we've got the physiological effects of CO2, which are going to change photosynthesis and how stomata open and close and how plants grow leaves. But I've already told you that this plant physiological response might involve the plants closing their stomata, which alters their water flux. And it turns out that that change in the water flux also has a temperature impact. And it looks like this. So this is the temperature increase associated with the physiological effects only. And it looks much smaller than the radiative effect of the CO2, but it's actually still meaningful, where we get up to a degree of warming in some places. And I want to point out, I'm not the first person to point out that there's warming associated with these physiological responses. That also dates back to the mid-90s and a prediction that this would be the case. But this means that we have some amount of temperature increase that's actually occurring because of these plant processes, photosynthesis, stomatal responses, etc. So I'm going to show you the ratio between these two maps, basically how much of the physiological effect contributes to the total amount of warming due to carbon dioxide. And that map looks like this, and this was work by Claire Zarakis. And you can see that this green map is showing us something like 10, maybe up to 15 or 20% of all the warming associated with CO2 is happening in some places because of these physiological responses. And even over the ocean, and we see actually the biggest numbers over the ocean because we have a smaller amount of warming from the radiative effects, and we've got some the warmer temperatures that have been sort of blown out from over the land over the North Atlantic. But here we can just see this is a meaningful contribution. It's not the dominant factor by any means. If we average across the whole globe, across all of the models that were available to this, we get something like an 8% of the warming associated with CO2 is due to these plant physiological responses. But it's larger in some models, and you can see it's also larger in some places. So plant responses are having an impact on climate. But the thing I actually want you to think about most here is that these plant responses are highly uncertain. They are very, very uncertain. We can put a plant in a box or a leaf in a box, and we can try to understand what happens when carbon dioxide goes up. But it's really hard for us to know enough about how a whole ecosystem will respond to the combination of increases in CO2 and increases in temperature, changes in water availability and water stress, etc. So I would view this as the assumptions we've made about plants are making a major contribution to what we think will happen in the future, but we need to be really thinking carefully about how those plant responses are represented. All right, so the take-home point being that plant responses also alter climate, and they're highly uncertain. Okay, our last story is that looking more at this biological uncertainty and how it impacts climate. And we have lots of collaborators on this work, including a bunch of folks who work at the National Center for Atmospheric Research. So I showed you this diagram of the Community Earth System Model's land component. And now I want to tell you that there are a lot of equations that describe this, and there are over 200 or about 200 of these things we call parameters, which are basically numbers in these equations that we've had to figure out what value to assign them based mostly on observations, but sometimes on other types of theory. And for example, this is the equation that describes how stomata open and close, and it depends on photosynthesis and relative humidity and the amount of carbon dioxide in the atmosphere. But then it's got this number G1 in front of it, and that would be one of these parameters. And it tells you the relationship between these three other variables. And we would figure out from observations, usually of leaves, what that number should be for different kinds of plants. So we took some work by a bunch of folks that work at NCAR who had run the land model, just the land component by itself, for all of these 200 parameters to their observationally plausible low value and their observationally plausible high value. So a lot of times observations show a range, and we have to pick one number to put in the climate model. And we found that 18 of these 200 parameters that had the biggest impact on how energy was exchanged with the atmosphere, because we are going to add the atmosphere and see what that does. And it's not so important to pay attention to what these are, but basically a bunch of things about plants and other things on land. And so what you can conceptualize this looking like is 36 possible worlds that have different assumptions about land. And each one of them is nominally a plausible assumption we could make based on how we think the land surface works. So what do the temperatures look like on these 36 different worlds? Well, I'm going to show you this plot that has latitude on the bottom axis with the equator in the middle and the North Pole on the right. We don't have a lot of land in the southern hemisphere. So this is the change in temperature from our sort of default model that we have when we change one of those parameters. It gets warmer or it gets colder. And we can see we get a spread of about 3 degrees Celsius in some places and an average over all land of 2.2 degrees Celsius. Again, that's not as big as the amount of warming we expect with the doubling of CO2, but it's more than half. So this is a large amount of difference in temperature based on these different assumptions that we could make in the land model. And what is driving that? Well, a bunch of things about soil processes, especially how quickly the surface soil layer dries out. Those create the biggest changes in temperature. And things about plants, like how the stomata work. So those numbers I showed you in that equation, they have a really big impact on temperature. And it's hard to go measure enough plants to be really sure what we should set those numbers to. I'm going to show you all of the different things we tied now, and the size of this bar is telling us how big of a range of temperature we could generate by changing that one assumption in the land model with the atmosphere attached. And the different colors are showing us sort of functionally different parts of the model. So the light blue is things that relate to water in the soil. The dark green are things that relate to how plants use water. The turquoise is things about photosynthesis. And the main point here is that a bunch of different types of assumptions in the land model can all have a pretty big impact on temperature. And these are all, again, plausible values that we could pick for these processes. So what like the assumptions we make about land, they really do impact the climate that we expect land to have. And we think they're also going to impact the way that it responds to change, but that's something that we're working on now. So our take-home point number 3 is that things that we don't know about plants have a large impact on climate, especially over land. And that to me is both motivating and also I think something that we should be working on. We really want to understand climate over land because we live on land. And so I want to understand what that climate's going to be, and I need to know how the plants are functioning in order to do that. So to sum up, I've been talking about this interaction between plants and climate, and especially how climate is influenced by plants, and the fact that our climate system has plants in it, and it's really this coupled system that we have to consider together to understand how it's going to respond to change. And I didn't even touch on carbon here, but that is another major factor of how plants will influence climate. So changes in plants can change climate. The plant responses to climate can also alter climate. So we need to understand what those responses are going to be. That's a hard thing to figure out only from observations. So we need theory, we need experiments to figure it out, and we need to be able to represent that in our projections of the future. And finally, biological uncertainty is large. It has a big impact on climate. So it's critical that we account for biology and biological uncertainty in climate projections. And I should say most Earth system models, they have a representation of biology, but they make one representation of it. And I think we need to do more to expose how that uncertainty in the biology is playing a role in what we think the future will look like. I wanted to end by showing you all the wonderful folks that have worked in my lab over the years, and say that across all of us, I think we've been supported by many federal agencies, a lot of funding support from the National Science Foundation, Department of Energy, as well as NOAA and NASA and the Department of Defense and the USDA for some work on agriculture. We make extensive use of things that are supported by the National Center for Atmospheric Research, especially the Community Earth System Model, and we've had wonderful collaborations with the group that develops the Community Earth System Model for many years. And if there is time available, I'd be really happy to take any of your questions.
Thanks so much, Dr. Swan. That was an awesome talk. And we have a bunch
no,
of...
I can't hear Shane.
Oh, no. Uh-oh. Can everyone hear me?
Okay, I'm going to refresh because this worked last time. I'll be right back.
All right. Chat, are you able to hear me? Okay, great. Well, time for me to fill some time. I'm really excited to answer all these questions. We've got some great ones for Dr. Swan.
I can hear you now.
You can hear me? All right, awesome. This is great news because you have some amazing questions lined up. Okay, let's start out with Cosmo, who is wondering, I work at a botanical garden, and I'm wondering if you agree that we should bring in a climate specialist into such a place to teach the staff.
That could be really interesting. I also think that it may be worth getting somebody who thinks specifically about plants and climate. And so there's a lot of people who come from the biology side of the problem that are really interested in how climate is going to impact plants. And those would be the people I think would be really able to talk to that community who cares a lot about what the plants are doing and how they might fare under future climate.
Absolutely. Okay, another question from LEB119. Do things like pine needles also have stomata, or are these valves more focused on broadleaves?
Yeah, good question. They definitely do. So pretty much all leaves have them, and they have they're on early plants, ferns, etc. They're in pine needles or needle leaf plants have them. They function a little bit differently, but they definitely still have stomata. And then broadleaf plants evolved later. They've got stomata and they also have more veins. So they tend to have higher water fluxes, but they all use stomata to regulate those water fluxes. And so there's really a lot of similarities across them as well as a few differences. But yeah, that you can get into all the details of the plant and how they transport water through their vascular systems, etc. Which is, I'm learning those kinds of assumptions about what plants do. They end up making a difference for climate at broad scales.
So coming from someone who is not a biologist or an ecologist, does an early plant mean a plant that evolved early?
That is what I meant by that. Yeah. I should say
Gotcha.
I'm not originally trained as a biologist either. I did most of my training in atmospheric and climate science and then have moved closer and closer towards biology and plant physiology as time has gone on.
Very cool. Okay, we have another question from Sydney Lindquist. Have you seen evidence of plants evolving as a way to withstand climate changes? I know it's being witnessed with animals, and they listed coat changes and migration as examples.
Yeah, there's some super interesting adaptation patterns, say butterflies that change the amount of melanin in their wings to change their thermal regulation. It's the same energy budget we would calculate for Earth. There is two ways that plants could respond and a few differences. So butterflies are pretty short-lived. So organisms like that, they have a lot of generations. And so they can evolve over time as they pass down those genes to the next generation. That could happen with plants, but because plants tend to live for a long time, especially trees, right? They live for decades to centuries. That's going to be really slow. But they can also do something called acclimate, which is where they can just kind of get used to new conditions. And there is evidence for plant acclimation. We acclimate too. So if there's a heat wave in the beginning of the summer, it's a lot harder on our bodies than if there's a heat wave later in the summer because we get used to the heat a little bit. That's acclimation. So plants are able to do a bit of the same thing. Lots and lots of questions about how much acclimation they'll be able to do. When will they reach those thermal limits? How much will they be able to acclimate? But we do see evidence of acclimation. And I expect we would see maybe adaptation through evolutionary change, but also just community change. So we could just have new species coming in or better adapted species taking over in those new environments. So we do expect that there will be changes in ecosystems, but it may not be the same, maybe new members of that community coming in.
Gotcha. And you just touched a little bit on your background, the question before this, and Cosmo's wondering, did you start in either of these fields? If not, how did you get into them?
Yeah, I started in Earth and Planetary Science at Berkeley, possibly.
Wow, yeah, go Bears! Couple of Cal alums.
Yeah, and I did atmospheric science initially, but even in my undergraduate research, I was looking at the fluxes of carbon from plants as measured by these towers called eddy covariance flux towers. And so pretty early on was already working with some data related to plants, but then I went and worked on tropical meteorology and thought about convectively coupled waves for a little while at Columbia, and then returned and ended up working on droughts and thinking about the land surface a lot more, which got me into thinking about forests and ecosystems and plants. So it's been a bit of a journey, but I did not start exactly in biology, but I already had some early thoughts about plants when I first started to get into research.
Gotcha. Wow, the Berkeley to Columbia progression, our careers are kind of mirroring each other a little bit. Okay, LEB119 has another question. How does working in Washington State affect your research? Do you focus on the PNW climate in your research, for example?
Yeah, I don't specifically focus on the Pacific Northwest because a lot of my questions are somewhat global and I think more applicable than just focusing on this region. But I do think there's some really interesting things here, specifically related to fire. So in the Pacific Northwest, we have both what you might think of as a kind of typical Western US fire regime, but we also have these really wet forests with incredibly high biomass that don't burn very frequently. And so they're really interesting and a bit different. So I think a little bit about the Pacific Northwest, but I really am interested most of the time in this sort of global picture of what plants are doing. Where are the big levers on the climate system? The atmosphere won't care the same about plants everywhere. That's one of the questions I have. You know, where are the places where the atmosphere cares the most? And then what's happening to plants in those places?
All right, I think we have time for one more question. Cambrian is wondering how much research is on grasses versus flowering plants and trees?
There's definitely research on both. And so those flowering plants and trees, those are the angiosperms. They've got the broad leaves. Grasses are a whole other thing. And then we've got the gymnosperms, which are the needle leaves. Some grasses have a different kind of photosynthetic pathway that lets them actually not care quite so much about carbon dioxide, but also not care quite so much about hot temperatures. And so it's definitely really important that we also include grasses and we include them as functioning a little bit differently. And so we use, whatever we can get from the plant physiological literature to understand how we should represent these different types of plants and what they're doing in the Earth system.
Great. Thanks so much, Dr. Swan. Really appreciate it.
Yeah, thanks so much for having me. Thanks for doing this.
Of course. Yeah, have a good one.
Bye.
Bye. All right, everyone. Wow, we are on quite the roll. Fantastic talk after fantastic talk. This is just good stuff. It doesn't get much better than this. And we are coming up on 6 hours into the live stream. It's crazy. It's flying by. Time flies when you're having fun. That's what they say. So before we move on to our next speaker, again, I just want to take some time to bring us back to our mission and the reason why we're doing this. Again, weather and climate forecasts are really important. Everyone deserves actionable weather and climate data, no matter who you are, whether you're a climate scientist or someone that's checking the weather on their phone. We need to have accurate weather and climate information. And the US is a world leader in providing this information, from developing the first computerized weather forecasts and the first models of climate impacts and all the network of observations that we have. We are really world leaders in weather and climate science. But the success was only possible because of investment by the American public. So the fact that the current administration is sort of challenging the foundations and destroying the foundations of the success is really threatening and is horrible for the future of weather and climate science in this country. So I wanted to draw some attention to the proposed budget for fiscal year 2027, which cuts NSF and NASA's Earth science budgets in half, and it eliminates NOAA's research arm, as well as slashing programs for training the next generation of young scientists. And as a young scientist myself, whose research is partly funded by NSF, this budget is definitely concerning. And I have a bit of a prop here to illustrate this. You may be saying, Shane, why are you opening an umbrella inside? That's bad luck. And I would say it'll be bad luck for everyone, and everyone will be opening umbrellas at the wrong time if we defund NOAA and our weather and climate predictions become less skillful. So that's my personal message with the help of a prop. And with that, I want to move us on to our next speaker, and remind you, the public, to reach out to your representatives using wclivestream.com/act to contact, call, or email your representatives and tell them to fully fund NOAA, NASA, and NSF, and fight against this proposed budget. And these decisions are being made right now, so we need everyone to make their voice heard right now. Okay, so I want to remind everyone that all speaker views are their own. And coming up, we have Kirsten Mayer, who is an early career research scientist at a federally funded research center, who is going to tell us about learning from machine learning.
Wonderful. Thank you, Shane. So my name is Kirsten Mayer, and I'm going to be talking about how I have been using machine learning to try to understand our Earth system better, specifically where our sources of predictability come from on subseasonal timescales. And if that didn't make any sense, we'll talk through it a little bit as we go through the talk right now. Before I get into this hot topic of machine learning, I actually want to start off with properly motivating some research questions that I have that I think are that machine learning is particularly useful for addressing. And to do that, I'm going to start all the way back with this concept of forecasting. And mainly I want to bring this up because I have a feeling that most of you all have an intuitive understanding of the limits of predictability in our atmosphere. And so to demonstrate that, I want to talk about your calendar, this hypothetical calendar that you have. And today's the 5th, and let's say you have a picnic planned for tomorrow and a picnic planned for the 25th. And my question to you to answer internally is which forecast would you trust? Is it both? Is it one of them? And do you trust one of them more than the other? And it's likely that you trust the forecast for tomorrow more than you trust this 20-day forecast out to picnic number 2. And this is because on 1-day timescales, we're generally actually pretty dang good at making these forecasts. And these are typically referred to as weather forecasts. On the other hand, a 20-day forecast is very, very difficult. And your weather app probably doesn't even go out that far, to be honest, in terms of these predictions. And if it does, I don't know if I would trust it very much. And the reason you have this intuitive understanding is because the subseasonal to seasonal timeframe is actually very difficult to predict. So we're not very good at it in the first place. Subseasonal to seasonal is typically referred to as about 2 weeks to 2 months, or 14 to 60 days out. And even though it's not very predictable, it is very important for us to understand when we have good predictions, because it is important for preparing for extreme events. It is important for agriculture. It is important for water and energy management and more. So I want to talk to you a little bit about why subseasonal to seasonal, or S2S, timescales are so difficult to predict. And the main answer to this question, and the simplest answer, is chaos. And this concept of chaos theory is that very tiny differences in our initial conditions, how we initialize our forecasts, can ultimately lead to huge changes over time as we roll out our forecasts. And I have this nice animation that was provided by Kelsey Malloy, who's a climate scientist as well, that demonstrates, let's see here. There we go. That demonstrates an example of 2 different X's, a green and a blue one, and they're just slightly offset by actually 0.012. And even though they start at what appears to be almost the same place, by the end, you can see that they followed very different trajectories to how they get there. And we struggle with this problem in atmospheric science when we are forecasting, because we have these little errors in our initial conditions. We can never perfectly measure the atmosphere due to instruments have error themselves, or the fact that we have to interpolate between where we measure our weather in the first place. So the next question you might be asking is, how do we even make a useful S2S forecast if we have this problem of chaos? And the answer to that is what some people study, is this concept of forecasts of opportunity. And the best way I can describe this to you is thinking about a bathtub. And pretend you have this bathtub and you have a rubber ducky in it, and you've set a toddler in it, and they're playing around in the bathtub. The water's probably pretty chaotic in there, and you're trying to catch this rubber ducky to make sure it doesn't fall out. It's probably going to be pretty difficult to predict where this rubber ducky is going to end up. But now let's say you turn on your faucet for your tub, and you have really good water pressure, and you end up receiving this like a little wave that propagates through your bathtub. And now it's very clear where this rubber ducky is going to end up. This is analogous to things that happen in our atmosphere, but in a much more complex setting, where this faucet turn on is now a state of our Earth system or our opportunity for us to have enhanced prediction skill. One of these opportunities that we have is referred to as the Madden-Julian oscillation, or the MJO. The MJO is this has dual components, one where we have very stormy and wet conditions, and one where we have very sunny and dry conditions. And these two components are located in the tropics. They're not always there, but when they are there, they tend to propagate from the Indian Ocean across the Pacific and the tropics over about 20 to 90 days. And now if we're thinking about our picnics that we have planned on subseasonal timescales, your picnic number 2, you might be asking me why we're focusing on the tropics right now, or a tropical phenomenon. And this is because the MJO actually has global impacts. And this is through what we refer to as tropical extratropical teleconnections, or another name that we often apply to this is Rossby waves. And these Rossby waves are kind of like this wave that propagates our rubber ducky forward. And that's how we ultimately feel the impacts of the Madden-Julian oscillation over North America. Now, the Madden-Julian oscillation and other modes of variability have been known to influence subseasonal to seasonal timescales for many decades at this point. And so we actually have a variety of tools that we use at our disposal to make these subseasonal to seasonal predictions. And over the last decade, there has been this growing use of this idea of machine learning to make these types of forecasts. And in particular, machine learning is so popular is because it's a statistical tool that allows for nonlinear relationships to be represented, of which we have many in our atmosphere and ocean and climate system in general. And they're faster than our dynamical models. However, machine learning also has the caveat that they're typically referred to as a black box. And a black box, meaning that we don't really truly understand how they make their predictions. It's too complicated for us humans to understand. And this is a no-go if we're talking about trying to make predictions that are going to save lives and property. But fortunately, along with this new machine learning boom that we've experienced over the last decade, there's a field of explainable artificial intelligence, or XAI, that has been developing alongside it. This concept of explainability is trying to understand why a machine learning model makes a certain decision. And it's done by often applying another method to your machine learning model. An example of one of these methods is known as layer-wise relevance propagation, or LRP. And I thought I'd just give a very simple example of how LRP works and XAI methods in general. So in this example here, we have 3 pictures. They each have a horse in them. And a machine learning model was asked to identify whether there was a horse in each of these images. The machine learning model says, yes, there's a horse in every single one of these images, which is correct. But now you want to understand why it thinks that. Could it be because of the vegetation in the background? Could it be the fence? Could it be the humans in the images? Could it be parts of the horse, like its ears or its hooves? And so you apply layer-wise relevance propagation, and you get these associated heat maps of the relevant regions that the machine learning model looked at to make its prediction. And what you'll notice is that in this red and yellow region, that the machine learning model is actually highlighting a copyright symbol that's located there. And this is because the training data had horses and non-horses, but all of the horse images had copyright symbol, and none of the non-horse images had those copyright symbols. So it was much easier for the machine learning model to identify copyright than it was to identify horses that could be anywhere in the image. So part of my work is trying to determine whether we can use these explainability techniques in conjunction with simple machine learning models to identify subseasonal forecasts of opportunity in a data-driven way. And I realize this is a lot to throw onto one slide, but bear with me here. Just to give a general concept of what we did for this particular research problem is we decided to try to figure out whether an artificial neural network, which is a very simple machine learning technique, could actually identify forecasts of opportunity. And to do that, we set up a prediction problem where we actually knew the true answer to these forecasts of opportunity. And in particular, what we did is we provided a field known as outgoing long-wave radiation that the Madden-Julian oscillation can appear within, because it's a way that we can analyze convection or precipitation. And so we input that into our machine learning model, and we try to predict some circulation anomalies in the mid-atmosphere approximately 3 weeks later. And this is because we know that there's a relationship between the Madden-Julian oscillation and the circulation over the North Atlantic. And so our question, once we had this machine learning model trained that actually performed well, was, are these forecasts of opportunities that our machine learning model has identified actually physically realistic? And what we found is that they actually were. So here we're looking at the layer-wise relevance propagation maps. On the left is for correct positive predictions, and on the right is for correct negative predictions. And what we see here is that the machine learning model is highlighting in the shading here that these two regions, one of enhanced precipitation and one of very sunny weather in both cases, which are indicative of the Madden-Julian oscillation. What was even more interesting is if we actually separated our negative predictions into two clusters, we found that one cluster was associated with that Madden-Julian oscillation type signal, but the other cluster didn't have that MJO type signal, but instead had this hotspot of enhanced precipitation to the west of Hawaii. And to our knowledge, we are not aware of any research that suggests that there's a connection between this precipitation and the North Atlantic, suggesting that even though we were approaching this machine learning problem as a known problem, it seemed to identify a possible new avenue for us to explore in terms of identifying sources of predictability for subseasonal timescales. With that, I just wanted to briefly mention that all the work that I've done in order to help improve our predictability and understanding of subseasonal timescales has been funded by the US government, including what funded this research was the NSF Graduate Research Fellowship Program. And then as I continue my work at a federally funded research center, I am funded through the Department of Energy and the National Science Foundation. And with that, I'll take any questions if we have time.
Thanks so much, Dr. Mayer. Awesome talk. We have a couple of questions. First from Cosmo. Did you start off in this field? And if not, where did you start? And how did you get into this field from there?
Yeah, great question. I've actually always wanted to be an atmospheric scientist since I was little. I was more interested in the weather timescales when I was younger. I loved severe weather. Having grown up in the Midwest, we had a lot of really fun storms that came through. But through funding from NOAA, the Hollian Scholarship Program, I was able to work in Boulder, Colorado for a summer and was introduced to the Madden-Julian oscillation for the first time. And that's where my journey really started in undergrad to focus on the subseasonal timescales. And then through this graduate research fellowship program, I was able to pivot even further by trying to teach myself machine learning during my graduate time. And that provided me the opportunity to do that. So in short, yes and no would be my answer.
Great. And LEB119 is wondering, so do you have to train your own model or are you using an existing model?
In this case, I have trained my own model. And I did that because I had this specific question that I wanted it to target. And I was using a very simple model that are generally more explainable. You don't necessarily need to do this, but if you're trying to target a very specific problem, I would highly recommend training your own model, which if you have just a standard computer these days, you can do on your own computer.
Wow, so cool. And All Things Pi is wondering about R squared. What was the verification on that modeling? Just wondering about R squared.
Like the R squared. How we analyzed our model was accuracy. So this was a categorical prediction problem. And so we were asking it to identify whether the circulation anomalies were positive or negative. And so we are able to evaluate the performance of our model using accuracy.
Great. And then, I mean, I have a question for you, as an atmospheric scientist who, it wasn't my dream from when I was 5 years old. I'm so curious, was it you were just inspired by the weather you saw around you, or what made you so excited about this field from such a young age?
Yeah, well, actually, I used to be terrified of severe weather, and my mom had taken an introduction to meteorology class, and so she knew a little bit about radar, and we would watch the weather on the news, and she would just kind of explain it to me, and then from there, I was just really interested in learning more, maybe purely just to become less scared. But in the end, it just turned into a love of the atmosphere and trying to understand it.
Nice. Knowledge conquers fear. I love that.
That's right.
All right. Well, thanks so much, Dr. May. I really appreciate it. All right, everyone. I think I'm about to hand off my hosting responsibilities. So let's see if we can get Dr. Kramer in here to take over.
Hi, Shane. How are you?
Hi, good. How about you?
Good. Ready to take over. Got a fresh cup of coffee. So
great. Yeah. Well, yeah, you're pulling the the late shift, but you got this. I believe in you.
And I wish I had an umbrella next to me. That was a great prop.
Hey, you know what? I have one in my lab at Lamont, actually. So only I was there.
Yeah.
I could give it to you.
Yes.
All right. Well, thanks so much. Have a good one.
Thanks, Shane. Thank you all for joining the Weather and Climate live stream, or the ones who have been here. We're on hour 7 now of our 50-hour event, and my name is Dr. Sydney Kramer, and I will be your host for the next 2 hours. I'm really excited. And before we introduce our next speaker, I just want to remind everyone, like everyone else has been, why we're here today, which are that weather forecasts save lives, support businesses, and really help communities prepare for extreme events. And the United States has become a global leader in weather prediction because of decades of public investment in science, observations, and forecasting research. And those investments are now under threat. So if you value weather forecasts and climate information, please consider using the link in the video description to contact your elected representatives and make your voice heard. A brief reminder that all speaker views are their own. So again, now like any good academic all-nighter, grab a fresh cup of coffee and settle in. And it's my pleasure to introduce Dr. Jeffrey Schinder, who is an associate professor at Columbia University, where I am now. And he's going to talk today about accurate weather forecasts saving lives. Welcome, Jeffrey.
Great, thank you so much. Hope you can hear me just fine. And it's nighttime for me as well. I'm in New York, like I think some of us are, and my cat has decided to join in some of the fun. So you might hear her, or she might even join the video in a second. So yeah, it's great to be here. Jeffrey Shrader. I'm an economist. So unlike a lot of the folks in the live stream who are on the natural science side of things, I'm a social scientist. So I don't study how to create forecasts. I don't study how to gather weather data or climate data. Instead, I study how people use forecasts and use weather data in their daily lives. And today, I'm going to talk about a research project that I worked on with a number of really wonderful co-authors, where we were trying to understand how forecasts help people avoid mortality from temperature. So just setting the stage a little bit, this is a presentation based on a project that just recently got published in the journal PNAS. And you can see the list of co-authors here, really great team. And we're working on a number of projects related to the social science of weather forecasting. The motivation for this project came from some observations that you all might be familiar with. First, the observation that extreme temperatures are one of the worst and most deadly natural disasters. You might have heard before, for instance, that extreme heat is the most deadly natural disaster in the United States. In fact, it's more deadly than hurricanes, floods, and tornadoes combined, according to both this article from a couple of years ago, as well as routine statistics from the National Weather Service. And it's not just extreme heat. Actually, temperatures across the temperature distribution can cause really substantial mortality for individuals. So there was a working paper released just at the end of last year by a whole bunch of social scientists, including my former graduate student, Andrew Wilson. And in that, they quantified the number of mortality events that are associated with quote unquote suboptimal temperature. And they found that in the United States, about 5% of all deaths are associated with suboptimally cold or hot temperatures. So temperature is just this really important determinant of people's health, really important determinant of mortality. And this is something that the National Weather Service is well aware of. So if you go to the National Weather Service mission statement, part of their mission is to provide weather and climate data, weather forecasts, climate forecasts, and warnings to protect people's lives. So the National Weather Service knows that temperature, as well as lots of other extreme weather events, are potentially deadly for individuals. They've worked for decades now to try to protect people from those. And this is the origin of our research project, the first question we wanted to answer, which is just to try to understand empirically how effective National Weather Service forecasts are at saving lives, particularly from temperature exposure. Because although we know a lot about how temperature exposure causes mortality, there's actually relatively little work in the social sciences, at least comprehensive work like I'm going to show you in a second, trying to understand how effective forecasts are at reducing that mortality. So in our study, what we did was take an empirical approach to this question. We combined just a whole lot of data from different sources to try to understand the effect of both temperature and temperature forecasts on mortality. So we brought together a really comprehensive set of data on mortality events in the United States over about a 15 or 20-year period from the Centers for Disease Control. We combined that with measures of temperature exposure for individuals, so the realized temperatures, realized precipitation that they experienced. And crucially, we also combined that with comprehensive data on temperature forecasts from the National Weather Service. We put all of those data pieces together, and this allows us to then go and empirically assess the effect of both temperature and temperature forecasts on mortality. And so the empirical exercise we did, you can think of it as the following. Using all of our data, we went and looked at locations in the United States and tried to use a bunch of control variables to essentially match up locations. We were looking at two identical locations where one just happened to have forecasts that were in error and one happened to have forecasts that were accurate. And we asked whether the area that had a more accurate forecast by chance had lower mortality. If yes, that's indicative that more accurate forecasts can help save lives. And we did the same exercise as well on the temperature dimension. So again, looking at two identical locations, one just happens to be hotter than the other on a given day. Is there higher or lower mortality? Or if it's extremely cold relative to another location, does that cause higher or lower mortality? We did this, as I said, across the entire US, so all US counties over a 15 or 20-year period. And we looked at mortality on monthly timescales. This allows for some of these important epidemiological features. The effect of temperature, the effect of forecasts on mortality might be delayed. So we're allowing those delays to come over the subsequent month. So putting together the data and that empirical approach, we found the following results. So here I'm going to summarize our main results on the effect of both temperature and temperature forecasts on mortality in a couple of different figures. Because what we did is estimate this full surface that relates mortality to both temperature and forecast error simultaneously. So if we zoom in on the temperature mortality relationship, which is shown in this figure, we find the following relationship. Basically, for very cold temperatures, temperatures say below 5 degrees Celsius or just above freezing, we found that mortality is quite elevated on a given day. Mortality falls as you get towards warmer temperatures or more moderate temperatures. It reaches a minimum between 25 and 30 degrees Celsius in our particular estimation, and then starts to rise very rapidly after that. So in brief, what this figure is showing, and this is something that's been shown by dozens or hundreds of papers before us, is that both extreme cold temperatures and extremely hot temperatures cause elevated mortality. That's what's given by this orange kind of quote unquote U-shaped curve here. The piece that's really new is the dashed and dotted line. This is showing the effect of temperature on mortality when forecast errors are present as well. So when a forecast is inaccurate, a temperature forecast is inaccurate. Focusing on the dashed line, this is showing the effect of temperature on mortality when forecasts are highly inaccurate on a given day. And what you can see is that this dashed line is generally above the orange solid line, indicating that when forecasts are in error, mortality is higher. That's especially true for warm and hot temperatures. So another way to see that is to zoom in on the forecast effect itself. So now, rather than looking at the mortality temperature relationship that we estimated, we're looking at the mortality forecast error relationship that we estimated. And you can see that the mortality rate, which is on the y-axis, is really a function of forecast errors especially at hot temperatures. So just to put some text on this, on hot days, days above, say, 80 degrees Fahrenheit on average, which is quite a hot day in the US, or especially above, say, 86 degrees Fahrenheit, 30 degrees Celsius, very hot days in the US, eliminating forecast errors would really help reduce excess mortality. That's what we're showing in these first empirical results. And this is true across the US on average. Now, this first empirical result, which does indicate that reducing forecast errors, making temperature forecasts, short-range temperature forecasts more accurate would help save lives, it raised a couple of additional questions for us that we also sought to answer. Really, what's going to happen in the future was the basis of the question. So how much better can forecasts get? Temperature forecasts, short-range temperature forecasts are already really, really good. So how much more scope is there for making these forecasts better? And how many lives would that save if we look into the future? So that's what we did in the second half of the paper. We did structured interviews with expert meteorologists, operational meteorologists, to try to understand what they thought would happen to short-range temperature forecasts over the next few decades. And that's summarized in this figure here. So we have time going from the beginning of our sample in 2005 out to 2100. The black points here are the observed forecast accuracy measured by root mean squared error in our sample. And then the blue, green, and yellow lines are the projections that our expert operational meteorologists gave us for what they thought would happen to forecast errors in the future. The central projection in green is what I'm going to focus on here. So basically, experts thought that forecasts they've been improving for a long time, for decades and decades. They thought that forecasts were going to continue to improve, and they thought that they would improve only slightly slower in expectation than they've been improving in the past. So this was already news to us because I think some people think we might have run out of room to improve these short-range forecasts, but no, our experts actually thought that there was quite a bit of room to make these forecasts a lot better. Combining that with our empirical estimates relating forecast errors to mortality, we found this final punchline, which is, forecasts do save lives. Forecast improvements expected by our experts, these green bars here, translate to thousands of lives saved per year. Putting that in percent terms, our experts thought that forecast improvements could reduce heat-related mortality by about 20% in the absence of climate change. We also did analyses where we allowed climate change to happen and forecast to improve, and that's given by the other portions of this figure. And basically what we found is that because forecasts are most effective on hot days, as the climate warms, forecasts actually save more lives. And it just so happens that the number of lives saved by forecasts roughly equals the expected increase in heat-related mortality in the United States. This is not to say that forecasts obviate the need to mitigate greenhouse gases or avoid climate change. because this is like running to stay in place. If we were to not experience future climate change, then we wouldn't, then we'd save lives even in the absence of that climate change, as the first part of this figure shows. The last thing I want to say before I wrap up is that we also talked to our experts about how they expected forecast improvements to occur. They emphasized to us that future forecast improvements really depend on a number of things. One, just bread and butter climate science and meteorology, continued weather and climate data gathering, so continued launching of weather balloons and radiosones, continued surface stations, continued satellite data, continued model improvement. Our experts, of course, talked a lot about AI models, both the promise and maybe the peril of those, and how that might help forecast in the future. And of course, the need for continued training of and input by skilled meteorologists. So one of the really exciting projects that I have ongoing is trying to look at the role of meteorologists in this whole operation. So I think what we're finding is that meteorologists have a really important role to play, and actually that role is getting more important over time rather than less important over time. But bottom line is our experts emphasize that we really need to maintain investments in both weather and climate data, weather and climate models, and the people who are working to understand those weather and climate models if we want to realize forecast improvements in the future that we show are life-saving. So with that, I will conclude, take any questions, and I'll also at the very end, like the previous speaker, thank the National Weather, or sorry, the NSF, which funded this research for the last few years.
Great. Thank you so much, Jeffrey. As someone who lived in South Florida for quite a bit of time, I know how uncomfortable extreme heat can get. One question I want to start off with, which I think is really important from LAB 119, is studying mortality sounds like it could be emotionally taxing. Does your workplace have a way to lift your spirits after sad findings? And this also kind of goes back to what Jeff Masters said earlier about just how emotionally taxing or how we can get really overwhelmed and need to take breaks sometimes. So love to get your perspective on how you unwind.
I think that for me personally, doing the work really actually helps with these feelings. When I talk to folks who I know who are very invested in, say, climate change as an issue, very invested in public health as an issue, but aren't working in these areas, I think it's actually, in my personal view, maybe a little bit harder for them because they don't have this way to feel like they're engaged with and taking action on the issue. Whereas I feel like my day-to-day job is wonderful in that sense. Yes, these are emotionally taxing topics to some degree, but at the same time, I do feel like being able to contribute potentially to some solutions here is really validating and gives me a lot of feeling of, just engagement with the issue. So that's the most important thing that I feel day to day. In terms of dealing with these feelings as well, I think that's where co-authors are fantastic because we're all working in these same areas. And I don't know, when I talk to climate economists, I feel like they're actually some of the most joyful people, strangely enough, that I talk to, even though we are working to some degree on a little bit of a grim topic.
Definitely. I'm sure a lot of the people speaking today share some of that sentiment. And then another great, really relevant question from WhatDog75 is that they're asking, is it true that forecasts have gotten a bit worse in recent times because of all the federal budget cuts, or is that just their local confirmation bias?
So 2025 data, our study ran through 2024, and by happenstance or not, we don't know, bottom line, but by happenstance or not, 2025 short-range weather forecasts in the US have been worse on average. Now, if you talk to, or when I talk to meteorologists, they are very careful to say that it's hard to attribute those changes to any particular budget cut or change in input data or something else. But the fact is that forecasts have been a little bit worse in 2025. Now, there have also been a few possible explanations for that, right? So there have been some really high-profile missing radiosone readings because weather balloons weren't launched, for instance, because of cuts. Certainly, there's been a loss of skilled meteorologists to some degree inside the National Weather Service. And as I said, work that I have ongoing is showing that those skilled meteorologists are extremely important for creating highly accurate weather forecasts. So I'll conclude this by basically saying I wouldn't be surprised if weather forecasts were causally worse in 2025 because of some of the losses that the National Weather Service has experienced, but it's an extremely hard causal link to draw for such a short time period.
Definitely. This is a really small field full of great people. We definitely all know people that have been affected by these layoffs and really skilled forecasters at the National Weather Service. That's a really important thing to bring up. Last thing I'll ask you, because it has been blowing up the chat, is if your cat is near. Everybody would love to see it.
Oh yeah. Let's see. She settled down during the talk. Usually she's a very active collaborator during talks, but let's see.
Oh, I heard the little
willing
meow.
to come and be, yeah.
Our pets
This is
are
Aloha.
to us. Oh, she's so cute.
Yeah. She's
Oh,
a beautiful cat. And
yes.
usually she'd be asleep right now, but she's excited to hear my talk, I guess.
We all need our therapy animals. It definitely
That's right.
helps. Okay, well, thank you so much, Jeffrey. We really enjoyed our time with you, and we really appreciate you coming out and
Absolutely.
showing us what you know.
Great. Thanks.
Thanks, Jeffrey. So we're excited to continue tonight's lineup with another fascinating discussion about the connections between science and society, which I know people have been excited about in the chat. And first, I just quickly want to highlight another challenge facing the weather and climate research community right now. And efforts are underway to dismantle the National Center for Atmospheric Research, which Jen spoke at length about earlier. NCAR supports research, modeling, observations, and tools that scientists across the globe rely on to better understand weather, climate, air quality, and wildfire smoke, along with much more. And decisions like these affect not only researchers, but also the information available to communities, emergency managers, and policymakers. So again, if you're feeling inspired by these talks, please reach out to your elected representatives. We've made it really easy on the website. There are scripts. You just give them a call when you have time. It only takes a couple minutes. Our next speaker is somebody really exciting for me to introduce. Her name is Dr. Samantha Kramer, who also happens to be my older sister and fellow University of Miami alum. So go Canes, a very fitting mascot for our chosen field of study. And Samantha is a founder and principal scientist at the Atmospheric Interdisciplinary Research Institute, which is a women-owned research firm where she builds bridges between atmospheric science, federal agencies, and communities to better understand wildfire and smoke and its impacts. So her talk today is going to be about wildfire and smoke, a problem without borders. And with that, take it away, Sam.
Great. Thank you so much for introducing me. It's a really special moment to have dual family members, both in the same field and so passionate about this topic. So as Sydney said, my name is Samantha Kramer, and I'm here to talk about wildfire and smoke today. So let's jump right in. Many of you probably remember the summer of 2023 when the skies turned orange over New York. People in DC and Philadelphia were checking air quality apps for the first time. And that smoke came from fires burning a very, very long way away. Similarly, actually, in 2020, smoke from fires burning in Oregon and California reached the East Coast. And just like that, a fire in rural Montana can create an air quality emergency in Chicago, or a fire in Southern California can close schools in Nevada. For a long time, people have thought of wildfire as a Western problem, a rural problem, or somebody else's problem. But that's really no longer true, and the science is really just showing that, even more so than we see in the news. So the fire itself may be hundreds of thousands of miles away, but the health consequences can land on your doorstep. And this is a borderless problem. And really that changes everything about how we have to approach it. All right, let's start with the moment people fear the most, being told to evacuate. There's a common, dangerous misconception about wildfire evacuations. Staying put, waiting to see how bad it gets, is the safer choice. Science actually tells us the opposite. So my work in this area draws on studies of real evacuations, including the 2018 Camp Fire, North Bay fires, and I've even studied evacuation and civilian fatalities across the country, as well as internationally, looking at when people died, where they died, and why. And this pattern is really consistent. The overwhelming majority of civilian fatalities during a wildfire happen when people try to leave too late or don't leave at all. Very, very few fatalities happen in cars on open roads. What the research also shows is it's not just individual decisions. Some vulnerable populations, such as elderly residents, people without vehicles, or those that don't receive alerts in time, face compounding risks. Just kind of also highlighting that beyond just the wildfire and the smoke science itself, that our road networks matter, our communication system matter. And all of these need to function really well under pressure. And I just kind of want to highlight these images on the bottom of this slide here. It may look very scary, being in your car and evacuating with flames and embers burning on both sides. But the science has shown time and time again that that is actually a safer place to be than when the flames are approaching your house, 10, 20, etc. feet, not inches, feet. So it's really important to know your evacuation routes. And speaking of preparedness and knowing your evacuation routes, I want to talk about how we prepare for wildfire. Well, I'll be honest, fire weather forecasting is hard. Fire behavior under extreme conditions is chaotic. An emergency manager is getting a call at 2 a.m. about a fire that's moving rapidly, and they're not working with certainty. They're working with the best possible information under pressure with lives on the line. So my work in fire weather forecasting lives in that gap. Not trying to promise a perfect prediction, but we're trying to give decision makers better odds, earlier warnings, better situational awareness, and a slightly larger window to act. And the path forward here is genuinely exciting because breakthroughs are coming from collaboration across all disciplines that haven't always talked to each other. So we have atmospheric scientists working with fire behavior models, working with social scientists, looking into how people are responding to warnings, as well as emergency managers telling us scientists directly what information they need in the field. And that kind of interdisciplinary work is where we are going to make the most progress in terms of outcomes and safety. Not a single forecast model, but the connections between things. And some examples here on the right, you can see a red flag warning. You may have been under one in the past or have heard of those. That's basically telling you if a fire ignites, whether it's due to a campfire, it's due to a downed power line, it could be from a car or even a train, that if an ignition happens, the weather conditions are hot, dry, and windy enough to make that fire behavior extreme. So it'll move quickly and may exceed what management can do. Another thing our federal scientists provide are these significant fire potential outlooks, and those go out several months on those S2S timescales that our previous speaker was just talking about. And then lastly here, I also want to highlight that we do have a lot of great state agencies out there also taking in the federal information and then distilling it down to their local communities. And here you can see a CAL FIRE post talking about the extreme fire weather danger on the morning of the LA fires that happened in 2025. All things considered, despite how horrific the events were, it was a well forecasted event, and there was a lot of communication that went out ahead of time. Okay, so now that we've talked about fire, here's a phrase to remember. We want to run from fire and hide from smoke. It sounds simple, but it captures something important. They are two different hazards that require completely different responses. When fire is threatening you, you move and you follow the evacuations. When smoke arrives, you shelter, you filter, and you monitor. But the challenge is most people don't know what to do when the smoke rolls in, mostly because you hadn't previously experienced it or weren't aware that a fire multiple states or even countries away is impacting your air quality. They don't know how bad the air is, whether to keep the kids inside, run the air conditioner, seal off the air conditioner, and that's a public health problem. And it's one the federal science has been working to address. One example I've been involved with is the EPA Smoke Sense app, which was a citizen science tool that gave people real-time air quality information during smoke events, let them report their symptoms and their actions. And that anonymous data fed directly back into research on how smoke is impacting our communities. It was a direct line between federal science and individual citizens. Unfortunately, it went offline in late 2024 due to a expected update. However, its future is now uncertain, and it's a casualty of broader cuts to the EPA research infrastructure. And that loss matters because smoke is not getting less common, it's getting more common, and it's reaching people further and further away. And I just want to highlight here, there are certain community groups that are even more susceptible from fire and smoke health impacts near and far. So those with lung and health conditions, elderly, pregnant, and children are especially prone to health-related impacts from wildfire, not just immediately, but into the future. So please make sure you know what actions to take. Okay, everything I've described today, evacuation planning, fire weather forecasting, smoke health guidance, requires coordination at a scale that no single community or agency can manage alone. The science that makes it possible to anticipate, communicate, and respond to these events is inherently collaborative. It's built across local, state, federal, and yes, international partnerships, because again, our atmosphere is not stopping at a border. Addressing these problems means that we need to be talking to each other across disciplines and across state lines, different jurisdictions, and data and forecasts need to also be flowing across these jurisdictions. That kind of coordination doesn't happen by accident. It's been built deliberately over decades through publicly funded research and programs, and it only works if the infrastructure holding it remains intact. The EPA's Office of Research and Development, the scientific home of SmokeSense, and much of the nation's air quality monitoring and wildfire health research has been closed. So the EPA Office of R&D has been closed. Not to mention the cuts happening at NOAA, NCAR, and the U.S. Forest Service. These funding cuts and payment delays are affecting researchers, universities, and the agencies that depend on their work. Tools the public relied on are going dark at exactly the moment where wildfire and smoke are becoming a routine part of our lives. So I want to be clear about what this means in terms of practical terms. It's not an abstract loss. It means emergency managers are working with less information, or they're having to pay for privatized information. It means communities are going without guidance on when to shelter and when it's safe to go back outside. And it means interdisciplinary science that I just described is losing momentum right now when it matters most. The public funds this science and the public benefits from it. So here's what I'd ask you to take away from today. Know your evacuation zone before you need it. We've seen record fires even on the East Coast this year in the middle of the country. It's not just a Western problem. It's better to know if you are in an evacuation zone and what's your plan. Make sure you're checking air quality during smoke events. Air Now is still available and free. And stay engaged with the institutions doing this work because your attention and your voice are what is sustaining us as scientists. And kind of the big picture is that wildfire and smoke are a problem without borders. The science to address it has to be too, and that starts with all of us understanding what's at stake. And with that, I'm happy to take any questions.
Hey, Sam, thank you so much. That was great. A lot of the chat were just as excited about us, about being sisters and getting to do this together tonight. And Cosmo Conjure asked, specifically Dr. Samantha, I unfortunately took Dr. Kramer first here. How did you get into this topic? Were you always interested? And did you inspire me to get into the same field?
Ooh, that's a tough one. So I was historically really interested in physics, and I really love puzzles. And really the atmosphere is a giant, puzzle, and it really impacts everyone and everything. And so I actually started looking at Saharan dust transport. So if you live in Miami in the summer months, you're breathing in dust from the Saharan desert. And that blew my mind when I started at University of Miami way back. And from there, looking at aerosols, I started looking more at wildfire and smoke because it is a growing problem and a really important one. It's really tough. It's not going anywhere, and it does have devastating impacts that are only growing. As for whether or not had an impact. I'll let you say that, but I also want to make sure I add that I will be hosting during Sydney's talk tomorrow, which I believe is at 10:40 a.m. Eastern.
Yes, great. Another thing that came up from Arcturus729 is the idea of being a borderless problem. And if you have any comment on the idea that Western countries aren't responding to climate change appropriately because it isn't strongly affecting them yet compared to lower income countries and more marginalized groups. And if the more marginalized groups tend to be bearing the brunt of the deaths. And I think it's important to also talk about this within the contiguous United States as well. I think these disparities do exist domestically as well. So if you could speak on that, that'd be great.
Yeah, absolutely. I will say the preparedness to react and mitigate your exposure to smoke, especially, does see a lot of disadvantaged communities are unfortunately not as prepared to react. So if you're in a disadvantaged community, you can't run out to your Home Depot and buy a $200 air filter because the air quality is bad. It also comes down to, the age your house was built, if the windows seal properly, if you have an HVAC system. If you don't have an HVAC system, how are you going to filter your air? And like I mentioned previously, EPA had come up with a number of great low-cost solutions, such as putting like a standard air filter on a box fan, which ended up doing some really good filtration for wildfire smoke. And places like California are now setting up clean air shelters for disadvantaged communities. So there is a place to go and retreat from the smoke if you are unable to mitigate that in your own home. And there's a lot of research being done in that area. In terms of the international problem, fire has always been a part of our climate, but especially in the US, we have been suppressing fire for so long that we have so much fuel to burn. And a lot of, depending on the country, there is more seasonal burning than potentially allowed in the US, depending on the region, just because, we tend to put out fires where other folks, and especially the indigenous community, tend to embrace fire. And I think there's a lot of differences between cultural aspects of fire in that sense.
Yeah, those are all really important points to bring up. And also with things like resources such as clean air shelters, it's also an important time to speak on the importance of funding FEMA and their actions in responding to these really extreme climate events that we're getting. LEB 119 also asked, where were you in your scientific career during the 2023 summer? Were you already working in this field at the time?
Yes. In 2023, actually, I will say in 2020, I was living in San Francisco when the sky turned orange and we had ash coming in our windows. And that was really scary. And then fast forward to 2023, I'm living in Denver now, and we've also had some of the worst air quality days in the world due to fire-related smoke. In 2023, I was working in this field, and SmokeSense was online. We had gotten a lot of responses and a lot of great information and data where folks were telling us, how they were responding to smoke, what they were experiencing. Again, that wasn't anonymous, but we could then use that response to kind of understand what messaging is getting through. I remember people calling me from the East Coast, we're from New Jersey, being like, what do we do? This has never happened before. Like, I don't even know where to look. And at least at that time, I was able to point folks, to that tool. And that actually prompted a redesign. In 2024, we spent a long time trying to make it a better tool. But unfortunately, due to the funding cuts, it has been indefinitely halted. So again, just trying to fill those gaps because it's going to happen again.
Yeah, absolutely. Cosmocondra brought up something that's really important for the public to understand. And she said, I learned recently there's healthy floods. Are you saying there's healthy fire? So if you could speak on prescribed burns, that'd be great. I know Samantha's done a lot of work with prescribed burns. So.
Yeah, so the favorite term right now is beneficial fire. And yeah, historically, is a good thing for the local environment. Indigenous communities had long used wildfire to kind of turn over minerals and improve agriculture. Historically, we should have been burning in the last few decades. However, due to our suppression of those fires, we're really behind. And prescribed fire is one of our best possible tools to reduce the fuel loads. The main problem with the beneficial fires, and that could be, a wildfire that's easily contained, and they're like, you know what, we have enough resources here on the ground, the weather is calming down, let's just manage this and let parts of it burn to reduce some of the fuel loading, is again the air quality impacts. So it's a coordinated effort between the air quality agencies for prescribed burn. It is very hard to get one of those approved, and the weather has to be perfect, and you need all of the staff on site. It's a large undertaking to do a prescribed burn. Just from the permitting process alone is really daunting, but it is a extremely, extremely important aspect to combating the wildfire problem.
And a follow-up question to that, does that extreme amount of investment to do these prescribed burns tend to come from federal funding or from state funding?
That's a great question. And the answer is both. If you think about all of our natural wildlands, like the national park systems and those, there's a lot of burning that needs to be done, and land ownership plays a major play. For example, in California, the beneficial fire plan that was released in 2020 has the state agreeing by 2025 to burn 500,000 acres per year of beneficial fire. And the Forest Service also matched that with a guarantee within California to burn 500,000 acres. So it's really a partnership based on the land ownership. Because fire is not going to stop at the boundary of that state park or the national park. They need to kind of coordinate in that way.
Right. And I'm going to use some little insider knowledge for this last minute. Do you happen to have one of your kitty cats right next to you to show the world?
Unfortunately, I do not. I wish I did. Hopefully they'll make an appearance during the hosting window tomorrow.
That is a plan. All right. Thanks so much, Sam. And again, reminder to tune back in 10 a.m. Eastern time tomorrow, and she'll be hosting then. Thanks for joining us tonight, Sam.
Bye, Sid.
Bye. That was awesome. Really cool moment for us. And now I just want to highlight that science advances because ideas are rigorously tested, challenged, and evaluated by experts. The process is especially important today because proposed changes to federal research funding could allow political appointees to override scientific peer review when determining which projects receive support. For generations, the United States has benefited from a system where the strongest scientific ideas compete on their merits. Preserving that process is essential to maintaining scientific excellence and public trust. Please reach out again to your elected representatives if you feel moved to let them know that you agree. And I am really excited to say that our next speaker is going to be Dr. Andrew Dessler, and he is a professor of atmospheric sciences at Texas A&M University, and he's going to give us a little bit of insight on how science really works in 3 easy steps. So I'm going to turn it over to you, Andrew. Welcome.
Thank you. Thank you. It's great to be here, and I really appreciate all the viewers. Thank you guys for tuning in. I'm going to talk about something that I think a lot of people don't really understand about how science works. So now arguments over any scientific topic, whether it's climate change or vaccines or you name it, they revolve around competing scientific claims. For climate change, is the earth warming? Are humans to blame? What are the impacts going to be? And over the last 150 years, the scientific community has developed this really remarkably robust method to determine which claims are true and which are not. And this is what I'm going to talk about. So anyway, how does science generate knowledge? So if you ask a high school student, how does science work? They'll give you the high school definition, which they learned in 9th grade science, which is you have an individual scientist makes a hypothesis, conducts an experiment, and draws a conclusion. And this is more or less what actually happens at the individual level, although it's a bit more iterative than that, where experiment, hypothesis, design are kind of happening at the same time, and you come up with an idea and you kind of do some analysis, and it wasn't quite right, so you come up with a slightly different idea, but nevertheless, at the end, you've reached some conclusion about whatever hypothesis you've ended up with. Now, this is not science, though. This is step one of science, and the reason is any individual scientist can make mistakes. Scientists are human. They make errors. Maybe there's a bug in their code. Maybe they made a mistake in their experiment. And so just because someone's done an experiment, reached an conclusion, doesn't mean it's right. And so, and scientists don't take the results of an individual experiment as being like, okay, this is now correct. So what's step two? Well, step two is the scientist writes up their report, what they did in an article, and then they submit it to a journal, and it goes through peer review. And this is the first layer of quality control in the scientific world. And during this process, they send the report to other experts in the field, and the other experts in the field judge whether the methods are sound, if it appropriately references previous work, if the conclusions logically stem from the data. And if you ask any scientist, they will tell you peer review is miserable because you get brutal comments back. I mean, I cannot tell you how brutal it is. And you have to go through this cycle of, you get comments back from the reviewers, and oftentimes they can be mean, and they can, it's very tough, and they're criticizing your work. You spent a year on this, and so you have to revise it, and it goes back to the editor, and the editor will sometimes send it back to the reviewers. And so you really have to respond well to those comments. And so in order to get it published, it has to go through this process. And eventually, if you write a paper, it goes out for review, it comes back, you fix it, maybe it does it a couple times, the editor will eventually accept the paper. Now, peer review is really good, and it catches an immense amount of bad science, but it can't catch all bad science. Some reviewers are sloppy, some reviewers are overworked. Sometimes they just miss, they're humans, they miss obvious mistakes, and they can't catch hidden errors. Like there's a bug in the code, so it wasn't doing exactly what you described it was doing, or maybe you misread a lab scale. And so peer review is the first step of quality control, but it's not the last. Just because a peer-reviewed paper makes it into the journal doesn't mean the paper's right. And nobody thinks a single peer-reviewed paper is right. So then what happens is important results are retested by the scientific community. I like to call this the crucible of science. So if you write a paper that's really interesting and you release it, it will get dissected by the community at that point. And in some cases, people will try to reproduce what you did. That actually doesn't happen that often, maybe more in lab experiments than in computer experiments. But more likely what they do is they test the implications of it. If you say X is true, you might say, well, if X is true, then I can look at Y, because Y will also be true. So you can you can test the implications of it. And if something survives long enough, then the claim is accepted. So this is how we generate knowledge. So let me give you an example. All right, let's go back to the ozone hole. So 1985, I'm sure very few of the people watching were around in 85. I remember 85 well. 1985, the ozone hole was discovered. And Joe Farman and his colleagues published the observations taken from Antarctica showing that every year the ozone, a big chunk of ozone over Antarctica was disappearing. And this was shocking because up until the discovery, most atmospheric chemists thought that most of the ozone that was going to be lost would be lost at mid-latitudes and high altitudes. So this loss was happening completely in a place where nobody thought loss would be occurring. So immediately, when you see something you don't understand, scientists started trying to fill the void. And so a bunch of theories emerged, which were all published in the peer-reviewed literature, by the way, that argued about different possible causes. So the first one was chlorine chemistry. So here's a paper by Susan Solomon and a bunch of other big names in the field arguing there was chlorine that came from fluorocarbons. Another argument is that it was nitrogen chemistry, not chlorine chemistry. And the nitrogen could have come from solar proton events. In other words, it was the sun that was doing it. And the third claims that it wasn't chemistry at all, but it was dynamics. If there's very low ozone air in the upper troposphere, and so if you have rising motion, then you'll bring that low ozone air up into the lower stratosphere. And so that's a different way of getting very low ozone air in the lower stratosphere. And so we had these three theories, all published in peer-reviewed literature. And so then the scientific community went to work on testing which of these stood the test of time, which of them could survive in the crucible of science. And so pretty quickly what happened is they flew into the ozone hole and they measured nitrogen, and they saw there was no nitrogen there. So it couldn't be nitrogen that was destroying the ozone. So they were able to rule out reactive nitrogen as the cause of the ozone depletion. And then people were doing various calculations and measurements. They realized that the air in the polar vortex was descending. That would bring high ozone air down. It was not rising. So you could eliminate the dynamic theory. And then there was the chemistry. Well, they were, again, the same planes that were measuring oxides of nitrogen in the polar vortex were also measuring chlorine, and they saw there was a ton of chlorine there. And they saw that the chlorine very strongly correlated with the regions where the ozone was depleted. And so people refer to that as the smoking gun paper, really established that it was chlorine chemistry that was destroying the ozone. And so what basically happened through this process is a consensus emerged as to what was going on. Now, it's important to understand, you often hear people talk about scientific consensus. Let me make the point, consensus is organic. There's no vote, there's no poll, there's no meeting to decide what it is. What it means is that people go to meetings, I talk to other people, and pretty soon, everyone kind of independently decides this is the right answer. It's the ultimate free market of ideas. And if you read any peer-reviewed paper after the late 1980s, they don't even talk about these other theories. They just take it as given that chlorine chemistry is responsible. And so this is what we mean when we say a consensus has emerged. It doesn't mean every single individual scientist agrees with that, but it does mean that there really is no legitimate debate about the issue. All right, so this then brings us to the question of where can you see, or anybody else, what scientists think? Well, it's in the peer-reviewed literature. If you read the peer-reviewed literature, you see the entire historical record of the argument. You see the ozone hole being discovered. You see the theories emerging about what it could be. You see the debate about those theories happening. You see testing of rival hypotheses. And then you see the community coalescing around one of them. That's consensus. And so, just read the peer-reviewed literature. Now, I will point out that there's a lot of opportunity for people to misrepresent the literature, because you can go into the literature, and if you go back, you can find papers that say the ozone hole is caused by dynamics. And somebody says it's fluorocarbons and chlorine. You can say, oh, but I have this paper from these famous scientists that say it's dynamics. And what they don't tell you is like, well, that idea was disproven and nobody believes that's correct anymore. Even by the authors who wrote those papers, they just don't talk about it. So the peer-reviewed literature is there, but what's the problem with this? So the problem is that the peer-reviewed literature is written in a language I call nerd. So this is something I just cut out of a paper, and it's extremely hard to understand. So don't even try to read this. It's even hard for me to understand, and I wrote it. So, reading the peer-reviewed literature is incredibly hard. And, it takes graduate students years to read all the literature in a field. And so you can't really expect policymakers or individuals to read the literature. And so this is where scientific assessments come in. So what is a scientific assessment? Well, the one you've probably heard of most is the IPCC reports, Intergovernmental Panel on Climate Change. And the fundamental role of an assessment is to read and summarize the peer-reviewed literature, doing exactly sort of what I described is the argument. So they summarize what's in the literature. They synthesize what's settled, what's disproven, what remains actively debated. And importantly, it's authored by large teams of scientists. And that's important because large teams are less likely to be biased than small teams. It also means that the impact of any individual biased scientist is minimized. The teams are assembled to avoid bias. Like they don't let one single person who might have an axe to grind, pick members of the committee, because he can stack it with people who all believe one theory. And so they don't do that. And in addition, the report undergoes several rounds of peer review itself. So the scientists write it. It goes out to other scientists. They write comments. It goes back to the authors. They edit it. It goes back out to the peer reviewers. It comes back. It goes through many rounds of peer review. And the credibility of these reports comes from this rigorous process. That really is why you can believe in it. It's the gold standard. And if you see an assessment that's written from a different process, it very likely might not be credible. You can actually see, if you look at them, you can see the evolution of consensus. So I'll just give you one example about attribution of warming. So in the 1990 IPCC report, it said the size of the observed warming is broadly consistent with predictions of climate models, but is also the same magnitude of natural climate variability. Thus, the observed increase could largely be due to this natural variability. So the 1990 IPCC report said, we don't know why it's warming. Maybe it's humans, maybe it's not. We just don't know. 1995, the second IPCC report said the balance of evidence suggests a discernible human influence on global climate. That, by the way, is the definition of a sentence that could only be written by a committee. Basically, it doesn't say much. It says, humans are having some influence. We don't know how big it is, and maybe it's not having any influence. In 2001, the evidence was getting stronger. The consensus was emerging. Most of the observed warming in the last 50 years is likely to have been due to the increase in greenhouse gas concentrations. 2007, most of the observed increase in global average temperature since the mid-20th century is very likely due to the observed increase in greenhouse gas concentrations. So we went from likely in 2001 to very likely in 2007. And then in 2013, it's extremely likely. So you can see the consensus emerging over time in these things. The 2023 report basically says the same thing as 2013. It can't get a lot stronger than that. And so you can see this occurring in the assessment reports. So I'll just wrap up here. How does science work? Well, let me start by saying science is our ultimate tool for deciphering the universe. It's what we've developed is the most successful way to determine what is true and what is not true. And the understanding of science is written into the peer-reviewed literature. So if you want to know what scientists think about something, read the literature. Now, it's hard to do for people that don't speak nerd. And so in those cases, rely on scientific assessments. They are what I call the Rosetta Stone. They translate nerd to English. Anyway, hopefully there's some interesting questions. I love talking about this, so I will open the floor. Thank you.
Hi, that was an amazing talk, Andrew, and really pulled back some of the, mystery on our process of how our studies sort of get out to the public eventually. One thing that's been coming up throughout a lot of the talks is AI, of course, and Henry F. Drake brought up a great question, which is, Andrew, what do you think of the imminent flood of AI written papers and implications for peer review? Some applies to proposals as well.
Yeah, that's a really long discussion, Henry. I think that even before AI, our publication system was at the breaking point because of how many papers people were writing, and it was wearing out peer reviewers. And I think AI is going to be just disastrous. I think we really need to rethink how the whole system works. It's probably time. We've been doing this for 150 years. It may be time to redo it. It still works, but I could easily see a world where you can go to your Claude code and say, run CESM with this slightly different convective parameterization, analyze it against a control run, and write a GRL paper. And a week later, you get a paper. And so it's going to be a lot of papers. The papers won't be very good, though. That's the problem. So there'll be really a lot of mediocre, possibly correct, maybe not. And then it's going to wear out the peer reviewers. And so the peer review won't be particularly good because people are just going to be so overwhelmed. I think the quality of peer review has declined since I was a graduate student because of sort of the amazing growth of the number of papers that are being published. So I think science still works, but I think it's showing its cracks.
Definitely. And I would say some journals are, a little better than others and really keeping that high standard of publication. This is a great question, just in terms of speaking as a professor. LEB 119 asked, this is a bit more personal, but Dr. Dessler, what % of your academic role is dedicated to teaching versus research?
Yeah, that's a good question. So it's part of it depends on how you define teaching. So there's really two categories of teaching. One is classroom teaching, sort of what everybody knows. You stand in front of the room and write on the board. And then the other is graduate student mentoring, which is also teaching. I mean, and so I don't spend that much time in the classroom, but I spend a lot of time mentoring students. So, talking to students, reading stuff they write. And so, I think it's really, in fact, I would say it's hard to separate research from mentoring, because, the whole reason that universities exist is not to do research, it's to educate students. And the reason we have research universities is that's how you educate a PhD student. You can't just have somebody in class and explain to them how to do research. They have to do the research. And so, I think that, I spend a lot of time mentoring students, not that much time in the classroom, but all of it's teaching.
Right. Completely agree. And then just one fun question. Can you think of one really big example where the consensus in climate science ended up drastically changing over time?
Yeah, that's a great question. So let me preface this by saying something I think is really interesting and true. And that is that the reason science works is it relies on the collective intelligence of a lot of people who are already pretty smart people. I mean, I view my job as competing with the smartest people in the world. And then they work together. So it's this incredibly smart collective intelligence. Collective intelligence is very powerful. I don't know if anybody remembers Who Wants to Be a Millionaire, the game show, where the contestant would get asked questions and he could sometimes poll the audience, and the audience was almost always right. And so, the collective intelligence of the scientific community is such that it almost is never wrong for things that it says, we believe this very strongly. It would be unthinkable if it was proved the Earth wasn't warming. It would be unthinkable if it turned out DNA wasn't a double helix, or quantum mechanics didn't describe atoms or molecules, or smoking didn't cause health impacts. That would be literally unthinkable. So for this specific question about climate science, I don't think there have been any places where important, strongly held beliefs turned out to be wrong. If you read some of the very old assessments going back before the IPCC, there's a report called the Charney Report, written in 1979. That was for the National Academies. And you read what they wrote, actually a reporter just sent me a memo from Exxon from, I think, 1981, 1982. And I read it and I thought, these guys have it exactly right. There's nothing, there were a couple of things in there where they said, we're not sure if this is right, but we think it is. And they were always right. So, I think that one of the things that gives me the most confidence in climate science is that there haven't been big revisions to our knowledge base. The stuff that Arrhenius thought in the 1890s and Ravel thought in the 1950s and Plass in the 1950s and Charney in the 1970s and Manabe and Weatherald in the 1960s, as Nadir talked about. It's all stuff that we now know is still true. We just know it a lot better.
Right.
Our knowledge has improved
Agreed.
Tremendously over that, but they had the right idea.
Absolutely. Yeah. That's a really great point. Well, thank you so much for joining us again this year. Everybody in the chat seems to remember you very fondly from last year, so we really appreciate your time. Thanks for coming.
No, thank you guys for doing this. I think this is incredibly important. I really appreciate it. So thank you. And I'll be hosting tomorrow. So if people want more of my insight, I'm not sure exactly when, but it's tomorrow afternoon. So I'll hope to see people then.
Great. We'll see you then. And thank you, the viewers that are still here and have been here for a while, and for spending part of your evening with us as we continue exploring the science that helps us better understand our planet. And we'd like to again remind everyone that the weather and climate information we rely on today is built upon decades of sustained public investment. From weather balloons and satellites to ocean observations and climate models, these systems provide the data needed to monitor and understand Earth's changing climate. Unfortunately, many of these programs are facing significant funding challenges under proposed federal budget cuts. So if you haven't already, please consider using the link in the video description to contact your elected representatives and advocate for continued support of weather and climate research. And I am really extra excited about the rest of the speakers that I'm going to get to introduce until midnight, because we all have something in common. And we have all passed at some point through the doors of University of Colorado in Boulder, right near NCAR, throughout our careers, go Buffs. And our next speaker is going to be Clark Zimmerman, who is a graduate student in oceanography at the University of Wisconsin-Madison. And she's going to be talking today about the Atlantic meridional overturning circulation. Welcome, Clark.
Hello, thank you so much for that introduction. Yeah, I did go to CU Boulder as my undergrad, so that's a cool connection. As I was introduced, my name is Clark, and I'm a graduate student at the University of Wisconsin-Madison. I study the dynamical stability of climate systems, and I'm currently funded by the NSF. Okay. So today I'll be talking to you all about the Atlantic meridional overturning circulation, or AMOC. I'll be referring to it as AMOC for the rest of the talk, and some of the statistical techniques that I study, and then I'll briefly introduce my current research project. So let's get started, and let me introduce my PowerPoint helper, Mate. That's a picture of my cat's face. Direct your attention to wherever she is on the slide, and that'll help you follow along with my talk. So, what is the AMOC anyway, and why do we care so much about it? Well, the AMOC is an important element of the global climate system. It's responsible for transporting heat from the tropics to the higher latitudes in the Northern Hemisphere. Additionally, North Atlantic deep water masses aid in the regulation of global heat and carbon budgets by sequestering excess heat and CO2 into the deep ocean. While the primary driver of the AMOC is debated, the strength of the AMOC has generally been considered proportional to the density gradient in the Atlantic Ocean. Some contenders for AMOC drivers are deep convection in the subpolar North Atlantic, pushing the circulation on, or alternatively, Southern Ocean westerlies pulling the circulation through Ekman transport and the associated upwelling. I don't study the AMOC's drivers, however, rather the potential existence of an alternate mode of the circulation. It's been posited that the AMOC is bistable, with an on or strong state like the modern day AMOC and an off or weakened state, potentially during previous ice ages. However, the possibility of a shutdown of the AMOC is hotly debated despite the media excitement about a future collapse of the AMOC. It's yet unclear whether the modern day AMOC is bistable, as in if an alternate steady state exists in our modern world. Additionally, there's been much conversation regarding the future trajectory of the AMOC, with many comprehensive models predicting future weakening, but observations generally showing no or little decline. So, what might cause a collapse of AMOC if such a thing is possible? To understand one potential mechanism, let's take a look at the AMOC from a few different perspectives. On top, you can see a depth latitude schematic of the AMOC. Below, we see the AMOC in density space. This illustrates the increase in density AMOC water masses experience as they're transported northward before any deep convection occurs. And in the third plot, we see density in depth space, highlighting the shoaling of dense water mass classes in the subpolar region, with more stratification in the northern hemisphere than the southern hemisphere without the aid of that Southern Ocean Ekman pumping. Just for clarity, stratification are these lines right next to each other, so a large difference in density over a short distance or short depth. Okay, so now let's look at some surface and subsurface currents associated with the AMOC and the subpolar North Atlantic. This region is very important to AMOC dynamics due to the North Atlantic deep water formation that occurs here. The water masses brought up from the tropics by way of the North Atlantic current, which are those red arrows also connected to the Gulf Stream. Once those salty Atlantic waters are brought up, they undergo water mass transformation, which increases their density class to form North Atlantic deep water before sinking and being transported southward at depths of around 1,000 to 2,000 meters. If the AMOC is driven by this deep convection, which is debated as I mentioned, then an increase in buoyancy in this region could trigger a positive feedback, potentially resulting in a sudden collapse of the circulation. This is the salt advection feedback, in which increases in stratification here could reduce that deep convection and thus reduce the amount of warm salty waters being brought up, further reducing that deep convection and AMOC strength. However, there's another important feature here, the subpolar gyre, highlighted with this orange circle. Vigorous mixing by a wind-driven circulation could mitigate some of the impacts of the buoyancy-driven positive feedback mechanism that I just described. Okay, next we'll get into some of the statistical techniques that I study, specifically CSD theory, or critical slowing down. But first of all, what is a critical transition? So here we can see a system described by this differential equation, which has a bistable regime bounded by two saddle node bifurcations, illustrated with those stars. As the system is forced linearly with some forcing, F on our x-axis in this plot, it evolves from the monostable regime at the tail into the bistable regime in the middle. Critical transition occurs when the system experiences a sudden, irreversible transition from the bistable regime into the alternate steady state. Now, let's look behind the scenes at the evolution of the dynamical landscape of the system. The potential wells shown around this plot indicate the system's preferred state or states on the x-axis for some given forcing. So, for example, let's take a look at this transect in the bistable region, where the upper branch solution corresponds to the right-hand well, the unstable solution corresponds to that hump in the middle, and the lower branch solution to the left-hand well. So if our system starts out on the upper branch in the right-hand well, as the forcing is rammed forward, the system falls from this well into the left-hand side. If we reverse the ramping, the system can't follow the same path back. It must be forced to the lower saddle node to make the right-hand well again accessible from the new steady state on the left. This is irreversibility, and it leads to a hysteresis in the system. Now, CSD is an attempt to use statistical indicators to predict this type of irreversible transition. Let's use an example of this technique being applied to a simple model of the AMOC. This is the two-box model from Chessy in 1994, which is adapted from the Stommel 1961 box model. This model is very simple. There's two boxes. One is warm and salty, represents the subtropics. One is cold and fresh, representing the subpolar region. The temperatures are clamped and the salinity is forced, with the subpolar box getting progressively fresh. So here the state variable is just the salinity difference between the two boxes, which in this model is directly proportional to the strength of the overturning. So here we can see a single stochastic run or realization of thermohaline flow from that two-box model, with freshwater forcing on the x-axis and salinity difference on the y. In this model, the apparent saddle node bifurcations are very robust, and the trajectory of this realization mostly follows the analytic solution, transitioning from the on state into the off state. In order to analyze the statistics of a model, we generally want to conduct many runs of a model so we can analyze 100 or even 1,000 realizations to better understand the overall behavior of the model. So now we can see 5 different realizations overlaid on top of each other, showing how the model experiences a range of critical transitions right around that critical threshold. So CSD theory tells us we can predict this type of transition by looking at the statistics produced by these time series. It's most easily understood by looking at the associated potential wells at a few different forcings. In our time series, Okay. So the state of the system begins by being corralled by the narrow left-hand well, whereby the system experiences relatively small deviations and has a low memory as it's bouncing around essentially randomly. It then moves into the bistable regime with a wider well, where it's experiencing larger fluctuations because the well is opening up, so the system is able to move more. So here the system has lost some stability and the memory of the system has increased. Lastly, it falls off the cliff into the alternate steady state or right-hand well, where it resumes with those small deviations. Statistically, we can measure the changes in deviations and memory as variance and autocorrelation, with increases in these indicators acting as so-called early warning signals for this type of critical transition. As expected by CSD theory, the variance and lag-1 autocorrelation both increase as the system approaches the critical threshold. As you can see in this simple example with a robust bifurcation, CSD theory holds up well. However, we do need to be careful when applying this technique, as several stringent conditions must be met before it can be confidently applied, and it's best used as an indicator of stability changes rather than a warning of collapse specifically. Feel free to ask me more about that if you're curious. I don't have time to go super in-depth during this talk. Okay, so I will very briefly discuss where I come in to the problem. So in general, these are the questions I'm seeking to answer through my research, which is presently supported by the National Science Foundation. So I use box models like the one showed before, varying in complexity from that simple 2-box version to much more complex versions to assess the AMOC's dynamical stability. Some of the questions I'm curious about are if simplified representations of complex dynamical systems can even be used to assess the real system's dynamical stability. With the AMOC specifically, idealized models tend to readily simulate this type of collapse, as you can see here on the left. The system's jumping back and forth between different states. But comprehensive climate models typically don't simulate this type of bifurcation for the AMOC. Which brings me to my next question of if box models are inherently unstable, is there some sort of remote forcing or coupling that would be stabilizing for the system that we're missing in these simple models? Or is it because we overemphasize the salinity impact that's emphasizing that positive feedback? And lastly, I'm curious what the minimum complexity required to include all relevant dynamics is while maintaining the benefit of an idealized model. Because you can't recreate these type of dynamical landscapes from a comprehensive model. There's just too many degrees of freedom. So it'd be nice to have a simple model that does include all of the relevant dynamics. Okay, that is all I have prepared. I'm happy to take any questions now. And you can feel free to shoot me an email as well if I don't get to your question today.
Thank you so much, Clark, for such a fantastic talk. Everybody has been obsessed with your cat, and I do, and everybody's pet. So I just wanted everyone to know
puppy.
He's my lab assistant, and he comes with me to the office, and he is very well known and loved in the scientific community as well. So everyone meet Charlie. And Clark, somebody brought up a really great question about AMOC specifically and how you sort of chose that being your scientific career focus at this time.
Oh, why I chose AMOC? So my situation is maybe a little bit different from some other oceanographers or climate scientists. My background is in physics and statistics. So the type of statistical techniques that I study could be applied to literally any climate system or ecosystem or even financial system. Any type of dynamical system is really very similar, and these type of techniques can be used for any of them. The reason I focus on the AMOC right now has to do with basically just how important it is for the climate system, and the fact that with climate change, if this system does in fact have two stable states, we could be approaching a transition point where we could be transitioning into the other state. So it's very important to be studying this system now. So beyond that, no real personal reasons as to why I study it.
Yeah, and that brings up a great point that a lot of the work that we do when it's really based in physics and math has a lot of different applications outside of our field as well. And another question from LEB 119 brought up, is it difficult to study AMOC in Wisconsin, or are there lots of great resources for your studies there? And that also brings up a really interesting point in that different universities and different departments tend to have faculty that have different focuses of research, and some are better for certain topics than others. So if you want to speak on that, that would be great.
Yeah, absolutely. So that's what everyone says to me when I tell them I'm going to oceanography grad school in Wisconsin. Yeah, there's no ocean near here. But all of my work is on the computer, so I wouldn't say it's any more difficult to study it than from any other place. However, you bring up a great point. My department is definitely known for its more meteorology research. The oceanography department is very new. In fact, I am my advisor's first ever grad student. There's a lot of fresh faculty in the oceanography portion in our department. So yeah, I would say that our specialization is definitely in the meteorology side, but our oceanography side is growing for sure.
That's great. And Fish Failurson 5114 asked, are there any misconceptions about the AMOC that you'd like to address that weren't already?
Yeah, I kind of hinted at this in the talk. I am of the personal belief, don't talk to, don't talk to the University of Wisconsin about this or the NSF. But I don't believe that the AMOC is approaching a critical transition or collapse. The timescales of the AMOC are very long. So the time series that some studies have used in order to predict this type of transition are either not long enough, in my personal opinion, or have the coverage is a little bit too variable in order to really understand the statistics that it's producing. Because, for example, if you're taking one data point every year for 50 years, and the next 50 years you're taking 3 data points per year, the change in those statistical indicators over that time is not going to be super accurate, because you're going to have that signal of the frequency of observations in there. So I would just say, don't freak out when you see a New York Times article saying the Gulf Stream's collapsing tomorrow. We're probably fine.
Definitely. People obviously love a nice catchy title, but you bring up a really great point in that, the general public tends to think about observational comparisons as reality or fact. But sometimes our observational records can be really flawed and require a lot of tweaking to get something meaningful out of them. And sea surface temperatures specifically are one of the harder things for us to really have a good gauge on over a long period of time.
Exactly, yeah.
And on that note, how does data quality and instrumental noise limit our ability to evaluate these early warning indicators? From Shawn Wang.
Great point. I feel like I kind of touched on that just now, but this is an excellent point. Instrumental noise. So if an instrument has the same noise throughout the entire period, then that's not an issue. You can easily remove that type of noise from your time series and still get great info about it. It's more when there's a change in the amount of instrumental noise or in the color of the instrumental noise. So like if the noise is autocorrelated itself, that can definitely mess with your results. And if the data quality is changing over the time, it will definitely limit your ability to understand those early warning indicators and potentially make them not useful at all, because you wouldn't be getting the signal from the system, you'd be getting the signal from the data.
Right. Really great understanding of that for everyone. Really good job explaining that. And thank you so much for joining us. We wish you all the best in your graduate studies. And thank you so much for taking the time to present. That was a great talk.
Awesome. Thank you.
We are well into our 8th hour, and it's breezing by because we are having so much fun. And I want to continue to highlight the science that helps keep communities informed, prepared, and safe. We want to remind everyone that weather and climate research depends on long-term investments in science, observations, and education. Many of the forecasting tools and climate data sets we rely on today were built through decades of public support and federal funding, and proposed cuts to agencies such as NOAA, NSF, and NASA would affect not only current research, but also the training of future scientists. If you value weather forecasts, climate information, and scientific research, please consider using the link in the video description to contact your elected representatives and make your voice heard. Our next speaker is Hartig, who is an early career scientist, Arctic scientist specifically, and is currently sitting at CU Boulder, like I said, SCOBUFs. And today, Kara is going to be talking to us about Supercool Arctic clouds. So welcome, Kara. We look forward to your talk.
Thanks for the intro, Sydney. So as she said, I'm Dr. Kara Hartig. I'm a postdoc at the Cooperative Institute for Research in Environmental Sciences at the University of Colorado. So this is a really cool opportunity to work with a large collection of scientists all in the same place who do slightly different things. This gives me a lot of really good resources to work with. And we're going to pivot a little bit off of the ocean from this last talk to look upwards at the atmosphere and think a little bit about what's going on over our heads. So I wanted to start by pointing out, for those of you who maybe don't think about the Arctic as much as I do, that it is warming 2 to 4 times faster than the globe as a whole, which is a major motivation for trying to understand what's going on with climate there. So the plot that I have here is showing the temperature change from the late 21st century to the early 2000s. And the color indicates how strong or weak that temperature change is. And here you can see that you have this really amplified warming signal at the really high northern latitudes in the Arctic. This feature is called Arctic amplification. It's been studied very extensively. It's been known about and predicted for a really long time, but it's complicated enough that there are still a lot of factors about it that we don't entirely understand, which I find fascinating. So as I mentioned, there are a number of different factors that contribute to Arctic amplification. I'm going to focus on just one of them, but there are a lot of really interesting things to learn here. So one of the factors is water vapor, clouds play an important role, sea ice plays a huge role in this signal, heat transport, both in the ocean and the atmosphere from other regions. The one that I'm going to focus on is clouds. I find them especially interesting for a few different reasons. One of them is that they have a pattern of warming, of enhanced warming near the surface and less warming at higher altitudes that looks just like Arctic amplification. So it's a really good candidate for being an important factor here. They also are so transient that it can be very challenging to get good time records of them. So we have satellites that have been taking observations for a long time and we can use those. But in places and circumstances where your satellites are not giving you super reliable retrievals, and the Arctic is one of those places, it gets especially challenging to understand what the observed trends are in addition to being able to predict what the future is. So we have a lot of really interesting scientific questions that come up with clouds that we'll be exploring a little bit in this talk. So the data that I work with and that we'll be looking at together is from the North Slope of Alaska. This is a long-lived Arctic observatory. I have it shown in the map on the left-hand side. It's been there since the late 1990s and has been taking measurements continuously. It's managed by the US Department of Energy. As I said, they have over 20 years of continuous observations across many, many different instruments and measurements. The photo that I have shown here is showing a few of the instrument platforms that they have set up at this site. And you can just imagine how many different instruments they stick on the top of each of those buildings and run from the computers inside of them. One of the other huge advantages of this site that I think speaks a lot to the importance of having publicly funded science is that all of the data is quality checked and validated by experts. And I don't just mean scientific experts, I mean experts in the specific instruments that are being used. So they know exactly what the noise is on those instruments, they know what kind of conditions leads to them being trustworthy or untrustworthy, and they can add flags for all of those things into the data so that scientists like myself who are really interested in analyzing the data but not as familiar with the individual instruments themselves can use them in a responsible and informed way. So this is a huge resource for scientists. It lets me work with data sets across many, many different instruments that I don't myself have to be a total expert in. And this gives me a lot of cool opportunities to understand what's going on with the clouds at this location. So one of the important reasons that we're interested in clouds is because the surface temperature, so that's the temperature of the air that's near the ground, is closely related to how much energy is flowing into or out of the ground. So on this plot on the x-axis, we're looking at the amount of energy flowing into or out of the surface. So points on the left-hand side means that the surface is cooling. On the right-hand side means that it's warming up. And on the y-axis, which is the vertical, we have the surface temperature. So near the top is warm and near the bottom is cooling. And the important distinction here in the color is that each of these points is an observation combined of temperature and the surface energy at this slight north slope of Alaska. And the color tells you what is happening overhead at that time. So the gold points are when there is clear sky overhead and the blue points are cloudy. And you can see that there's a sort of natural separation between colder energy losing surface when it's losing energy from the surface when we're in a clear sky state, and warmer and having sort of holding that energy in the surface when there are clouds overhead. So clouds are helping to determine whether the surface is in this energy gaining or energy losing state, and subsequently the surface temperature. And this is a big motivation for trying to understand whether you can effectively predict what sort of cloud cover you'll have in the Arctic. Now, the surface energy balance, the amount of energy flowing in or out, affects more than just the surface temperature, which is part of why we look at that directly. So the amount of energy going into the surface influences how quickly the sea ice melts and how hard it is for it to regrow in the spring and the fall. So it can contribute to things like the sea ice loss that we've observed over the last few decades, shown on the left. It can also contribute to the melting of ice sheets, especially in Greenland. So having these events that bring in intense cloud cover that lead to Trapping more heat near the surface can cause rapid melt events on the Greenland ice sheet, and both of these effects, especially the ice sheet melt, can contribute to sea level rise, which is felt across the globe. They also impact biodiversity, so things like the amount of energy that's coming into or even through the sea ice into the ocean below can impact phytoplankton and algae, which serve as the base of the marine food web. They can influence migration patterns of fish and other like larger megafauna in the ocean. They can even contribute to extinction of some of the more sensitive species. They also influence permafrost. So we were just talking about what happens over sea ice and ocean. If you look at what these impacts can have over land, at these high northern latitudes, the land is frozen solid all the time. So it's very, very hard. And this is called permafrost. But as you start to increase the amount of heat going into the surface, then you can melt that permafrost, which can compromise infrastructure such as roads, buildings, and pipelines. It also releases harmful gases, including greenhouse gases. So the surface energy balance is important for understanding a lot of different features of the climate, and especially the ones that are really important for climate change. Now, the Arctic surface in winter tends to be either cooling really quickly or maintaining temperature. So this plot is showing us just the surface energy. And you'll notice that you have this kind of camel hump shape where a lot of the observations are clustered either in this strong surface cooling on the left or in this surface maintaining temperature on the right. Now, there are a couple of implications for this. This means that there are kind of two preferred states that the surface likes to be in the Arctic. It also means that the average conditions are not the typical conditions because it's really a combination of these two very different states. So if you look at just the average, it represents a state that is rarely actually observed in the atmosphere. And that also means that small changes of how often you're in one state or the other can have a really big impact on the average energy that's coming in or out of the surface, especially over an entire season. So understanding how you kind of seesaw between the two humps of this camel helps you to get a better handle on what the total energy exchange is between the surface and the atmosphere in the Arctic. Now, as it turns out, clouds are a really important factor for determining whether the surface is cooling. So here I'm showing again in the gold, the clear sky conditions, and in the blue, the cloudy conditions. In the background in gray, you have the same two-humped camel that we were looking at before. And you'll notice that when it's clear out, we're almost always in this surface cooling state on the left. And when it's cloudy overhead, we're almost always in this surface maintaining, holding heat on the right. So clouds have a really important influence on whether we're in one state or the other. And that means that under things like climate change, if we change the occurrence of cloudy versus clear skies, we could be looking at a major change in the surface energy budget. So we want to make sure that we can predict those possibilities really well. But how is it that these clouds have these influences on the surface energy? So I thought we'd start by talking a little bit about what clouds actually are. So clouds are suspensions of either liquid droplets or ice crystals in the air. Each droplet is tiny, tiny, tiny. They're 0.0008 inches across, which is about the size of a grain of pollen. And they're so small that they're able to stay suspended in the air just because they fall so slowly. The air resistance is actually what keeps them up. And many, many of these little droplets have to collide into each other and condense into a bigger droplet before they're large enough to fall out of the cloud as rain or snow. So they sort of hold themselves up by being super, super tiny. Now, clouds need two things in order to form. The first is water, and the second is aerosols. So water is what is making up the clouds. You need it to be saturated in order to condense into a liquid or an ice. So if you don't have enough water in the atmosphere, think of this kind of like your humidity. If you're below 100% humidity, there's just not enough water that it's able to easily condense into cloud. You need to have a lot of water in the atmosphere and be at saturation, 100% humidity to form liquid or ice. The aerosols are what determine the where. So these are tiny particles that give the water somewhere to collect instead of having to kind of spontaneously condense out of thin air. There are many, many different types of aerosols that exist naturally in the climate, as well as some that are produced by human activity. This includes things like dust, pollen, wildfire smoke, sea salt,
And depending on where you are in the world, you might experience different types of these aerosols. So where I live in Colorado, we get a lot of dust and a lot of wildfire smoke, especially in the summer. But if you're in a coastal region, you might have a lot of sea salt aerosols that are seeding your clouds. But you really need both of these things together, both water saturated and aerosols, to start to form droplets that can become clouds. Now you can get supercooled liquid clouds under conditions when droplets are able to remain liquid even when you've dropped below the freezing temperature. To understand this, we need to think about what it is that's preventing the liquid from freezing when it gets so cold. So the first part is that as water begins to freeze, it has to release some heat in order to transition from a liquid to a solid. If that heat isn't able to escape the droplet, it gets trapped in the remaining liquid, and that liquid is no longer below freezing. It heats itself up. So you need to have kind of efficient heat evacuation systems set up for your individual droplets before they can freeze. You also need particular types of aerosols to help you form ice. So ice will form more easily if you have a physical structure inside of the water droplet that looks kind of like ice crystals do. It makes it easier for the water molecules to arrange themselves properly to freeze into ice. So typically, both of these things together means that under really cold conditions, you can actually have liquid clouds even when you're well below freezing. And this happens extremely often in the Arctic. Now, the reason that we care about whether the cloud is liquid or ice is because liquid clouds have a much bigger impact on the surface energy budget that I mentioned before. Part of this is because liquid clouds have many more droplets. So I mentioned that you need specific types of aerosols to form ice. Those aerosols are a lot less common than the types of aerosols that form liquid. So if you have a liquid cloud, you might have millions of droplets per single liter of air. But for an ice cloud, we might be talking about 5 or 10 ice crystals in that same volume, just because it's a lot harder to get the types of aerosol particles that can form ice. So the fact that you have so many more droplets in these liquid clouds gives them a lot of opportunity to interact with radiation and heat. So having liquid clouds overhead, and especially in these really cold regions where you can have supercooled liquid clouds, even when it's very cold, allows you to trap a lot of heat near the surface. Now, clouds can also have a cooling effect just because they reflect a lot of sunlight, so it never reaches the surface in the first place. But I'll remind you that we're thinking about the Arctic right now. And in the Arctic in winter, there is no sunlight. It is dark for months at a time. So this heating effect ends up really winning out and being the most important. And in Arctic winter, as I mentioned, because of these maintenance of supercooled liquid, you can have liquid clouds commonly. So here on the gray bar, we're thinking about all of the winter days that are observed at the North Slope of Alaska. About 70% of the time, there are clouds of some kind overhead, and about 30% it's clear. And between 30 and 60% of the time, you have liquid clouds overhead specifically. So even though it's always below freezing this time of year, you can often still have liquid clouds in the Arctic. And those, as I mentioned, have important implications for the surface energy and the surface temperature. Now here to kind of drive this point home, we're looking at this same camel humped plot that we were looking at before. In this case, we have clear in gold and cloudy conditions in green. But now instead of just looking at any types of clouds, we're going to think specifically about when there are supercooled liquid clouds overhead. And that is these blue indicators here. And you can see that most of that far right hump is coming specifically from cases where you have liquid clouds. So understanding liquid cloud occurrence helps us to figure out what's going on with the surface energy. So to look a little bit at the specific type of observation and study that I do, I try to understand how cloud properties like the amount of liquid, the amount of ice, how deep the clouds are, how long they stick around, vary as a function of what kind of weather conditions we're under more generally, to see if they respond differently under different weather conditions. So to do this, we used a actually quite old machine learning method called self-organizing maps. This has been around for 15 or 20 years, in case you didn't know that machine learning has actually been around in science for a while. And we use this method to define 12 weather regimes. And those I'm going to indicate by these gray boxes that are showing up here. So each of these indicates kind of a distinctive type of weather. So you can think of this as being Like maybe on one particular square, we're talking about like getting really, really cold, frigid air blowing out of the Arctic. It tends to be very dry. It's coming off of the Arctic Ocean. And once we move down to this lower right-hand corner, we're starting to look at these much warmer and wetter conditions when the wind is blowing off of the Pacific Ocean and we're bringing in a lot of fresh moisture. Now, each of these boxes corresponds to a different type of weather regime, but the closer they are to each other in this grid, the more similar they are. So I'm going to say that the most important distinction is to know that this upper left-hand corner is these cold, dry, Arctic-y conditions, and the lower right-hand corner is the warm, wet, sort of Pacific Ocean moisture conditions. Now, these are all being observed at the North Slope of Alaska, but this is a way that we're going to characterize the weather regime there. And now what we can do is try to understand for each of these different regimes, are we seeing significant differences in things like cloud properties? So we start with a vertical colored bar that's going to show us which of these 12 regimes have significant differences in the total amount of water in the atmosphere. And we see that, as we had hoped, most of these cases have a distinctive water vapor signature. They've got that green flag on. This means that our method is doing a good job of actually representing different types of weather. Now, we can also do a flag for whether the amount of ice in the cloud is different, and that's shown in this light blue color. And we see that a lot of these regimes are still indicating differences in cloud ice. So that starts to tell us that the weather conditions do actually influence the amount of ice that you form in your cloud. And we found that that has to do a lot with the amount of moisture that's in the atmosphere. But if we do the same thing for the amount of cloud liquid, which is the one that's important for the surface energy, there is not a single weather regime in this whole set that has a significantly different cloud liquid from any of the others. They all look almost exactly the same. So this has been what we would call an interesting null result, which means we were expecting to see that the cloud liquid depends on something, maybe the temperature, maybe the moisture, maybe the winds. And what we're finding is that it's actually really insensitive to a lot of these conditions, which leaves us with a lot of open questions that we still want to understand. So where we're going from here is trying to look at things like, well, maybe the immediate conditions at North Slope of Alaska aren't what matters. Maybe it has to do with the history of those clouds. We also want to understand what types of clouds have the biggest impact on surface temperature over their lifetime. So I have a student who's coming in on a research experience for undergraduates program this summer to work on that. And we're also looking at what sorts of conditions might be dissipating these clouds so that they no longer can stick around in the Arctic, and whether that might change with climate change. So,
Dr. Hartig, it breaks my heart to cut you off a little bit early. I'm so sorry for time. That was such an incredible talk, and you covered so many complex topics and made them so understandable. So we are so happy you joined us. And I know there were some questions in the chat. If you have time to hop on YouTube after and respond to some, that would be great.
I'll do my best. I'm so sorry that I ran.
No problem at all. No problem. We loved it. That was perfect. And I will forever be using camel hump over bimodal. That
I think it's just more fun.
It is definitely more fun. Okay, so last speaker of my hosting segment. But before I get to them, I just want to say that I want to one more time shine some light on why we're here and how scientific discoveries are made. For generations, weather and climate research in the United States has been supported through a competitive peer review process where experts evaluate proposals based on scientific merit. Many scientists are concerned about recent proposals that could increase political influence over research funding decisions and weaken the system. Strong weather and climate science depends on independent research, open inquiry, and support for the best ideas. If you'd like to help protect that system, please use the link in the video description to contact your elected representative. I'm also going to note, and I'll explain more after our last speaker is done, but at the end of this next talk at midnight, we are going to be shifting to a new link. And so I'll explain that once Shawn is finished. But our next speaker, I'm very excited to introduce, and it's Dr. Shawn Wang. He is also currently at the University of Colorado Boulder, and he's actually working with my former PhD advisor, Chris Karnaskis. And he is a climate scientist and a series visiting fellow. So welcome, Shawn, and we can't wait to hear your talk. He's going to be talking about climate change disruptions to Pacific and Indian Ocean connectivity. Welcome.
Thanks so much, Sydney. Thanks for the introduction. And yeah, it's a small world. Me, you, Kara, Clark, everyone here at CU. So yeah, it's really great to have a good community here. And yeah, I'm really excited to be here and share my research on how climate change may be disrupting how the Pacific and Indian Ocean talk to each other. And for this talk, we're moving a bit far away from the Arctic and clouds there into the balmy, warm waters of the tropics. And so a little bit of background about me. I'm a postdoc at CU Boulder. As Sydney just mentioned, I study tropical climate variability on sort of longer time scales than weather. So I'm interested in thinking about decade to decade and century to century changes in the tropical climate system. And today I'll be talking about some research from my PhD, which looked at how global warming might be disrupting how the Pacific is influencing Indian Ocean climate variability. So let's dive right in. On this slide here, I'm showing a schematic of the tropical Pacific Ocean and sort of its average conditions, just to give everyone sort of an overview of that. And what we see here are the ocean surface temperatures with warmer waters in the Western Pacific, colder waters in the East. And you'll see that because of this east-west gradient in sea surface temperatures, or SSTs, we have much more convection and rising motion of air in the Western Pacific. And when that air, warm and moist, rises into the troposphere, it then circulates and descends over the Eastern Pacific and creates this loop, this atmospheric circulation called the Walker circulation. And so this is what the Pacific looks like on average. Now, as many of you may know, the tropical Pacific experiences these large variations that impact all of us around the planet. It goes by the name of El Nino Southern Oscillation, or El Nino. And during an El Nino event, what happens is all that warm water in the Western Pacific starts sloshing over to the Eastern Pacific. And when that occurs, the convection, that plume of air that is ascending into the upper troposphere, also shifts to the east, with some big implications, not only for the Pacific Ocean, but for other parts of the world as well. And similarly, the negative phase of ENSO, or the El Nino Southern Oscillation, is called a La Nina, which some of you might also have heard in the news and otherwise. And this is basically the opposite phase of ENSO, where we have a strengthening of this Walker circulation with even colder waters in the Eastern Pacific and even warmer waters in the Western Pacific. And so this sets up sort of the basic understanding of how the tropical Pacific varies on sort of year-to-year timescales. And what's important to think about with ENSO, with El Nino events, is that their impacts are not restricted to the tropical Pacific. In particular, during an El Nino event, it's usually found that the Indian Ocean, which is right adjacent to it, experiences this basin-wide warming. And the reason for that is because of these changes to the Walker circulation, to the atmosphere. When we have warmer waters in the Central and Eastern Pacific, we have ascending motion over there, and then we have descending motion sort of in the Eastern Pacific, Eastern Indian Ocean. And that basically reduces cloud cover in the Indian Ocean and increases the amount of sunlight that can come onto the ocean surface and increase warming. And so you can think of the typical relationship between these ocean basins as an El Nino event favoring a warming of the Indian Ocean. And why do we care about this warming pattern in the Indian Ocean? Well, it actually also affects various countries and atmospheric circulation and rainfall of its surrounding continents. Typically, when this Indian Ocean exhibits this warming, basin-wide warming pattern, we have a much stronger Asian monsoon. And we have evidence here from this paper in 2007 that when we have this Indian Ocean warming, that we have enhanced precipitation over India. And that has really big implications for the billions of people living there. Similarly, recent studies have found that this Indian Ocean warming can actually impact places around the world as far away as Antarctica. So this study from 2022 actually found that this warming pattern excites this large atmospheric wave pattern. You can sort of see it as these alternating red and blue blobs in sea level pressure that affects sea ice extent and concentrations all the way in Antarctica. And so this warming pattern and this cooling pattern of the Indian Ocean is actually a really big deal, and we need to understand what drives it. So, like I said, typically what we think of driving this Indian Ocean warming is patterns in the Pacific Ocean. And what I'm showing here on the left-hand side is a time series of their covariability and their coherence over the 20th century, or from 1900 to around the year 2000. So the black line here shows is an index indicating the strength of the Pacific Ocean zonal SST gradient. So the more positive value here means that the Pacific is more El Nino-like, and the more negative value means that it's more La Nina-like. So that's that cooling and warming of that Eastern Pacific. And then similarly, when we look at the Indian Ocean in orange, we see that it's warmer when it's more positive and cooler when it's more negative. And these two lines are pretty much on top of each other over the 1900s. But when we look at what's happened over the last 20 years or so, we see a very interesting divergence. We see here that from 2000s onwards, the Indian Ocean has been sort of anomalously warm, while the Pacific Ocean has been transitioning to some of a La Nina-like condition. And this is here providing sort of a spatial perspective of that, where we have that cooling of the Eastern Pacific that's typically associated with a La Nina event, while we have this warming of the Indian Ocean, which is a really curious situation. This is not typically the relationship that we're used to seeing between these two ocean basins. And so this has sort of led us to think, is this a climate change signal? Is this sort of a signal that global warming has sort of disrupted the relationship between these two ocean basins? And if we look at this time series here on the left, we see that really on these longer decadal timescales, we only have 3 to 4 complete oscillations of it. So whether or not the recent period that we're seeing, this recent disruption, this decoupling, whether or not this is really significant, whether or not it's really a robust climate change signal, is kind of hard to say just using data from 1900 onwards. And so ideally, what we would like is to extend this record even further back in time to get more data points, to get more of these cycles of El Nino and Indian Ocean warming to make a robust claim about whether this is exceptional or not. And so is this something we can do? Well, as many of you probably know, today we have a lot of different instruments and tools to help us observe and sample sea surface temperatures in the global oceans, including these Argo autonomous floats in the ocean, satellites, or ship-based measurements. But if we go further back in time, before like the 1980s, we have very sparse data. So on the right-hand side here is a map showing percent coverage of sea surface temperature across the global oceans from 2000 to 2025, from the early 1900s, and even further back before that. And if you look before 1900s, you see that the only real coverage we have is from the very few shipping lanes that were still present during that time. And not only is this data very sparse this far back in time, but all the measurements that we've made were using somewhat inaccurate methods of measuring ocean temperature, such as a sailor going over the side of the ship, pulling up water using a wooden bucket, and then sticking a thermometer into it when it's up on deck. And as you can imagine, that might introduce biases that we are not fully aware of. And so all this to say that using the instrumental data that we have now is difficult to really make these robust claims of, is the recent change we're seeing unprecedented or not? And so the goal of this study that I'm sharing today is to try and extend this record further back using 2 types of tools. One is paleoclimate records, and the second is climate model simulations. And we hope to really increase the sample size of this pre-industrial Indian Ocean, Pacific Ocean relationship to try and understand recent trends. So for those of you that aren't familiar, paleoclimate records are sort of these natural archives that are out there in the world that we can hope to extract climate information from. On the left-hand side is a scuba diver, a scientist extracting a coral core from this shallow water coral reef. And I want to stipulate that these scientists are experts at this and do not damage or detriment the corals from this sampling technique. They extract these coral cores that we see on the top here, and we're able to measure geochemical isotopic data from these, and we can use established relationships between these geochemical measurements and whatever variable we're interested in, like sea surface temperatures, to reconstruct and extend a variable we're interested in further back in time. So that's what we do here in this study. We're using a bunch of core records, some tree rings, and even one stalagmite, or sort of a cave deposit, to try and reconstruct the Indian Ocean sea surface temperatures and the Pacific Ocean sea surface temperatures further back in time than what we have from instrumental data. So I just want to show sort of the context for that here. On the left-hand side, in black is the instrumental data of Indian Ocean warming, that sort of warming pattern you can see. And in green is sort of the paleoclimate reconstruction of that same index, that same type of variability. You can see they're pretty nicely overlapped each other over the 1900s. And similarly, we're doing the same thing for the Pacific. We're trying to reconstruct that El Nino, La Nina-like pattern using the corals and the other paleo records we have. And we believe that this data is good because of the good corroboration that we see between the instrumental data and the paleo data. But what's great about this paleo data, right, is that we can extend it even further back in time before we had any quality instrumental data. So this gives us a longer context to try and study the relationship between these two ocean basins. And so the second tool that I'll be using to understand the covariability of these two basins is climate models. And so these are complex numerical models that are run on these large supercomputers, such as the one on NCAR that is currently in jeopardy of being dismantled. In particular, my study uses the CSM model that's sort of built by NCAR. And using this complex model, we sort of set all the configurations and tune all the dials based on our understanding of the boundary conditions from paleo records. And then we can simulate climate for thousands of years in the past, just like how we use paleo data to extend that record as well. So I'll just dive into the results of this analysis. So in red here, what I'm plotting is the correlation between these two ocean basins as sort of a moving window, a moving 80-year window over the 1900s into the present. What we see is that the decline of this red line here as it goes from positive to negative is sort of that decrease of decoupling that we saw previously. And now what I'm going to show is extending that record further back in time using the paleo data. So this is the relationship between these two ocean basins based on the paleo data. And as you can see, that it typically stays pretty positive, and it has some dips in like the 1800s, but not as intense as what we've seen in the observations. And finally, in green is the series of climate model simulations that also I'm using to study how these two ocean basins are connected. And what we see, again, is that on average, there's pretty good correlation between these two basins, and that there sometimes are some excursions, but not nearly as strong as what we've seen in the last 20 to 30 years or so. And to really drive home that point, what I'm plotting here is sort of a histogram of all of the 80-year windows for the last 1,000 years from the paleo data and from the climate model. And the big red bar is sort of the most recent 80-year period that we've seen in the observations. And this provides robust evidence that what we're seeing here is well outside the norm of what has happened over the last 1,000 years. Very briefly, if you pay attention, you might see that there are some excursions that aren't as intense as the present day, but do occur. And these actually align with periods of very strong volcanic eruptions. So if people are interested, I'm happy to talk about why we think that is as well. But I'll dive into my conclusions for now. So here, what we're interested in is understanding the relationship between the Indian Ocean and the Pacific Ocean on sort of these decadal timescales. And typically, an El Nino-like pattern drives warming, but in recent decades, we see sort of a disruption. And paleo records and climate models show that this change that we've seen recently is indeed unprecedented. So thank you all very much. And I'm happy to take any questions.
That was awesome, Shawn. Thank you so much. I always love learning about paleo, but I have not delved into it myself. So it's always like a really fun, totally different thing to learn about. One of the biggest questions for you in the chat that a lot of people agreed on wanting to know is from What Is My Life 6927. The question is the current damage to coral reefs going to significantly affect how this data can be collected?
Yeah, that's a really good question. I think that yes, absolutely. So, corals are really fascinating creatures. They are really great paleoclimate records because they sort of grow these annual bands, almost like tree rings, right? And we can use them to reconstruct temperatures at sort of these very tight intervals. But a coral is a living creature, and what we've found, what coral experts have found, is that severe bleaching, severe acidification, these extremes that stress the coral can actually affect the way that it records these proxies or geochemical indicators that we're interested in. So oftentimes, for some scientists, you have to do some correction here from the raw data that you receive from a coral before you can actually use it for the studies that I'm showing here. And if global warming and these heat waves are causing more coral bleaching or causing more corals to die, then that might become a greater and greater problem. So yeah, that's a really great question. And it's something that we're still struggling with, tackling with. Yeah.
Just another reason to care about our coral health and
absolutely
hoping to slow it down. Thank you so much, Shawn, for your time. That was such an awesome talk and first paleo talk of the live stream. So thank you so much. Thanks for joining us.
Thanks so much, Sydney.
Of course. Before I wrap up, I'd like to thank everyone again who has joined me tonight while I'm hosting, and hope you've enjoyed learning about the research, people, and institutions that make weather and climate science possible and impactful. And as a reminder, we'll need to reboot the live stream periodically to keep everything running smoothly. And that time is now. So please head over to the new stream to continue watching. You'll find the updated link at wclivestream.com/watch. It's been an honor to participate and hope you'll tune into my talk tomorrow at 10:40 a.m. Eastern Time. And we'll see you on the new link hosted by Claire Singer next. And hopefully she is joining.